I hope so.
I hope so. Okay. Shall we start? Maybe. Hi.
So, is your presentation ready?
I think so.
Okay.
So, then you start.
Good morning, everyone. Welcome to this session of PolInSAR method. I'm Yue Huang. We will have the 5 presentation about the forest tomographic SAR, and after the break, you will also have the session about snow and ice. So, shall we start from the first presentation given by Marco Lavalle? It's about the tomography SAR algorithm in the co-failure mission.
Yes, cool. Yeah. That's good. Thank you, Yue, and good morning, everyone. And thanks for joining for the first talk of the day. I will be giving an overview of one of the activities we're doing at JPL to design mission architecture, and so you see particular co-flyers mission concept for STV. What STV is and stands for, you'll see, I'm sure in the next years, stands for Surface Topography and Vegetation. It's an observable. It was recommended in the Decadal Survey report that came out in 2018. And of course addresses key science questions and application across several disciplines. So what happened after the report, the Decadal Survey report came out in 2018, NASA formed a study team, and so some of us were part of the study team to address the science gaps and technology gaps for mapping surface topography and vegetation structure from space. And so one of the outcome of that report was this table, which we call Science and Application Traceability Metrics, or SADM, to essentially drive and inform the development of an STV mission from space. So we are in particularly looking at JPL at radar architecture that can meet the STV requirements. And so we're interested in co-flyers missions because we basically, if you look at the needs that are listed in the SADM, especially in terms of resolution or repeatability, we're not going to address these needs with a single radar observation. So we definitely need multi-static SAR. The other important aspect is costs. So when you look at the constellations, of course, a single agency, it's difficult to support all the costs. Co-flyers also allow for flexibility and reconfigurability, especially when you look at different options. And number 4, I put here a great opportunity, I think, that all we have in the next 10 years is the ability to add co-flyers to NISAR. Since NISAR will launch in 2024, but will go on for 3 to 5 years, and ROSEL, which will be slated for launch later, a little bit like the Harmony mission. Now, the goal of what you're going to see, and it's the start of an activity, is to identify the most viable TomoSAR mission architecture by assessing the TomoSAR global performance, by playing with different options in the trade space. And now, of course, the challenge is that the trade space for a multi-static SAR mission is complex, and there's a lot of moving parts, and so that's what we're dealing with. Now, the way we're approaching the problem here is to develop a simulation environment. We call it trade study tool or performance tool because it allows us to play with the trade space and evaluate different trades in the mission architecture. Now, one thing that is important here is that we're not looking only we don't have a radar mission in mind. In fact, this trade study tool that we're implementing is also can also fit the evaluation of a LiDAR mission. And so what you see here on the screen is a sort of a higher level view of the trade study tool. We have blue box that are sensor agnostic, so you can apply to different sensor or different architectures. Could be L-band, S-band, or could be LiDAR, like I said. So the tool starts with an orbital geometry and all the errors associated with it, realizes the scene. That could be ice or topography or, of course, forests. We're starting from forest, of course, in this analysis. And then we have some simulation setup boxes that control the flow of the simulations. And then we get into the real important sort of measurement process simulations. That's sensor specific. We're in this particularly for the tomosar or multistatic component, we form the sensor to target geometry. Then we add error sources, generate raw data. So we're going through the full end-to-end simulation, generate 3D tomograms. And that's important in the two boxes that are at the bottom here. We estimate level 3 STV products from these tomograms. And then we extract metrics, which are then compared with the SATM, the Science and Application Traceability metric. So it's an end-to-end process. And we're not really interested in L-band or S-band. We're interested in these products. That's important because some of the simulations or measurements may be just sufficient to get to the STV required accuracy that we're after. So this is sort of the overview. The straight space there we're exploring has several variables. Here I listed a few of them. We are focusing on the formation size and geometry. We're exploring different platforms. Radar frequency, we're focusing on L-band and S-band mainly with a 40 to 80 megahertz bandwidth. Of course, we had to narrow down the trade space just because we have several options. And again, these are only some of the options and parameters that you can play with. You can imagine the SAR instruments has several parameters. And we found that these affect the performance more than others. Radar mode is a strip map or sweep SAR or even HRWS. Real-time versus post-processing poses difference in the way the performance go. The synchronization, whether it's the GNSS only or with this inter-satellite link, positioning and the tomographic algorithms. And today I'll show some of the early experiment with the tomographic algorithms, back projection and beamforming mainly, although we're adding more algorithms. So we're looking at both point targets and distributed targets. Today I'll show only point target simulations. Of course, we have some level 1 performance metrics. Resolution and the ISLR, the integrated side lobe ratios, are the ones that we look mainly, but of course there are all number of other metrics that matter in the mission design. And of course, I didn't say this in the beginning, but this is an iterative process. So what you see here today is just a tool. Again, this is starting in development about a year ago, but it will go on for several years. We have a study that started again after the 1-year study that will last for about 3 years just for STV. And of course, this will overlap and align also with the SDC, the Surface Deformation and Change study. So these are two observables that are conducting at NASA. Okay, so going into a little bit the specifics of what we're thinking. These are just 3 of the main architectures that we're looking at, just for the sake of examples. What we're thinking here is we're simulating ideal case rectilinear orbits. We're usually place that blue satellites as a transmitter. We use NICER parameters or Rosel parameters. These are 2 missions that we use as a reference. The first case is just a sanity check case. It's very simple. It's not realistic. Rectilinear orbits, in reality, orbits are not parallel. They don't stay parallel. They go all over the place because of the orbital geometry. The second architecture is an STV-only architecture where we have 4 co-flyers flying in close formation with NICER or Rosel. Of course, there's a bit of a along track separation. So we have 6 baselines in total. We can do tomography only with the co-flyers or adding the transmitter. This is an option, of course. And then the third option is when we allow a large bistatic angle, 15 to 20 degrees. So we're looking at along track baselines of 200, 250 kilometers. So it's very large. And this is an attractive concept because it can address some of the needs from the SDC community, the surface deformation and change for the 3D deformation vector or compensation for atmospheric distortions. And so we're sort of exploring that third concept to see if we can make both SDC and STV as sort of a trade-off between the 2 observables. And these architecture, like I said already, are evaluated across different options. The first options here is depicted on the screen. It's like I said, a ideal simplified geometry. We're using the SCH reference frame, where S is along track, C is ground range, and height is the vertical direction. You'll see these 3 letters in the next few slides. So just keep in mind, C is the ground range. So we place in this particular experiment one point target here in the center of the scene, where we basically form the sensor to target geometry and we simulate the point target response. In this case, we have a uniform array along elevation. N is the elevation directions. So here's the first results, just to give you a sense of what the simulator does. And again, I call it simulator, but it's really more a trade study tool. You can play with some of the variables and optimize some of the variables, such as the orbit geometry, to get what you want to get in terms of performance. And of course, you can optimize several metrics. But anyway, so this is an example of the point target response for a single target in two different tomographic algorithms, back projection and beamforming. The three planes here are the three-dimensional planes. CNH is the ground range height plane. Next is the height along track plane, and the third one on the right is the height ground range plane. And so that's what we usually consider when we look at tomography, right? So many of the presentations in the past few days were essentially looking at tomograms in the HC plane. So if you see a transect of these two HC plane, so vertical transect, it's sort of illustrated at the far right of the screen. And so we are basically comparing architecture by extracting metrics from point target, from those profiles. And so from these profiles, you can take the resolution and the ISLR. These are just two metrics, the integrated side lobe ratio, that when we can map globally as the orbit change. Now, one can do several considerations on this slide. One of them is, for example, that with back projection, we're definitely seeing a little bit of coarser resolution than a beamforming or Fourier algorithm. You can see also that the side lobe reduces. This kind of analysis is what we're after. The other important thing is that we're also looking at the 3D resolution cell here. And so as you can see between the two algorithms, there is also a difference in the along track and the ground range resolution, which is often something that we don't pay attention to. At least I wasn't really focusing on when I was thinking about different algorithms. So this is a sanity check that we ran by adding more satellites into the simulation. In this particular plot that you see in the left of the screen, we are adding platforms, and we are plotting the resolution extracted from the actual simulation at 4 dB of the peak and comparing with the theoretical resolution. And you see that matches very well back projection. But for the beamforming, of course, we have a slightly lower resolution. Now, this is done in the vertical plane. The other two are the resolution along track and in the ground range resolution. And what's interesting is, like I said earlier, the along track resolution reduces when you look at the beamforming, whereas the ground range resolution changed also from both the back projection and the beamforming. And the reason is because in tomography, we are dealing with the 3D resolution cell. So this is something that often we sort of don't consider. When we look at the 3D resolution cell, we have essentially a ground range resolution that is different from the monostatic SAR. It's not the usual formula that we all use, the speed of light divided by twice the bandwidth by a sort of multiplicative factor. So there is those kind of trades are sort of important in this tool. And this is actually important to consider the ground range resolution and the along track resolution, because that affects the number of looks, which affects the accuracy and affects the final performance. I'll speed up a little bit. So this is a different geometry where we have actual orbits. We design the orbits with the passive relative orbits theory. And so we are essentially looking at orbits that have a minimum and a maximum perpendicular baseline across different latitudes, and of course some cross-track baseline. Along track baselines also to avoid collision. In this scenario, we have different ground range and vertical resolution as the satellites go around the orbits, and also different integrated side lobe ratios. So the takeaway message of the slide is essentially that both the distribution of the co-flyers matters quite significantly, and so we have to consider that when we plan the radar architecture for tomography, as well as the algorithms that we're using, either back projection or beamforming. Moving on to the third architecture, we have co-flyers that are now lagging behind the nicer satellites, again, 200 kilometers or more. And this is interesting because the transmitter here has a different geometry, essentially. There's a large bistatic angle between the transmitter and all the receivers. And you can see that the performance are affected by that geometry, even though we are only doing tomography between the receivers in this particular case. Now, if you compare, just to give you a sense, the three cases, this is a typical point target response where you can see also the ambiguity are not that great, of course. You can play with the distribution to make these ambiguity location larger, but it does show how this kind of simulation, I think, are important, especially when you compare the geometry, when you have four co-flyers lagging the middle image with four platforms in the tomographic processing, and the same configuration when you add also the transmitter in the tomographic processing. As you can see, there is interesting consideration that one can do by comparing just that case. We are also including JEDI height. So you can see here the vertical profile. We're essentially informing the simulation with the waveforms that we take from JEDI, so it's a realistic, as much as we can, simulation. These are used just as a proxy. Of course, LiDAR is an optical sensor, is a completely different wavelength. We're in the L-band or S-band domains, but still, it's a proxy. It's the first steps, the best we can do to get a realistic distribution of heights. And so when we play with these profiles, we can simulate how well the various orbits, the various spacecraft geometry sees that particular target. And then you can start comparing the output profiles from the tomography with the input profiles. Whether that's correct or not, the input profiles probably not the same because LiDAR, like I said, is different than radar, but still it's a proxy. And you can do things like RMSE and correlation between the various architectures, the various profiles. So this is just an example of different profiles obtained by looking at back projection and beamforming. I guess there are a couple of messages. One, back projections seem to perform slightly better when we compare the profiles compared to beamforming or Fourier. The other message is that not all the profiles look great. Some of them are worse than others, although generally the correlation is fairly high, as you saw earlier, and especially when we go into a lower canopy, we see some discrepancies between the input profiles and the two output profiles. My last slide, one promising algorithms that we are adding is the histogram tomography we published this a couple of years ago. It's promising. It takes only one or two baselines at the minimum. Of course, you can improve with multiple baselines, and we're essentially trying to simulate this type of process to obtain the digital terrain model and the canopy height from the simulation globally, as informed by UAVSAR data. This is my last slide. I won't go through all the yes, it wasn't the last slide. So through the points, but I'll reiterate what Francesco Sarti said last Monday or Tuesday, that we have opportunities at JPL to work on for postdocs as well as students to work on different topics, including the one that I just showed. Thank you.
Thanks, Marco. Now we have time for some questions.
Thanks for your presentation. What are the changes you have to get these for on board in flight? What are there proposal for others just theoretical studies?
I'm sorry, the proposals? Or?
You get 4 passengers, and what are the chances you can fly them? You can get them.
Oh, what are the chances?
Yeah.
Oh, yeah. That's yeah. So that's something that we're looking into. There are opportunities in NASA that we can apply to for co-flight for small sats. Right now, we don't have any plans to launch, but everything that is done in this study is done in view of possible opportunities that can come up. For example, 4 satellites is not a random number. There are launch vehicles that can accommodate 4 satellites more easily than others. So that's how we're approaching the problem. But like I said, there are opportunities in the next 2-3 years that will come that we can propose to.
Thank you for the presentation. 2 questions. One is about the, you mentioned different operating mode for the emitting radar using a SCAMSAR or other sweep modes.
Yeah.
Did you find, could you simulate all these configurations using constellation? I guess it's getting very complex. And the second one is, which kind of diversity do you plan to use in the MIMO mode? I mean, you need to...
Yes, those good questions. So first question, it is complex to have there's several options. One could have a sweep SAR or scan and receive on the co-flyers, and that's complicated. You need a large antenna. You need to synchronize tightly. But also you can have sweep SAR transmitters, and so they just transmit and you just receive. So of course the performance will be worse, so you want to have high resolution. So basically that works, and that's actually the option we're looking at. Maybe multiple receivers can look at different options, a different portion of the SWAT, so that's what we're looking at. So when I said sweep SAR, it was more on the transmit side. On the second question, which I forgot. The MIMO mode. So the MIMO mode, diversity, it's TBD. There's code, frequency, which I think Stefano will present. And so yes, that's an issue. That's an issue. But just as a side comment, MIMO mode, from what we have seen so far, adds a lot of hardware complexity. But in terms of performance, it's not impressively better than SIMO. So that's what we're seeing. So. Yeah, Irina.
If you finish in time, we have more time for discussion.
Okay. Yeah. Okay. So just a question from my side, because we have quite a lot of experience now with generating dams, and our view on it is that mostly the dams that are used from scientists are really over critical areas, as for example mountain areas, critical in sense of radar critical, right? Because it's very difficult to get all these geometry effects rid of, let me say.
Yeah.
So, and when I'm looking now to this proposition, I think that's great, right? To do a 3D cube kind of over the years. But how to solve this really over these critical areas where most of the people really like to have a dam, because on all the other regions, mainly they have a dam, or at least a nationwide, but over these critical areas not. And the other big part is forest, right? This is what we also understand. Forest is a big issue which we try now to resolve it differently with different other techniques, like forest height, right? As a different approach, not a dam only, but using other algorithms. So how was your investigation on these a little bit?
Yes, so the approach that NASA is taking is not a single satellite or single mission cannot address all the areas everywhere. And so there is a number of people looking at LiDAR data, for example, LiDAR missions, or data by, like for example, X-band SAR maybe can, with a larger bandwidth, can give you a better resolution, especially in those high steep areas. So that's sort of the approach. This will probably address 80%, I don't know, I'm saying a number, but it will address the majority of some of the targets for STV. That's one answer. The other answer is that we can play with radar parameters. Even if we have only single architecture, we can play with incidence angle, things that TandemX has done, I guess, baselines and resolution to some extent. L-band is limited by 80 megahertz, as you know. We cannot go into very high resolution. So yeah, that remains a challenge, passes, ascending and descending passes. And yes, so that has to be seen with these tools, but yeah.
So I think we have to go. I know that there are questions. I apologize for this. We are already 8 minutes beyond.
8,
So
wow. Thank you.
Blame Marco not to be in time. So the next presenter is Stefano De Baldini from Polim. He represents a French-Italian team, and he speaks about FDM MIMO-SAR tomography from space.
So thank you, Kostas. So good morning. We're talking about FDM MIMO-SAR tomography, and this is the reason why basically it seems pretty clear that the number of SAR sensors is going to increase in the next futures. Those are just a few quotes from the web as of September 22. ISI has planned for over 10 satellites. Synspective, a constellation of 30 satellites. Capella Space, a constellation of 36 microsatellites. So the question is, does that make a new SAR paradigm? Well, I think that we have to define what kind of paradigm we want to consider. For the industry, my take is that the main goal is to improve the current capabilities of SARs in terms of revisit time, coverage. So let's say products that already exist and that guarantee to the industries an immediate return. So yeah, this is a new technological paradigm, but I think that as researcher, it's also our duty and our scope to demonstrate a new paradigm to use those satellites. And this is exactly what this talk is about. This is a tomographic session, so of course I'm gonna propose a new use of those constellation of small satellites to do SAR tomography. Okay, SAR tomography is basically what can give you 3D voxels, so a 3D representation of the scene. For vegetation, I don't want to say it's consolidated, but it's close to it. There have been a lot of campaigns. We can get forest height, we can get the terrain below the vegetation, we can get the vegetation structure, and matter of fact, biomass is going to implement that. It's also useful for snow, and tomography was demonstrated by different research groups to be able to tell you the stratigraphy of the snow, and this is something that can be used for enhanced SWE retrieval. And tomography is also useful for ice, so you can survey the interior of the ice body. But we have to say that despite we had many successful campaigns with ESA, with JPL, with DLR, spaceborne tomography of natural scenarios is yet to come. And the reason is basically temporal decorrelation. So as long as we use a single satellite, we can only do tomography by collecting different orbits. And this takes time. So there is no way that we will ever reach the same performance as an airborne campaign. So for example, for Africa, we had 11 passes. TomoSense is 20 to 30, depending on the frequency. UpTomoSAR was done with 20 passes, AlpSAR with 36, and there's no lab, to the best of my knowledge, with up to 50. So can we go there from space? Before my answer, just let me remark that it is true that biomass will implement tomography of a forest. This is true because at P-band, the temporal decorrelation is predicted to be not so much. So we are currently assuming that we can get 7 passes without being too much affected by temporal decorrelation. But of course, keep in mind that vertical resolution is limited to some 23 meters. So it's not quite the same as an airborne campaign. And when it comes to spaceborne tomography, I personally think that MIMO, so multiple input, multiple output, is the way to go. In very short terms, what does it mean? We assume that all satellites act both as transmitters and receivers. And if you want a very simple MIMO theory, we can say that in the limit of small bistatic angles, we can assume that the data acquired by a given TX and RX pair can be thought of as being acquired by a virtual monostatic SAR placed in the middle. So basically, we have here the 4 MIMO satellites, and this is the virtual formation that you get. And keep in mind that when it comes to MIMO, the key question is how to deploy the real elements to maximize the number of distinct and uniformly spaced virtual satellites. The theoretical limit goes with n squared, if you consider all the possible pairs, including the monostatic. You never reach this limit. There are approximate rules in array theory for a suboptimal deployment. You can go for an optimal deployment by an exhaustive search. It takes some time, but since we are playing with satellites, if we assume 4, 5, 6, 10 real satellites, then this is something that a computer can do. And so, for example, with this configuration, so if we have 4 uniformly spaced MIMO satellites, then we have 7 distinct virtual elements. But for example, if we go to these other configurations, then we have 9 distinct virtual elements. So the deployment is quite important here. We have just said that the theoretical limit goes like n squared. We never reach this limit, and this is the optimal deployment and the resulting number of uniformly spaced distinct virtual sensors for 3 to 6 real satellites. You can see that with 4, we get 9 virtual satellites. With 5 real satellites, we get 13. With 6, we get 17. So it's not bad, but it's far from a state-of-the-art tomographic campaign. So for this reason, we started to look into correlation tomography. And correlation tomography is an alternative approach to tomographic imaging. It goes well with natural scenarios because it needs some multi-looking to work, so it's okay for any distributed scatterers. It was proposed in the context of SAR by Treuhaft, by Shane-Claude, and it was largely considered in the preparation of the proposal for SACOM-CS and Parsifal. So, again, in simple terms, if you assume correlation tomography, then tomographic imaging depends no longer on the number of elements, but on the number of available baselines. That is, it depends on the set of the differences of the positions of the different elements. And keep in mind that by element, we can consider real element as well as virtual element. So this is the game that we can play. We have n real MIMO satellites. This creates up to n squared over 2, more or less, virtual satellites. And the number of differences is up to the square of the virtual satellites. So it's ideally go with the 4th power of the number of satellites. And this is a lot. This is a lot. Of course, we cannot reach the 4th power, but we will investigate now some actual formation that can largely increase the number of baselines. And so let's say that the problem can be cast in this way. We need to find the position of n physical receiving and transmitting sensors such that the set of position differences among all resulting virtual sensors form a uniformly spaced array of a maximum length. This problem has been solved. If you browse the array literature, there are methods to do that. The solution is referred to as minimum redundancy virtual array. There also is a Chinese patent on this. And this is how it works. I have here this example for just 3 real elements. This is the optimal deployment, so it's 0, 1, 4. We have 6 virtual non-uniformly spaced sensors, and this virtual array form a uniformly array of 9 uniformly spaced baseline. So with 3 sensors, we get 9 baseline, with 4, 25, with 5, 45, and with 6, 75. And now we talk. Now we are starting to compare a spacebound mission with a state-of-the-art airborne campaign. We have 2 problems, though. The first one is channel access. So a tacit assumption in MIMO literature is that you can always tell, when you receive a signal, you can always tell which transmitter originated that signal. And to do that, in array literature, they usually get away with that by writing that they use orthogonal waveform. But this is not possible for the case of SAR. And basically, this is a technicalities. It depends on the ratio between the width of the transmitted pulse and the width of your scene. So for array literature, like for an automotive SAR, the area to be seen is pretty small. For a SAR, it has to be very large. So there is no way to do that. And this was demonstrated by Krieger in an excellent paper in 2004. Unless waveform design is coupled with beamforming in elevation, which works, but it complicates the system, or the transmission occurs in separate frequency bands. And in this case, we have an FDM system. It just works. Spatial decorrelation is the other problem. In the array literature, they do not know what spatial decorrelation is. They never consider distributed targets. They only consider points. So this is not their problem, but this is the problem of ThermoSAR if you want to see distributed scatterers like forest, snow, ice, and so on. So the solutions that we propose for channel access, we like to play simple, and so we assume a simple frequency division multiplexing approach, which means that all satellites transmit simultaneously on a different frequency band, and all receive everything. So every satellite receives on a much larger bandwidth. This is guided by the idea that we can increase the number of satellites, since the payload of individual satellites is much more simple in terms of hardware. For spatial decorrelation, the idea is that we need to design the formation to optimize resolution while accounting for which spatial wave numbers are actually captured by the acquisitions. And now we need to talk a little bit about wave numbers. So I need to go for a while into the theory of diffraction tomography. Basically, the diffraction tomography says that the information that you retrieve when you have one transmitter and one receiver can be mapped into a specific region in the wave number domain. So just imagine that you take a spatial Fourier transform of a scene, and so you have spatial frequency that are called the wave numbers, and every bistatic acquisition is mapped to a different wave number. So in a multistatic experiment, the trick is that you have to map the different wave numbers so that you can get a good spectral coverage with no hole, and hence get a good spatial resolution. This is the standard way to do things in seismic, for example. And just to be clear, KZ is here the vertical wave number. Do not confuse it for the interferometric wave number. And so it is a different KZ. When we go to FDM MIMO ThermoSAR, those are the rules to map a transmission at a certain frequency and at a certain receiving and transmitting angles to wave numbers, so KY and KZ. You can see that each acquisition, so each SAR acquisition, each pair of transmitting and receiving sensor is mapped into a segment. Here the continuous segment represents monostatic acquisitions, and the dashed segment bistatic acquisition. The spatial resolution is given by the whole coverage of the wave number domain, so the larger the better. The interferometric wave number, which I call here delta kappa z, is the vertical separation between any two segments. So you can form an interferogram. It just means that you take any two segments, and the usual kz, which I call here delta kz, is the vertical difference. This is not theory. This works. If you do tomography, you form a tomogram here, you compute its Fourier transform, then you get exactly the spectral coverage that is predicted by the theory. So how do we handle the correlation in this way? Well, we can do it in a simple way by evaluating the projection of individual segments onto the horizontal axis, so onto the KY axis. Basically, you can prove that the coherence is given by the ratio of the common bandwidth along KY to the total bandwidth along KY. And on this ground, we can discuss optimal deployment in a graphical manner. Basically, an interferometric pair is marked as valid if we have a spectral overlap, or if we have a decent spectral overlap. And for valid pair, we get the interferometric wave number simply by taking the vertical difference in the KY and KZ domain. And this led us to a principle that we call the minimum redundancy wave number illumination, which basically means that we need to find the position of n physical MIMO sensors such that the set of valid vertical separations among all the illuminated wave numbers, thank you, is as close as possible to forming a uniform array of maximum length. So I couldn't find any elegant solution to do that, so we resorted to an exhaustive search, where basically we annotate for every possible combination the resulting vertical resolution, the height of ambiguity, and the spectral overlap, meaning that we want to have a certain ground resolution. We fixed that, and this is the result. For 4 satellites and for 5 satellites, we have the vertical resolution given as a function of the height of ambiguity, so every point corresponds to a different formation, and the colored line represents to a worst resolution after common band filtering of 10 meters, 20 meters, of 20 meters. And this is just, the bottom panels are just the effective number of baselines, which is just obtained by taking the ratio between the height of ambiguity and the vertical resolution. And this is what we get, the result of the optimization for 4 and 5 satellites. So with 4 satellites, we have the equivalent of 16 monostatic passes. With 5 satellites, we get the equivalent of 25 monostatic passes. I know I'm running out of time, so I just show you some simulation. Basically, we implemented the geometrical simulation by deploying elementary scatterers, and with a total bandwidth of 5 megahertz with some guard bandwidth. And this is the result with 4 satellites. You can see that we can detect the 4 layers very well. This is the ancient algorithm for array theory, which has much larger side lobes. This is with 5, even better, and this is with 5 with the algorithm for array theory. Those are the conclusions. I just let you read it because I'm out of time and I want to get a question. Thank you very much.
Thank you very much, Stefano. Questions?
Too many wave numbers.
Yeah.
Yeah, thanks for the very interesting talk. That's a really good idea. Use the FDM to make the channel access.
It's simple.
Possible.
Yeah.
So I was wondering about when you have multiple the channels access, that will limit the bandwidth. Will it reduce the range resolution or not?
Let's say that the range. Let's say that you need to think tomographically this way. The range resolution for individual satellites is given by the bandwidth of a single satellite. So in this case, we have 500 megahertz. And so with 4 satellites, we have 125 megahertz. And this is the range resolution of individual SAR images. If you combine them all, it depends what to do. If you go for vertical resolution, then we have designed the formation to have a worse ground resolution of 10 meters. And this is what you get for the final product, for the final 3D product, I mean.
So he finished in time. You have now to have the questions. And then you are the next one.
Oh, okay, so I go first. Very interesting presentation, Stefano. About the techniques where we go to the virtual array to the array. That's your proposal. So my question is, what about the radiometry accuracy, radiometry performance?
The radiometric performance. Well, we aren't investigating this approach. I would say it is just as good as the radiometric performance of individual satellites. And we can debate whether with small satellites we get a good radiometric performance. But I would say that this is more related to the hardware.
Yeah, so just looking at this slide, the 500 megahertz, have you looked at into the practical implementation of?
For the moment, we are assuming some guard bandwidth of 6 megahertz, which based on the pulse length, it should suffice to get a very good rejection of the side lobes from the other transmission.
Okay.
Any other comments, question?
Okay.
Matteo? Thank you, Marco.
So how much does your scattering change in 500 megahertz?
Good question. Let's say that if we work a text band, it's not dramatic. Our idea for the snow is that it's not. For snow, I mean, based on the experiment we had, it should just work. I think that also for forestry, I mean, for example, for PolInSAR, there was a central frequency about 400 and the bandwidth that was nearly 200, and it sort of worked. So in this limit, I don't think this is a problem. Might be a second order effect, though, of course.
Oh, it's working. Okay. Just go back to about a little bit of history. 10 years ago, when we developed together the virtual array in the Jobit gas campaigns. So the idea is, can you use that data to validate your concept rather than just simulation? Because basically we had a multi-static acquisition in Jobit gas, basically.
Yes-ish, because the tropiscat array was designed to have a uniformly spaced virtual array. So the baseline differences, it was not designed to optimize the baseline differences. Another problem is that there are no many looks because there is no azimuth variation. And correlation tomography, of course, works under the assumption that you can multi-look a little bit. So yeah, we can do something, but I don't think it's a real benchmark.
Thank you.
So maybe before we move to the next paper, one general question, because we need to have a discussion. And for me, the question a bit provocative is why we try to get with the density somewhere where you already are with phase. So the height vertical resolution remembers me on the density, on tomography. That is me on 25 years ago trying to make 2D SAR images with the highest possible resolution. Today we know that for, except if you look on urban areas, that for distributed scatterers you don't need the sub-meter resolution. So my question is, do we need in tomography to address environmental issues this super sub-meter vertical resolution, which we already get in terms of height sensitivity with interferometry? You try to get something with the density, but you already know that the phase is much better. Just to think and to have this argument and try to understand where we like as a community, do we need this half-meter vertical resolution in tomography and why?
If you want to get a snow stratigraphy, yes, you do. For snow stratigraphy, for sure you do. For forestry, you could argue that maybe a 2-layer model will do. Okay, this is debatable, but at the end, tomography is always a benchmark to validate. I mean, that model is validated against tomography at the end.
The radar world, but not the physical world, because a P-band reflectivity profile has nothing to do with a forest outside.
If you go for a stratified medium like snow or ice, the radar world maps quite well to
but forest
physical
is a stratified
world.
medium. Forest is such a medium, and we know that radar reflectivity has nothing to do with natural reflectivity.
I wouldn't say that it has nothing to do. But anyhow, the case of no ice and probably also subterranean, I think it's a bit different because in that case you have actual dielectric interfaces. So this is my take.
Thank you.
Thank you.
Okay, we can move to the next presentation. It's about the deep learning enhancement of TomOSAR. Its presenter is Serafan.
Doesn't work? Okay. Hello, my name is Sergio Alejandro Serafin Garcia, and I'm presenting, let's say, some of the experiments that we're doing around this idea, deep learning-based enhancement of TomOSAR stacks. And the people that is working with me and my supervisors are Matteo Nannini, Gustavo Daniel Martín del Campo Becerra, Ronnie Hensch, and Andreas Reiber. I like to highlight here that these are experiments and the things we obtain are interesting, but let's say there is also stuff to do, so have that in mind for the next slides. In order to be all in the same page, I think I would like to start doing like a small repass of the TomOSAR geometry and the TomOSAR, let's say, basic context. Basically, we acquire SAR images at different heights, and then we coherently combine them in order to create a tomographic aperture, so we can distinguish different volumes in height for each pixel we have. Here there are some interesting concepts. One is the letter D here, the baseline. That is basically the distance between the flights, and the other one is the maximum distance between the one height and the other one, that is the tomographic aperture. And these values are important because in the question that we have in the right part of the slides, we can see this equation, and one is the resolution for when we focus the information. And we can see here that the attainable resolution for the Fourier case when the baselines are equidistant, it's inversely proportional to the tomographic aperture, and the ambiguity position, it's also inversely proportional to the minimum baseline. This basically means, or the idea that I want to reach with these ideas is that when we group all the acquisitions together and we create this tomographic stack, this co-registered tomographic stack, in general terms, we can say that the bigger it is, the better the quality in terms of ambiguity suppression and resolution that the final tomogram will have. And that's what we are trying to do. We are trying to use a neural network to, let's say, take a TomOSAR stack that we already have when we have a missing baseline and try to use it to generate it. So we have, let's say, a bigger TomOSAR stack, which will mean that after focusing, we will have better tomograms. That's, let's say, the idea behind. For this, we are using an UNet. Basically, the UNet has two parts, a contractive part. With this is a little bit a modified version of the classical UNet that is used in biology. And so basically, we have 5 steps of deepness. When in each step, we have 2 3x3 convolutional networks, followed by a linear rectifier, and then downsampling max pooling layer. And then we have also the expansive part of the unit when we have this 2x2 layer of convolution that like get bigger the feature maps, and then we have two convolutional 3x3 convolutions, and then linear rectifier, and also here we are copying and cropping half of the features from the parallel steps in the contractive path. The inputs that we're using for the neural network are 96 by 96 patches, where each baseline of the Tomosar stack is represented via 3 channels, one with the imaginary part, one with the real part, and one with the amplitude. And in the output, we represent the output with the phase and the amplitude. We are doing these experiments and this test with 2 data sets. One is the 2015 UAPSAR mission over Munich. That is an L-band sensor. We are only using H polarization, and the resolution is 1.6 meter in range and 0.8 meters in azimuth. And the master track is at 12,500 meters, and the slaves are the one displayed in the table. The other data set we are using is the EFSAR mission in 2017 over the test site of Frostham. It's also an L-band sensor. This one has a 1.3 meter resolution in range and 0.6 meter resolution in azimuth. The nominal height is 3,720 meters. And I'm taking only the first 15 tracks that are more or less evenly distributed over 70 meter tomographic aperture. These are the results. For this, it would be very nice to have the laser, but then I will just give you some hints. We can see that the main structure of the SLC is recovered here. Let's say this is an urban area, so the streets and so they look quite similar. Of course, it's difficult in the projection to say this, but for that I have the 2 images in the lower part. One is an amplitude ratio image. And here we can see something quite interesting in this, because the original image has a radio frequency interference, and we can see how the network is somehow filtering it. That's also something we were not expecting, but something that happened. And we can see that in the subtraction. On the right part of the amplitude ratio image, we can see how it's taken somehow away the interference in radio frequency. That's something we'll explore in the future, but something we're not expecting. And then in the other part, we have, as a matter to compare the results in the complex domain, we are using interferometric coherence, where 0 is the lowest and 1 is the maximum. And we can see here that in certain areas, actually, the results are pretty well or pretty close between the artificial and the original SLC. Here we have the histograms, where you can see that in the upper part of the slide, we see the amplitude in decibels and the amplitude in linear scale. And we can see they are quite close, but there's still work to do. And then we have the scatter plot. We can see, let's say, the SLCs are close. For the case of Frosken, we have here again the results, and here there's where the problems maybe starts. We can see here how in the interferometric coherence that in the forest areas is actually pretty low, which is bad, but also expectable since it's a bit more, there's way more randomness there, and it's logical that for the network it's harder to learn it. But in the amplitude ratio, there is really not that much to see. And then also in the interferometric coherence, we have these strides that we also don't know exactly where they came from. Let's say the logical answer would be that it's because of the patches, but it's not because of the patches. It has nothing to do with that. I have tested a few times. We have some ideas, but well, let's say for now that's that's what they have. Then here we have the histograms. In this case, actually the results are way better, and as we could see also in the ratio on, they are quite close between the original and the estimated one. So yeah, here I think there's not much to see. And maybe the most interesting slide here, and where probably I should have ended the presentation, is this one with the interferometric validation. I like to call this slide like the face is not only bullshit, because here in the right upper part we have an interferogram with the original SLCs between the first and the fourth light, and then just below it we have the interferogram between the first and the fourth baseline, and we can see they're actually similar. So this means that somehow the network is being able to recover at certain point the phases, which should be a good indication that we can actually perform tomography. We also subtract the phases, just lower the optical image, and we can see also there is plenty zeros there. So somehow this is a good indication that what we are doing makes somehow sense, and that we can continue. But I mean, for me, it was a bit bad not to put tomograms, so I did maybe a trick experiment where I also have here the interferometric coherence between the original and the artificial for baseline, and we can see also here that for some reason it's actually quite similar. Then here we have some tomograms that it's over a surface. This is the FSAR mission, and in this case I only took seven baselines. That's the first tomogram that we can see where like is only original data, and then in the second tomogram we can see from like going up and down, up to down. I extracted one baseline, and we can see how the tomogram got worse, and then in the final one I input the one that I generated with the SLC, and we can see how the first lobe after the main spectrum of the surface decrease the power. That's somehow, it's a good hint, but of course this is like a kind of trick experiment because I made worse the tomographs in order to, let's say, make more impactful the addition of one baseline. The conclusions are basically the ones I mentioned, the things that we discovered with the radio frequency interference. The good news is that somehow the phases are being able to be recovered, but we still have plenty of work to do. So, yeah, that's everything.
Thanks. It's a very nice presentation. So, anyone have some comments and questions? Okay.
I don't know if I understood correctly the objective of your approach. You have a scene with a very low ambiguous height, and you have replicas. And do you want to simulate data so that you improve this ambiguity when you perform tomography? Is this the objective of your approach?
No, the objective is estimate and use SLC in order to decrease these ambiguities.
Okay, then you want to, in fact, to filter the ambiguity and to choose the correct one.
Yes.
Okay, does it happen that you select the wrong one? Because when you have ambiguous replicas and you have a very regularly distributed baseline set, you know, it may be hard to select between one replica and the original one. Of course, we know it's on the ground, but the algorithm doesn't know it, no?
Yeah, it happens. So I was hesitating in putting the tomograms, because of course I selected a case where the impact of the addition it's high. But I don't know, is that the question?
Yes, in fact, when you have several replicas, and it happens with the Capon beamformer, sometimes it does not select the one you expect.
Yeah, exactly. Yeah, so yeah, that happened. I put here an example where, let's say, it works nicely, but it's tricky.
Okay, no problem.
Yeah. Thank you.
Thank you for your presentation. So basically, that's when we're dealing with this interferometry or tomography. So basically, we're dealing with the geometry information. So in your model, how can you handle that information? Basically, do you using like the factor phase too high or KZ information or something like that in your model?
I'm not understanding the question.
Okay, so how can you handle the geometry information in your model?
That's not an issue I've been facing so far, to be honest.
Okay, thank you.
Okay.
Very nice presentation. I have really a similar question. I mean, to me, it is not very clear how, let's say, you provided training information. I mean, with the DUNet, you have to create patches. Of course, you have to create, they can be also multi-channel patches. And to me, it's not very clear how, let's say, what do you fit in these patches? Just, let's say, the complex information, or do you add also all the geometry layers that can be extrapolated from the co-registration analysis and whatever processes that comes before?
For now, we are feeding only the SLC. So each SLC is transformed into 3 channels, one with the real part, one with the imaginary part, and one with the amplitude. The amplitude is added there to help the network to have it, like, consider it into in the processing. Is something that is something does in deep learning. We are, for now, the experiment, let's say we have a TomosR stack, and we are taking one baseline out, and we are using that baseline as a target for the training.
No, I got this, but as was pointed out, I'm wondering if you had, let's say, all the geometric information, if you, in the patches that you provide to train your network, you should be able to give, let's say, a very multi-layer stratified information. So you can create, I don't know, a training data set that contains the real, imaginary, KZ, all the other angles that you can calculate. I mean, in order to feed the network also, not just with, let's say, the signal information, but also with all the geometric information that maybe might give, let's say, a boost, maybe not. I mean, of course, this is a black box heuristic, let's say, approach. So just, let's see, I'm wondering what will happen if you do this.
Yeah, I think I got it now. Yeah, like we especially with the cassette, we will be, it's an idea that was around, like, to also consider it as a channel in order to, let's say, like the network to consider it during the training. Yeah, it's actually a good idea. Thank you. We will look forward into that.
Thanks, but I have really a similar question. Okay. Thank you very much.
Thanks to you. Okay.
Stefan already introduced the concept of correlation tomography, and now Roman is going to speak about multi-frequency coherence tomography over forest areas.
Good morning, everyone. My name is Roman. I'm a PhD student at DLR in the PolInSAR group. The number of satellites working in different frequencies is rising. Therefore, there is a need to find a way to use the data from them in a more coherent way. In this talk, I will share with you some ideas of how to use this multi-frequency data for reconstruction of the vertical reflectivity in forests. So the title says multi-frequency. It also means that we use data from different sensors, therefore different geometries, and with working different frequencies, acquiring over large time span. To address this objective, I didn't want to miss a chance to report first impressions from the Gabon Next campaign, which was taking place just a few weeks ago. More as a broad and more comprehensive overview of the campaign will be given by Irena in the next session. And here I just wanted to use some of the data to address my objective of research. So we are in Gabon. It's very warm. We are in the middle of the transition between wet and dry season. It still rains from time to time, but already not every day. And this is an example of the optical image taken by a smartphone from this plane, Dornier, where the FSAR system is installed. You can see that the quality of the smartphone image is remarkable. This is the city of Libreville, and this is the test site, Monda Forest. It's a national park. It's a protected area, but still it has a lot of disturbances which are induced because it's close to the city. Now let's look on a radar image. So this is the image which was acquired in 2016. And now we have also the image from this year. You see that we have now just a smaller patch processed. Oh wait, this pointer doesn't, yeah. But it's just because we processed only a smaller azimuthal patch just to reduce the processing time, because I didn't have time to process the whole image so far. But this smaller patch in azimuth is processed in a fully polarizational and tomographical, the whole tomographic stack was processed in both L and P bands. We have 12 passes in both years, and they are acquired in exactly the same way, so it's exactly the same incidence angle and exactly the same baselines. If we look, where is this? It's how the plane is. So it's a right-looking radar. The plane was flying from here, from the ocean towards the land. And this is the snapshot from the flight radar website. You can see that we fly in these weird shapes, but it's actually here. You don't see it from this extent, but these lines are super straight. So it's important for tomography to maintain very straight lines. And this time, the pilots were able to maintain the precision of the lines within 1.5 meter, 1 meter, 1.5 meter in both vertical and horizontal directions. And therefore, the quality of the tomograms which we have is quite good, and it's comparable with the 2016. So these are the first tomograms we produced. You can see here that there is a bit of a shift between them. But it's just because we still need to apply additional phase calibration, but still these tomograms are seeing the same now, as you can probably see. And so what we want to do now, we want to understand if there is any change between the two different years. One is acquired 2016, another 2023. How to detect the change? One way is to find some reference data. It can be, for example, LiDAR data. We have 2016 LiDAR. We will have soon the LiDAR data from 23. Another way is to also try to understand what's happening in between, right? If we have some information in between these years. We don't have, however, any tomographic information in between, but we have interferometry in between. We can take, for example, TandemX data and try to fill in some information from interferometry in between these years. So these are interferometry, and they cannot produce tomography from that. But maybe if you, as Stefano was saying, there is a way to do some profiles. And let's assume for now that I was able to produce some profiles in between. How I did it, I explain in the next slide. But the idea now is that I have some TandemX acquisitions from 15, 17, 19, and I want to see how my profiles are developed. It's a different band, but still we can probably see if something is happening. So how these profiles are produced? So again, we go back to coherence tomography. The idea was proposed by Shane Cloud some years ago. So basically, we want to use now the information from interferometry, from coherence, and to reconstruct the profile. Normally, what we use this equation for is we use it for forest height inversion. But in general case, this equation is not applicable for anything. So you cannot use it for even forest height inversion, not to mention the coherence tomography, the vertical reflectivity reconstruction, because we have here a continuous function, and here we have just a complex parameter. Therefore, if you want to use this equation, you need to parameterize your vertical reflectivity. Normally, what we do, often for forest height, we parameterize it either by exponential function or Gaussian function. And here in the coherence tomography, the idea is to decompose the profile onto some basis. So this is an example where I decompose the profile onto some basis. If we want to reconstruct the function exactly, you need to use an infinite series. But if you just approximate it, we can use some number of coefficients, some number of basis functions. And you use this equation. You just put this decomposition here. And once you've written it like that, you have just a linear system. So you can add baselines. This is a single baseline case when you reconstruct only two coefficients. If you add baselines, you can reconstruct more coefficients. However, if you add baselines, it doesn't mean that necessarily you would improve the quality of reconstruction for several reasons. I will not mention it here. So now I concentrate only on a single baseline reconstruction. So we have two linear equations. We want to find two coefficients. And we do it like this. Yeah, so I forgot to mention that since I don't invert any more forest height, I would like to invert the vertical reflectivity, so I need to feed somehow this equation with the knowledge of ground phase and forest height. And I take it from my tomographic profiles, which I have. I estimate the grounds, and I estimate, it's not exactly forest height, it's kind of forest height, which I just take as the highest peak in a tomogram. And I use this box where I apply the coherence tomography. So one important question here is which basis to use. Because since we work only in a subspace, the basis which you use affects the quality of the reconstruction. Originally, the Legendre basis was proposed to use in this method. And here, since we have data from different frequency and we want to combine all of them, the idea is to use basis from one frequency and apply this basis for all other frequencies. So this is the P-band basis which I derive from P-band profiles. They are derived in a very simple way. We just take all of the profiles which are available, we put them into some matrix, we derive some what we call profile covariance matrix, and these are just orthogonal functions which we will use as a basis. And now let's look again in the profiles which we have. So that's what we have. It is our beamforming profile. These are our PCT profiles, which are inverted using the same basis as which we derived from here. And we can also do the same for P-band, right? So we can apply the same basis for P and X-band and also repeat procedure for P-band. So now this was the beamforming, this is the PCT profile. And there's both advantages and disadvantages. Some advantage of that is that you can kind of have the same basis and you can more clearly see development of each of the component over the years, because they look a little bit more clean when you do it like that. You can repeat the same for L-band. I will not stop much on this. So for L-band, the profiles are not looking very well because the profiles were, the baselines were optimized for this test site for P-band acquisition. Therefore, L-band has a lot of side lobes. But still, the idea is that I want to try to say here is that I kind of use now same P-band basis across all of the frequencies. And I reconstruct the profiles in a kind of coherent way. However, since we use only one baseline, if you have temporal decorrelations, it affects your performance. We estimate the ground phase from external data, so from tomographic data right now. Therefore, if you have ground errors, it will also affect the profile reconstruction quality. It also depends on the basis which you use, since you only work on a subspace. And also there is, again, you work in a subspace, so there is nothing which tells you that you will have a physical profile at the end. So your profile, which physically should be positive, while reconstructing it can produce some negative values. So we need somehow to also establish a quantitative assessment of the profile which you reconstruct. And we propose to do the following here. So let's look again into tandem X acquisitions. So these are both test sites are now shown, but let's keep focusing on the Monda forest only, it's here. And we have different interferometric acquisitions with different baseline levels. What I didn't mention so far is that what kind of wave number I was using for coherence tomography reconstruction. The wave number which you use might affect a lot your performance in case if you use a basis which is not very fit for your frequency and for your forest. Therefore, it's important to use the basis which you can use and reconstruct the profile from just a subset, from just a smaller number of of coefficients. So, but your profile, if it's correct for one baseline, it should be also correct for all other baselines. So, what we propose to assess the quality of a reconstructed profile, let's take one baseline. Now let's go back. Let's take one baseline. Let's say we take this one with capacitor 0062, and we try to invert the coherence tomography profiles. And then we try to fit this equation with the profile which we reconstructed. So this would be our modeled coherence, and this is coherence from the data. If we compare the coherence from the data and coherence which we model with the profile which just inverted, then they should be exactly matching, right? Because we kind of solved back and reverse problem. We found the profile from this equation, and then we feed again in the model, we get exactly the same. But if you use another baseline, they will not match exactly. And the mismatch will be larger if you use much different wave number value, so much different baseline. This is an example where it actually worked well, because I used the basis which was optimized for X-band. But if for other types of bases, it might not be working well. So you can see for this baseline, it works still well, but if you go to larger wave numbers, there is some mismatch, but it's not a large mismatch, I would say. So, but a lot of deviation. Good. So this is a quick summary. Yeah, so the idea is quite simple. We just want to detect the change between different years. And since we don't have any tomography, we'll try to produce profiles between them from coherence tomography using different band. And we use the same basis for all of the frequency. And we try to then validate the resultant profile using coherence again. Okay, so as a last impression, the Monda forest is not famous only for its interesting forest and beautiful radar images, but it also has this amazing hike which you can make there. You can go by car from here, you can park your car here, and you can start the hike. You can go to this forest. We arrived in the rainforest just during the rain, and you have to wait until the rain stops, and then you can start. And you can go through some obstacles and arrive into this beautiful tropical beach and play football with these guys. Thank you for listening.
Thank you, Roman. Questions? Marco, Stefano. You are close with Sara.
Just a curiosity on how did you, the upper limit of the integral in the PCT formulation as the 3 height, how did you?
It's from tomography.
From tomography. Okay.
I have 2 questions. Actually 3, but the third one is about the tropical beach, so maybe we can talk about this later. So the first question is about the radiometric output of coherence tomography. Maybe if you can go back to the slides where you compare the P-band tomography, and because you also tried PCT at P-band, right?
Yeah.
Okay. So can you comment on the radiometry of P-band PCT versus P-band tomography?
I didn't...
This is it, no? This is the upper panels. Oh, okay.
I didn't really look into the comprehensive radiometric analysis of the profiles. I just first results. Yes. From here, from such resolution, it's really hard to make some assumptions. I mean, I can only from here try to see if there is some change in the ground to volume ratio, or maybe if we can see some third layer at some of the places here. But from more than that, I'm not sure I can say.
Because so if I compare the 2 upper panels, the ground to volume ratio seems to be pretty different, but maybe the normalization doesn't help. So
yes. That's something I still have to analyze a bit more. Yes.
Thanks. And then the other question is, so if I take a look at the 3 PCT panels for X-band, they look pretty much the same.
Except for this one.
Okay.
Except for the 2015. Because 2015 is having a significantly different baseline. So baseline affects a lot the performance. So just from looking into PCT profile without having in mind all the pitfalls which you have there, it's hard to really compare them. But I would say that here the change is not very present, because the forest here is developed already, and it's still a protected area, but here, this area is closer to the city, and it has shorter forest. And here, I would expect some more changes, but it's still, I have to understand these changes a bit more.
Okay, thanks.
Nice idea. I was wondering, so when in this approach you make the assumption that the physics are very similar, or there's some physical invariance between the two acquisitions, that you can estimate some characteristic of a P-band profile with these X-band interferograms. Did you have to compensate for the penetration of P-band into the canopy? Normally the peak of reflectivity is located below the LiDAR treetop height estimate. Did you have to take into account this fact in your approach?
So what I would take into account is to cancel the ground from P-band before applying the basis for X-band reconstruction. So these are results, because campaign finished very few weeks ago, I didn't make a comparison with ground-cancelled P-band profiles. I just used HV polarization here. But yes, if you ask me, I would start with using the P-band profiles, ground-cancelled ones, so some SKP decomposition or something.
And a very quick one to finish. Here you're using your your own basis, you estimate from the P-band data, but the problem with this is that then you may have some problem of positive semi-definiteness, and when you make the fit, do you plan to use a more simple basics like some Diracs or very some shapes that don't have this problem of doing the fit, doing the coherence tomographic fit?
I'm not sure. So you speak about positive semi-definitiveness.
Yes, sometimes
when I derive the profile, because when I derive the profile, my matrix is positive semi-definite. But once, but the profiles which I use, which are from PCT, can have negative values.
Yes.
It's not. They are not physical at the end, the profiles, because it's just a subset. Therefore, you need to have it in mind. So there is some maybe relative information of the reflectivity, but the absolute value is not very much physical, I would say.
Thank you. Yeah.
Maybe a last question to close the loop to the question to Stefano. What do you think is the effect of the vertical resolution of the starting tomographic stack in order to retrieve a basis?
I mean, it's of course depends on the forest. If you expect some layers there, then of course it's better to have much better resolution. If you cancel the ground, so the resolution is important for the ground. So if you, therefore it's better to have the profile which are ground cancelled. But if you use the profiles which include the ground, then you might have problems because at the end you want to use volume coherence and estimate volume profile.
If there is no other question, then I think we can thank Roman.
Thanks, Roman. And the next presentation will be given by Matteo. It's the last one in this session. It's about the linking changes of PolInSAR 3D reflectivity profiles and the PolInSAR measurements in forest scenario.
Okay, thank you. Thank you, Yuan. So welcome to this presentation, and we like to make, so me and my co-authors, which I like to thank, which is Noelia, Roman, and Kostas, we like to make a few points about if you have a structural changes on ground in forest stands, how do you see this change in tomographic reflectivity profile? That's one point. The second point is, can you, say, link this reflectivity profile change to a change in interferometric coherences? and I will tell you why we think it's important also to address this point. Of course, so we have done this based on this analysis based on real data, and I hope at the end of the presentation I will not have more questions than answers. And so to start, of course, first of all, you need a forest that change, and you also need a consistent interval of time so that you are able to observe this change. So we take this forest here, which is the Froscham forest, still close to the Traunstein forest. It's basically the same test site that was using Noelia in her presentation yesterday. And we had 3 LiDAR acquisitions. So we start in 2016, 2018, 2022. And just by exploring here, for instance, here we are plotting here just the LiDAR first return with 1 meter resolution. And just by exploring this in different stands, then you can start to understand which kind of changes you can find in this forest. Of course, you can have stands, for instance, this one. This is a rather heterogeneous stands and with many species and so on. And here you don't have relevant changes. Some here, and of course with time there are some clearings that appear, but apart from this, then you don't see big things going on. You have also younger stands in which they are left as they are, and indeed you see some relevant growth, so several meters in principle here. We saw from the LiDAR data you can account around 1 meter per year of growth. But of course you also have more drastic changes. So this is basically forest management, where there are big stands which are, quite some amount of square meter which are basically cleared. So this is just to reduce forest volume. And you see here how this is increasing with time. So this is somewhere here. And you have also a bit an intermediate case, which is basically thinning, in which you have, so you start from a situation like this, and then in between a few of the trees, they are cut. So this is for several reasons, among which also, it could also be to allow the younger trees to grow. Now, of course, the question is, this is just from a qualitative analysis. The other question is also how can we go a bit more quantitative and then to try to identify where the changes are and then to look into our radar data to find them. And we were just going very simple. So what we did, so we first of all reduced the resolution from 1 by 1 meter to 25 by 25 meters, because this is a resolution in which you can also retrieve your tomographic profile, and it's rather significant to see these kind of changes that you have in this test set. We calculate the top height, so, and just by averaging the tallest first returns in this 25 by 25 meters, and then we calculated the mean height, still in this 25 by 25 meters. And of course you have, now you can do this. So in particular for this transect here, you can do it, so for the top height, I was just plotting one of them because we were doing it for the 3 years, but I was plotting one of them because you don't have, especially here, you don't have relevant changes in top height. But in some places, now you start to see changes in the mean height. So, and for instance, here, the mean height is increasing, while here and here you have some significant decrease of the mean height. And this can come, for instance, from several situations. I was just sketching a few of them. For instance, here, when you have an increase of mean height, it could come from something like this, in which you have, in principle, you have an increase of the occupancy of space because the tree grows, so they don't grow in height, too much in height, but they grow, of course, in the horizontal dimension. They occupy more space, and therefore your mean height, so if the top height is here, your mean height will increase. When you have a decrease of mean height, however, this can be for several cases. Here I was sketching just a couple. So for instance, if you are in an homogeneous stance and then you cut a few of the trees, then you start to have gaps in between. And the same also, this doesn't need to be an homogeneous stance like this, but you can also have some more vertical complexity. This is just to say that behind this mean height, there are many situations. We don't claim that we have a clear structure index, but we just like to say that with this, we can distinguish, or at least find out a bit what is going on in our data. Speaking of which, we also have 3 tomographic acquisitions to look into. So 2017, 21, and 22. So they, let's say so, beginning and end, they match quite well the LiDAR. In the middle, it's a bit, you have already a difference. And indeed, if you start to explore what you have in the LiDAR and what you have in the radar, you start to see also that here and there, that there are differences, but they are just on limited surfaces. So now what we like to do, so we took the same transit of before with these kind of changes, and then we calculated the tomographic profiles. There are 3 tomographic acquisitions, there are 3 different baseline sets, but of course they are sampled more or less in the same way. So what we could do, we could first of all take all the tomographic acquisition, just interpolate the different vertical wave numbers so that we get to a set of same vertical wave number, and in particular we went down to just 5 tracks with a vertical resolution of 15 meters. So this is sort of low resolution, but of course with this kind of top height you are still able to distinguish scattering contributions. So that's the initial situation in 2017, and you see you have quite a variability of profiles through the transect. When you go in 2021, you have a drastic change of profiles. So, and in particular, you see 2 things. The first one, that this variability, strong variability of profiles, especially here, is lost. And now, basically, you see profiles which have a very dominant contribution on the top. And on the other hand, however, now if you try, of course, you don't have a lot of change here, for instance, between 2016 and 2018. Here, looking in the images was difficult to say if this was indeed the case also for 2021, maybe yes. But if this is the case, now you see that for other reason, you have a change of profiles, you know, this change of profiles now, it's difficult to say if it's because you changed the structure, so the biophysical structure in the background, or if it's just because of the electrics. But now if you look at the acquisition of 2022, the last one, now these look a bit more similar to this, and therefore basically what you see here is just the electrics. So, and this is, for us, it's a seasonal change. So you start from a situation in which the leaves are developing. You end up in a situation here in which the leaves are there. Maybe it was also warm these days. It was transpirating after a dry period, who knows? And then here, basically, the leaves, they're starting to be gone. So, and this is what affects your change here. But now, if we take the longest period of time, and we go to see if you have these structural changes of before, let's focus maybe on the first one. Here we say the mean height increases, maybe you have more material on the top. And indeed, you see that here you have an increase. After these 5 years, you have an increase of power here on the top. So it's something, of course, it's something more that you would like to see than what you expect, but this is consistent, for instance, with this structural change. The same is what you have afterwards when you reduce the mean height, so this means you lose material on top, and indeed you lose also backscattering on top, which is not reflected in the middle when you have this seasonality. What happens then next? Here is where you have also the other bigger change. And you see here where you have this drastic change of mean height, you also have a drastic change of profile. From being canopy dominated, you have it now ground dominated. But also here that you have some reduction of mean height, you are actually, let's say so, you don't have the same change of profiles. I mean, you have a change, yes, but it's a bit in the contrary direction. So you see here from low canopy scattering to high canopy scattering. So again, this means that yes, you have a structural change, but superimposed, you also have again at the electric change. So now, if we like to characterize them, so to go a bit forward, what can we do? The first thing that we can do is, so we take 2 acquisition times. You have time 1, time 2. For the 2 of them, you have 2 coherence matrices. The easiest thing to do is just to consider the difference, and then to decompose this difference into a basis. It's not like in the presentation before that the basis in the profile domain, now the basis in the coherence domain, and you will understand in a while why I like to have it in the coherence domain. Now, of course, if you decompose this difference, now just eigenvalue and eigenvector decompositions. So, but in principle, long story short, is that your profile afterwards at this second acquisition, you can write it as the profile as the first acquisition plus the linear combination of the eigenvector profiles, the difference eigenvector profiles, weighted by the eigenvalues. And of course, when you have a positive eigenvalue, means that this is a contribution that was increasing, its power was increasing from the first acquisition to the second. And when you have a negative eigenvalues, now its contribution power was decreasing. So this is how we interpret this. And of course, here you have, if you like to see the eigenvalues, this is how they look like. In principle, you have 5 tracks, 5 eigenvalues. So you have the maximum positive, the maximum negative. You have also something in between. But in principle, in many cases, you see that what is in between is 10 times lower than what is at the extremes. So in principle, this means that you can start to think that you can characterize your change just with the maximum positive eigenvalues and the maximum negative eigenvalues. And indeed, now, if you take the corresponding eigenvector profiles, so this is what you get. And you see that you have, let's say so, you have a lot of dominant contribution in these eigenvector profiles, which are between your ground and your canopy top. So this is something that it's related actually to the forest. Sometimes, however, they are outside. And this is related, for me, they're related to the side lobes. So this is because it's maybe an artifact in this, in the whole processing. So for instance, because the interpolation that you need to make to bring back everything to the same geometry, there maybe it introduces some artifacts. However, this does not stop our analysis. It's interesting to see what happens in actually our reference points. Now here, you increase mean height, and you have an increase of power in the top, and a decrease of power close to the ground. And here, you decrease the height, and indeed, you decrease your power here close to the top. Same things here, where you have where you have this decrease of mean height. It's consistent with what we have observed here. And then here, as we observed before, now here you are conditioned a bit by this side lobe change. But in principle, you see that you need to increase the power. Your relevant contribution is an increase of power here at the top of the canopy. Now we can go a bit forward. So we make an additional assumption. We said we can live with the maximum positive and the minimum negative eigenvalues. And working in the coherences, this let us make this approximation here. So that in principle, what we can do, we can take, and so you work with the coherences, but at the same time also your vertical resolution is not too high. So this means that you can consider your, or you hope you can consider your eigenvectors as steering vectors. So this means that the underlying change is just caused by, you model them like Dirac deltas. And if they're Dirac deltas, you end up just needing the heights where this change occurs. And if this is true, this is something that it's good news. Why? Because then if you just need heights, so you can measure atomographic profiles at one instant. And if you like to see the reflectivity change, you just need 1 or 2 interferometric acquisitions. You don't need more. So you can live already with this low-dimensional observation space. And now we are approaching a bit also that, I mean, maybe the important part of the presentation. So we just calculated now the heights at which, according to this assumption, we calculated the heights at which you have the increasing power, so in which you have contributions with increasing powers and contribution with decreasing powers. And first of all, if we plot the heights along the, so for the whole test set, you see that you don't have noise, you have patterns. And the question is how to interpret these patterns. And we start, for instance, to compare these patterns with the change between the difference between the top height and the mean height, which means that if this difference increases, means that your stance is becoming sparser at the top for what we have said before. If it increases, means that it's becoming denser. So, and in particular, let's go here. So if we follow this first block, just stay on the diagonal. If you stay on the diagonal, you have, for instance, here red, which means your stands here are become, because of the thinning, they're becoming a bit sparser on the top. And indeed, you increase power at the ground. And when you have some relevant decrease of power, you have it at the top, which is consistent with what you like to see or you would like to see. Of course, this is not everywhere. For instance, here, you have a bit the opposite. So you actually increase power close to the top because you have maybe a dielectric signature superimposed to the change. Now you can also analyze different parts. You basically get more or less the same story. So in principle, you can start to this means that you can start to interpret these patterns with the actual structural change. Of course, under the boundary conditions of your dielectric changes. Now, something interesting, so it's also that, for instance, you see here you have a significant regrowth if you consider the change of H100, and indeed you see that you have a significant increase, or you have an increase of power here for positive heights, so above the ground, and some decrease of power at the height of the ground. So this is something, it's still to be assessed because these are lower stands, but it's something that it's there and seems to be consistent. Of course, there is also another thing that I like to add before concluding, which is, so up to now we were looking for these structural changes. Is there a way in which you can maybe attack the dielectric changes and maybe try to separate structural and dielectric changes? And here now we started to look at polarimetry, and we separated, we looked for the channel with the maximum ground to volume ratio and the channel with the minimum ground to volume ratio. We got the profiles, and since this is a low resolution profile, then we interpreted the ratio between the power at the ground and the power of the volume as a ground to volume ratio. So in 2017, you have this situation. When you go to 2021, you actually have this. You have a drastic change. And remember, 2021 with respect to 2017 was the acquisition which was mostly impacted by these dielectric changes. So you change basically not only where these 2 points, minimum and maximum ground to volume ratio are, but you change also their distance. So in principle, this may tell that if you like, so you should not rely only on these height positions, but you have to rely also on other parameters, and especially these PolInSAR parameters. And I'm at the conclusions. So now, of course, so the good news, what we have found is that you have these structural changes in the profiles, or at least you have changes in the profiles that you can interpret based on the structural changes. So the potential that we see, one potential that we see is that you can locate this three-dimensional structure just having an initial tomographic acquisition and an interferometric acquisition afterwards. This is one possibility. The challenge that we see is that you need, of course, so the biggest challenge is the separation between structural and dielectric changes, having in mind that both of them are information content. The perspective is that we have a rich observation space. You have interferometry, you have polarimetry, and you have polarimetric interferometry, and you cannot neglect the one in favor of the others. But this is something that we need to understand better. We are not so far, and in particular, we also need to know how much a change actually affects a tomographic and an interferometric change. That's all from my side, and now I'm happy to get your questions and your feedbacks.
Thank you, Matteo. Last round of questions before the coffee.
Thank you, Matteo. So my imagination is a little bit fantastic. That so basically that we have the data at different time. So the idea is we can decode the single loop complex data at different time, and we can combine it in a certain covariant matrix for different time to see if there is something like stable target and changing target, and compare with your technique. Is it possible?
Yes, you can also even do more. So let's say, so here I was starting to do something similar just by taking the difference between the covariance matrix. You can play this game in many different ways. Of course, what is not addressed here is the role of temporal decorrelation. And this is, so when you have temporal decorrelation, how you can use it to get changes, even there. So to extract the information content in terms of structure and in terms of the electrics and so on. And this is, it's very relevant with all these missions that have a revisit time. So of course for biomass, but if you think also Roselle, and is there any chance for zero baseline missions? So if you have a profile in P-band and you have a zero baseline mission in L-band, can you take the zero baseline coherence and get some change there? So that's very challenging, and you know, it's just another question on the table.
Thank you.
Marco?
So you mentioned polarimetry in the context of PolInSAR. I was wondering if you believe that PolTomosAR, so polarimetry in the context of the full vertical profile, can be beneficial for this. So what is the role of polarimetry for layer by layer, do you think?
In principle, with polarimetry, you have, so it's not only channel, you have a way more to try to interpret these profile changes, and then you have a full coherence region. And you may also explore this to get your changes and to separate your changes, not only from a tomographic and an interferometric acquisition tomograph, but from a tomographic and a polarimetric interferometric mission. We are not so far to have a cooking recipe and to an understanding about this, but I think it's there, and we need to explore this.
Okay, thanks.
Tui and Andreas, ladies first.
Thanks, Gustav. Thanks, Matteo. Yeah, you mentioned that the challenge is to separate between structural and dielectric changes. It's a really a good thing to mention.
Mm-hmm.
We have the change in dielectric constant during the day and
yes.
And across the seasons. And so, did you look at the change at different time of the days, diurnal change?
We have the data, but we didn't have the time to have a look at it.
Okay.
So we have it actually in the very same forest, but also in Gabon.
Yeah.
So
okay. So it's.
But of course, the problem there is a bit the sampling during the day. So and
okay.
even less we know what to expect. So if you have a ground-based system, of course you have a continuous sampling.
Yeah.
And in that case, of course, you can track. I remember these results of the Tropis, the Tropis cut. Just with phase centers, you could track the changes of the water content. And that's, of course, it would be very nice to have something like this. Yes.
Thank you.
Thanks a lot for the presentation. So this is inspiring. So concerning the use of LiDAR data to detect if the forest is growing or if changes in density, it's for uneven forest it's quite difficult. So I'm not really convinced about this difference between H100 and mean forest height. It could be also, so if you get change there, it could be also a result of growth in certain height layers.
Mm-hmm.
So that's a little bit more complex. Maybe you can comment on this?
Yes, so let's say, so also for us, we have a similar idea. So let's say, so we had a look, so starting from just a qualitative look of the maps, we saw the kind of changes that we had there. And we thought that just tracking the top height changes, I mean, tracking the canopy height models in a lower resolution, in this case, could tell us something of what is happening. But of course, we don't think, or at least we have no proof that this is something that is general. So we need something more, and that's something which is also sensitive enough. So, and of course, yes.
Any other comments, questions? Maybe, someone? No, you are just tired, it's fine. So maybe to close the discussion, and for me the question is, you see that intensity lies often to you. And the question is, can polarimetry help us to find out the truth? And the question is, what is the role of polarimetry in tomography? Where are the limitations? And maybe, I don't know, maybe we need this high vertical resolution to bring back polarimetry in tomography. So I would like to have maybe your thoughts on this and how you can, because at the moment you use polarimetry only in a very limited way. And why? So where are the limitations of introducing this? Especially if you look on the electrics, then it's the game of polarimetry. So it's not just one more channel, maybe the solution. And why we are not able to explore polarimetry in tomography in his full power. So with this, think when you have your coffee and be back tomorrow. Ah, no, Klaus has something. Ah, okay, so, no, I finished, so someone has to close the session. So, but you can make your announcement afterwards. Yes. Afterwards. So let's finish the session first. Okay, good. Okay. Thank you for allowing us to close the session. I have to say that this is not all tomography. This was only tomography about forest. We have a tomography on ice, on the cryosphere session. So, and now I sat up and...
Thanks a lot for this session. And now it's time for the coffee. I'm sorry for the late too.
Okay, just...
Coffee.
2 quick announcements. First announcement, a reminder to the session chair, a very kind reminder. Please provide your summary of the session, 1-slide summary and recommendations, and hand this to Sabrina so that we have the input for tomorrow. Second announcement, in the coffee break you will find a table from the MAP team. If you have any requirements for the MAP, any use cases, they are very interested in getting some feedback, and this can be very wide. You can just bring your ideas there, say, I don't know, I want to do a neural network based on level 1 biomass, NISA, and JEDI data, you should give me the service, tell them, and they will shape the map that you can do it. If you have more specific requests, it's also possible if you say, I need a GPU, I need the 4-minute model, for example, on the map, tell them, and they will make it possible. So it's your chance to get the map in a way that you can really use it. Thank you.
So we are about to start, and please take a seat.
May I have your attention, please? Can we start now?
So good morning again, and even if the coffee break was short, I hope you enjoyed. And so let's start with the next session. It's a session about campaigns. We have 5 papers, and you will see that there are at least 3 campaigns mentioned, if not 4. And again, all of them, they address forest scenarios. So, and we are happy to keep the discussion going, like in the previous session. And so please, if you have a question, just go ahead. And don't forget also to post your comments on the Padlet, so all the different instruments that you have tried in the past days. And we can start with the first speaker, which is Irene Heinzek from DLR. And she will speak about this very recent Gabonese campaign on the forest of Gabon.
Okay, yeah, thank you very much, Matteo. So welcome to this talk. So I would like to provide you an overview of what we have done just recently. I just had a talk here to somebody just to say or to tell you what is recently. Recently really means that the team came back last week, and that the last flight that we had over these Gabon test sites was really on the 10th of June. So what you see here today are really very, very preliminary results that we have. And I would just like to provide a framework of the campaign, all the things that we have done and the data that will be potentially available. This campaign has been not done just here in the frame of DLR with their airborne system, but in cooperation with NASA, JPL, but also University of Maryland. Mainly, I like to name here Lola Fatoyimbo and Mark Simard, but also Michelle Houghton, Brian Blair, as well as also Ralph Dubaya. And also what is important always on this campaign is if you go in a country, a foreign country, then it's also very important to have the support, the local support, and this has been done by IGEOS, which is the space agency, the Gabonese space agency, and here I'd like to thank very much the head of the space agency, which is Abubakar Mambimba Ninjobui, and the 2 assistants that he has, Larissa and Vianney, which were very helpful for us. And for sure, I need to say that this campaign in general has been supported by ESA. It's an ESA-supported campaign, and mainly responsible here was Tanya Casal. She was also with us there, and Malcolm Davidson. Okay, let us go very shortly through the goals. The goals, in principle, have been to measure changes. We have been already in Gabon in 2015 and 2016. In 2015, we had an air campaign organized and flown by Honora. And in 2016, it was DLR. And now we come back actually after 7 years, and we would like really to see the differences. So which kind of differences we would like to see? So first, we would like to see what is the sensitivity of polarimetry in terms of changes in the intensity, polarimetry, and interferometry, but also to see temporal changes within the campaign, not only within the 7 years, but also within the campaign in terms of the observables that we have, but also about the geophysical parameters that we can retrieve there. The one important point also for ESA was to simulate some ROSE-L level 1 SAR products. So that's also something that we will do. And then we would like to go a little bit further on to see also what is the sensitivity then also in L-band. So main parameter was really P-band, and then going back to L-band. Probably just to come back because here you see on my slides actually two names. So the one name is Gabonex and the other name is AfriSAR 2. So the first campaign in 15 and 16 has been called AfriSAR. And when we came back, we were asking support to the Gabonese people, and they were a little bit complaining about AfriSAR because they were saying, why AfriSAR? You're only flying in Gabon. So therefore, we changed the name to Gabonex, so that's our official name for the Gabonese, and we have the other name, which is kept by ESA, just that you know. So I'm switching a little bit forth and back on these two names. Okay, what are the test sites? So that's actually Gabon that you see, mainly Gabon. And you see, in principle, the rectangles here, the yellow ones. The yellow ones are the ones which are our test sites. And then in the surrounding, this is, in principle, the airspace that we are using on this different area. So Gabon is a whole area here. This is seen by the Google map. And you see, I said, the different test site within. So we were flown actually all the test site, same as also in 2016. However, we have been asked to fly 2 test sites in addition. This has been suggestions by the Gabonese scientists. The one, therefore I'm pointing it out, is here in Mitzig, which is mainly has a main idea to detect illegal logging activities which are ongoing in this forest part, and the other one which is very close to the coast, which is Port Gentil, and here the main idea from them was to try to separate mangrove forest from a flooded forest, so to see really what are the differences in this respect. Okay, what we have done for these, because normally when you fly, it's also good to have a calibrator, and we have a calibration test site, which is called NCOG. NCOG is a site where also AGEOS is positioned. AGEOS, as again said, is a space agency in Gabon, so and they are building, so that's not a corner reflector, what you see here. It has a shape of a corner reflector, but that's really AGEOS, this building of AGEOS, which is a triangle, so that's very nice to see in our FSR L-band Pauli image, and the trihedral itself is actually these response that you can see here. And this trihedral is quite huge, so it's quite an effort to install this trihedral. It has a dimension of 5 meters, so it's really strong in size. We have shipped it beforehand with a ship, so with sea freight, and we needed around 3.5 days to install these corner reflectors with around 3 persons. So you see how extensive this really is. And in addition, as Roman was already saying, it was very hot and humid, and you have no shadows there, so that's really quite a tremendous work to be done. However, this is very close to the Gabonese Space Agency, and this has been our site where we were flying between our measurement flights also to make calibrations. What are the flight configuration that we had? As said, we tried to keep everything the same as in 2016, where we had the main focus on P-band, which means why focus on P-band? Because the baseline for P-band are normally, you have a different sensitivity to height, so they are different as an L-band. However, we had some new components. We were saying, okay, we would like also to have some adapted baselines that are adjusted to L-band. This is what we done. We had the request to simulate Rose L acquisitions, which mean we do also 6-day repeat observations. Then we had some new priority flights also. That you can see here in terms of, we were doing lower priority flights with the 40 and 80 meters, so these are different baselines configurations, and as said, we had 2 new test sites which we included. You see the table here, so everything that is in red is new, so from 2023 in this table for the baselines that you can see, and one baseline here. We had these only in 2016, but we are pretty sure we would not need this, so therefore we haven't done it again. We didn't flow them. And if it's written twice, it means we have flown each test site twice within the 6-day repeat, so 6-day time difference in between, except of these 2 test sites, which we were just had a recommendation from the Gabonese, and we were only flying this one. Probably people recognize that one test site is missing, which is Rabi. So Rabi has been flown also last time in 2016. It's not flown this time because we were not expecting really changes between 2016 and 2023. and therefore we have not collected these data sets. As said, we had cooperation with NASA, and mainly here because of their airborne LiDAR sensor, so which means we were coordinating the flights, and this you see here. We have the coordination of the yellow boxes that are the ESA flights, and then the lines that you see, they're small, tiny lines from Elvis, from the LiDAR, and we were coordinating like this, that we have adjacent flight on the same spot. What we have also coordinated, and I'm not showing it now here, is also flights from TandemX. So we have the same lines also, and we have adjusted the test sites also like these, so that we have the same direction of the flight lines also for TandemX measurements. Probably just shortly to NASA and Elvis campaign. They were this time flying with a new instrument, so they took the instrument from 2016, they had it, but they had also a new version, they call it Elvis C LiDAR and Elvis F LiDAR, as you see here, and the main difference here is a resolution, so the footprint that you have, in 2016 was a 20-meter, and now the new one is a 10-meter footprint LiDAR. So, but in principle, all the rest, so the coverage and the swaths are the same. It's only that you have now here a little bit a different footprint. Yeah, and with this we hope that we see also more differences or better separations in the waveforms in order to have, when we have these different spatial resolutions. So they have also collected the data, so we expect to have, in principle, the data from the acquisition in around 4 to 6 months. So their main flight time was, and you see it here, it was quite adjacent to our one, so they finished a little bit earlier, as we have finished some days before, because they have a jet which is much faster flying and much higher flying, so they had a longer endurance, which means so they could fly more test site at once, so they didn't need so much time to fly over the whole test sites as we have done it actually with the radar system and with the smaller DO. Okay, so that's the preliminary results. They were just sending me this yesterday. These are now the LiDAR flights that you see over the different sites, the one that they really conducted, and you see here the height differences here over the forest, and that's really great. So they collected actually all the test sites very fast, within some days already. And then we had a phone call. We were discussing a little bit how was the weather situation, because LiDAR is very sensitive to cloud cover. And we decided that they, in principle, fly again. And so they have done actually these, therefore it's written there, they flew all the test sites also twice within some days. And yeah, we were looking forward now to see the data sets in order to investigate it a little bit more. So that's now the first preliminary results for the GabonX campaign. You see here for each test site that we've flown, the P-band or L-band, so everything that's on top, because it's so many images, I just selected now one row on P-band, which you see for Monda, a P-band, Port Gentil, P-band, and for Lope in P-band, and then below you see the row in L-band, which is Mabuni, Mitzig, the new test site, and Pongara. And probably just to give a little bit of view, what do we see here? Some of them, you see these are primary forest. If you go for example, for Monda and Mitzig, these are primary and secondary forests with some degradation. So in Monda, degradation ongoing, and said in Mitzig, it's more illegal logging. Then we have the mangrove forest and the flooded forest in Port Gentil and also in Pongara. And then we have, in principle, the mix between tropical forest and savanna areas, which is Lope, and here in Mabuni we have these also again savanna and primary forest estimation that you will be able then in principle to investigate. So we have seen already from Roman, he was showing these slides, so I'm also focusing a little bit to give you a view on what kind of quality do we have? So the first assessment of the data on the example only on Monda, and again only on a small part of Monda, where we have here then the TomoSAR profile that I will show later on. And here I will show the results, the first results from P and also from L-band. So let us go through the coherences. This is always important for us to have a check how the coherences look like for the different baselines. And you see here on top, you see the baseline and the associated capacitors that we have. And it's already very well to see if you just go back, sorry, just to mention it. So here we have very dense forest, and here it's more mixed, so it's not so dense and more, let me say, surfaces uncovered. And this you see also here, in principle, with the change of baseline, you see where the decorrelation is ongoing. It's more on the upper part, which is an indication that we have volume decorrelation. In this case, we see very clearly that we have here a decorrelation in the interferometric coherence, and in below you see the coherence stays quite stable over natural surfaces which are not strong vegetated. So that's already a proof of concept that these data can be used for any kind of volume estimation. This is in P-band. What we have also, and this was amazing this time because the weather was so stable, not only good for the LiDAR, but also good for the baseline flights. And we had a very small deviation of our nominal tracks, which is around 1 meter and even less. And this you see also very well on this point spread function, which you see here. So we have no side lobes, so they're really flying straight over the whole area. So this was a perfect flight tracks that we got. And again, this is one of the first tomograms that you see now in HH polarization over Monda. And again, you see so the surface areas, and then starting slowly to see the volume here, and the separation between the ground and the volume are quite visible. So we were not going into detail, just to have a sanity check that tomograms can be developed. And Roman was already showing also, he was taking some of this data set already to investigate them. So we were also checking very fastly what is the difference between AFRISAR-1 and GARBON-X. And you see the only thing that you really see as a difference here is a zero line. So we were not still really calibrating them. So as said, is the first preliminary results of both for the different polarizations, but they look quite similar. So there are differences, and we will investigate the differences. But just to say, the data seems to be very well and also very well calibrated. Let us go to L-band. We had also L-band data. You see, again, the baseline, and you see strong decorrelation ongoing here in L-band. So therefore, we changed a little bit the baselines. So we checked also to have horizontal baselines. So therefore, we have now 5 and 10 meter, which is less decorrelated, but it's already a sign that L-band is stronger decorrelating in this tropical forest part. What we have also done, we have the 3-day difference coherences. This is P-band 3-day difference, and you see very strong and high capped coherences, whereas on L-band you see the decorrelation is already going very, very strongly ongoing. This is for the zero baseline, so really strong differences between L and P-band, just that you get a view of a tropical forest, how it could look like. And this is now it's not a 3-day, but it's 3 hours, 3.5 hour difference. And you see it's not so much difference if I switch back now to the 3-day difference. You see the coherence is high in P and L band, but it's not so much different if you just do it after 3 hours. It's a little bit higher, but really not so much high. Okay, what we have also done, just as a sanity check, we just look on our profile. So we were using, in principle, the coherence, we used the capacitor variation, and we were checking in principle here now the coherence, the sync function that you see here, and we had a very nice plot in AFRISAR 2016, and we just checked how does it look like now for GARBON-X, and also here we see we have a very, very good spread of these. It's probably a stronger separation, and let me say the variation is stronger. However, it looks in principle quite well. Okay, we have also derived already the first forest height maps. So this is also what we have done within this 1 week now. What you see here in the first is the Elvis flight from 2016, because we didn't have now the new ones. This is AFRISAR-1, this is GARBON-X from time 0, and then 3 days later. So that's the maps. They look very similar, so also this means we have quite good results. However, there are small differences, but this is also what we expect after 7 years of acquisitions. Okay, that's already my last slide. I would like to thank very much the GARBON-X, let me say, team that were working very hardly in this domain. So we have been since May, from May until last week there. We're doing a lot of campaigns. We had also nice days. You have seen we had a very nice excursion also to the beach, but we had also very, very long days sitting only in a climatized room, but still very hot outside, and we're enjoying the processing of the data. Okay, thank you very much, and I hope you will use this data. So probably just one thing I just mentioned: the data will be available from Elvis in 3 to 6 months, and the data of the airborne campaign, in this case from the radar campaign, will be around available 6 to 8 months. So this is something that we will expect and will be then available to the community. Okay, yeah, thank you very much for your attention, and if you have questions, just ask.
Thank you. Stefano, with a question.
Thank you, Irina. Just a question. What kind of interferometric calibration will characterize the data received by everyone? I mean, will everyone be able to form a tomogram without dealing with phase calibration and so on? Okay.
Yeah, so this will be all well-calibrated data. We have done this already also for the AFRISA-1 campaign. And these are mainly also co-registered data too. So this is also what we do normally, especially for the TomoSAR stacks. So this will be available, yes. Mm-hmm.
Okay. And also geocoding information, because
yes, yeah,
okay.
We have always a grid behind so that you can directly do geocoding. The lines that you saw here, we have already geocoded it just for comparison. So some of them just to check this too. Yeah.
Thank you.
Mm-hmm.
Other questions? So one back.
Thanks, Irina, for the nice presentation. I have a question about the second to the last slide. You have the 3-day temporal baseline P-band. No, the one after, sorry. Yeah, so did you try any correction for the P-band temporal decorrelation in the height estimation?
Yeah, as said, so these are really preliminary data, and we just came back, let me say. So this is just the height that we derived directly on the data set acquired on time 0 and on time 3. We have not done any kind of correction in case of temporal decorrelation in the moment.
Yeah,
no.
I saw the P-band coherence is already pretty high, so.
Yeah.
Thanks, yeah.
So I mean, it was just coming out like this and looks really good, right? So it seems in P-band we do not have really such a strong effects.
Other questions?
I have just a very quick question about what is your perspective for the future campaign, because we have a campaign in South America, in Europe, in Africa. What about in ASEAN?
Yeah, from a tropical area, we are going now to the ice area, I have to say. So we will probably, our next campaign will be in Iceland, which is probably at the end, so middle of this year in September. It's still not clear because we had some issue with the aircraft, but potentially we'll go to Iceland and we'll map some glaciers there. Mm-hmm. So we are doing a lot of different campaigns for different application areas. It's not only tropical forest, but tropical forest is one of our, let me say, nice thing that we like to do too.
Thank you a lot, Irina. So the next talk will be given by Stefano Tabanini. He will be talking about continuously with the TomoSense campaign about the mono and bistatic scattering from temperate forest. Please go ahead.
Thank you very much, Dean. Okay, so welcome again. And I'm giving this talk on TomoSense, which is a bistatic campaign that was concluded last year. This is the second talk about TomoSense. We have 2 more in this session, so let's say that I am happy to say that the work is finished and it looks good. So what is TomoSense? TomoSense is a NISA campaign to support research and development of bistatic and tomographic SAR. and it is especially tailored for forest. And of course, we address systems like biomass, because we have a P-band, but also bistatic interferometers like could have been SACOM CS, or like a companion or to Roselle, could be like. The campaign took place in 2021 at the Kermeter site, so this is the area within the Eiffel Park in northwest Germany. We flew with 2 aircraft to get bistatic data. Before you ask, it's a small angle bistatic experiment because we wanted to have coherence between the 2 flights. We have bistatic data at L and C band, and we also have monostatic data at P band. We have in situ collection of forest parameter at about 80 plots. The forest parameters are forest height, forest the diameter at breast height, and we know the tree species and if the tree was live or dead. We have collection of terrestrial laser scanning data at a scale of 1 hectare at 10 plots, and we also installed 2 5-meter trihedral reflectors for P-band calibration. Here is the flight plan. Basically, this is a space for maneuvers, and we went back and forth this way for about 20 or more times to get tomographic acquisitions from 2 opposite headings. Here is the flight plan for P-band. So basically, we have 10 passes nominally at the same height, and then we lower the flight height progressively to get tomographic baselines. This is for L-band. For L-band, we had the 2 aircraft, so the master always flies the same trajectory, and the slave follows at 32 meters lower, and then it progressively lowers its altitude again to get baseline diversity. The plan along track separation should be around 20 meters. We will see that this was not possible. And this is for C-band. Basically, the flight plan for C-band is a replica of the flight plan for L-band with just slightly different numbers. Now, the campaign execution was not simple, and we had a lot of problems. We had huge delay in getting permission to transmit from the German authority. We had the hardware glitch. We had bad weather, and by bad weather I mean that the storm capsized one of the 2 corners. I'm talking about a 5-meter corner, so it was a big storm. You might remember COVID-19, which also was a problem. And finally, we had the flood in northwest Germany. So it was a difficult campaign. At the end, we did it. We had one more glitch in 2020. Basically, the bistatic flights were intended to get coherent flights. So let's say the plan formation was like this, where the master and the slave would stay on the same line of sight, nominally. But there was a misunderstanding, and the pilot flew this other way, so with much larger baselines. And we took a look, and we decided that this is tolerable at L-band, because we can still use them, but it was not acceptable at C-band, and so we had to refly C-band in 21. Interferometric calibration. We had to work a lot on this because so for each data set we have even thousands of interferogram. Consider for L-band, for example, we have 30 monostatic passes, 30 bistatic passes, 4 polarizations, and we want to process everything together. So if you consider all the possible pairs, this amounts to thousands of interferogram. Basically, what we did was to do multi-squint interferometry and also to apply a bistatic version of the phase center double localization algorithm. So we estimated the trajectory the best we could. We defocused and refocused with the right trajectory. There is a talk dedicated to this, so I will not dwell in details. This is the result. This is a P-band vertical section, and in absolute coordinates. So here we see the profile of the terrain. I forgot to mention that this is a hilly topography, and this is the transect that we are looking at. And up here, you see the forest as it is imaged at P-band. If we overlay the LiDAR DTM, we see that the match is pretty good. And now we can jump to a ground-steered P-band vertical section, in this case HH, HV, and VV. We can see the forest profile very well now. And again, if we overlay now the LiDAR canopy height, we still see that the match is very good. This is for L-band. We have an HH tomograms from repeat pass monostatic data. So we see this is the terrain here. This is a ground steer tomogram. So it was resampled so that the ground is always at 0 meters. And the forest, and this is a vertical section from repeat pass bistatic data. It is nice to see that as physics teaches, the ground scattering gets weaker. And this is an interesting product. I told you that for L-band we have this problem that the baselines are much larger than planned. So we could not form tomography simply by beamforming, but we had to, let's say, use two-layer models, which in this case it works pretty well. And this is an example of a vertical section using just simultaneous bistatic interferograms. So this is an example of what we plan to do with correlation tomography with L-band bistatic system like the Roselle Companion or similar. This is the same with the black line indicating the LiDAR forest height. So, and some comments that are pretty much the same I just told, so I can skip this one. An example of forest height retrieval using only simultaneous L-band bistatic interferogram. So we just use 30 passes where the interferograms are, we have one interferogram per pass, basically. This is forest height as estimated by tomography. Basically, we just try to track the upper envelope of the tomogram. And this is the LiDAR forest height. So you see that it works. So it is, everything is as expected, and we have a more than decent fit with the LiDAR. This is an example of a phenomenological analysis. It is the ground-to-volume ratio. In this case, we have in monostatic repeat pass data HH, BV, and HV. And what is fun is that if we go to bistatic repeat pass data, you see that the ground is much weaker. So this is exactly as expected. And in this case, we could quantify the losses about 4 dB. Same product, but now using just simultaneous L-band pairs. Again, I repeat that this was the result of a two-layer model assumption, which more or less worked. And in this case, the losses, so the ground-to-volume ratio is in between what we get with repeat pass bistatic and repeat pass monostatic. This also tells that temporal decorrelation is not critical at L-band, so the repeat pass campaign works fine. And now we have, okay, this is a slide that I like a lot. It's very qualitative, but basically we try to compare all our results to forest biomass. I discussed this yesterday. We had, during the study, we had 2 different biomass maps. This was the first one with that was derived from LiDAR height with allometry derived from the literature. But then we had another biomass map where allometry was derived by TLS data. So the second one is supposedly much better. And you see there are areas where the allometry from TLS makes a big difference, like here. And you can see the smile on my face since the radar saw this difference. We try to evaluate the volume to ground ratio at L-band, and you see that whatever it is, we could track this difference, and so we could sort of use the radar to say, okay, there is a reason why I like this other biomass map better. Then some comparison between the forest profile by TLS and tomography. In this case, we used the bistatic L-band tomography because this is the one that we like better. It's also the newest one, so we like to use it. The story is that whenever we have a single peak, the radar and the TLS are pretty much together. They are pretty much consistent with one another. There are examples here where the TLS says that there is a sort of a bimodal distribution and tomography doesn't. So in this case, we have just a single layer. Well, okay, for some reason, of course, related to density as perceived at this frequency. Now we change frequency band. We go from P and L to C band. And we play the same game, so C band vertical section from repeat pass monostatic data, C band vertical section from repeat pass bistatic data, and C band vertical section from simultaneous interferograms. So if we use repeat pass data, we just see the ground. So the forest has completely decorrelated. It took, I think, about maybe 1 hour or a couple of hours to get all the passes, and this time at C-band has killed the forest completely. But it's nice to see that it didn't kill the ground completely. So despite this ground was covered by the correlating canopy, okay, we could detect it. And so this also means that in the C-band repeat pass interferogram, if you can detect a signal, this is most likely the ground below the forest. Not so if we use just the simultaneous interferograms. In this case, we can see some of the forest canopies, so this is good. But the problem is that I call this simultaneous interferogram, but they are not. And why? Because nominally, the two aircraft had to stay at the distance of some 20 meters along track. This was the plan, but the pilots had to fly in a windy day, and frankly, nobody wanted to risk their lives. And so they felt more confident flying at a distance of 40 to 100 meters, and this is what it is. So not quite as planned, but we took the opportunity to study the short time temporal decorrelation at C-band. And since we have, thank you, many passes, we could play this funny game. Basically, here we have the coherence between in what we call the simultaneous interferogram, so mono and bistatic, in the position where the spatial baseline is 0. So we have this data set where we can study the temporal coherence at 0 baseline. And as expected, I think this confirms all Marco's model. For example, we see a very good trend with forest height. So basically, the temporal decorrelation goes down with forest height, and it also goes down with forest biomass. What else? So we tried also to make some more sophisticated analysis. So we selected a few regions of interest where we try. So since we have, for some regions, many passes at 0 baselines, and at a different temporal lag between the mono and the bistatic. Then we tried to see if we could detect some trend, but the answer was no. Yes, there is probably a moderate decreasing trend, but it is really not so clear. And discussion. P-band and L-band are great for forestry. We can detect the ground, we can detect the canopy, we can study the details of the forest structure, and bistatic tomography is interesting. It tells you something more, and I think it is an interesting product. Correlation tomography was demonstrated, despite we had this problem of the very big baselines. At C-band, okay, temporal decorrelation is a killer. I would say that I would recommend a C-band bistatic mission for forest as long as the temporal distance is no more than a few tenths of milliseconds, or we are dead. Just let me tell you the final announcement. Oh, yeah, final announcement. The TomoSense dataset is freely available. It contains all the radar data. The radar data are calibrated. By calibrated, I mean that if you see that the phase is 0 in an interferogram, this is the ground. So it's a product that you can use to do whatever analysis you like without having to struggle with radar calibration. You also have HB maps, TLS, all the LiDAR maps, in situ data. You have the radar complex data plus tomographic cubes that we produced. So you don't even have to implement tomography. You can just start with the tomographic cubes and do your own analysis. The data are shared by ESA, but it's much faster if you send me an email, and I will reply with a Dropbox link where you can find everything. Thank you very much.
Thank you very much, Stefano. Very interesting. Any questions for him?
Thank you for a nice presentation. Can you hear me?
Can you speak closer to the mic?
Yeah. I was wondering what's the minimum baseline can be achieved for a bistatic configuration?
The minimum for L-band bistatic. I don't remember, but they're very large. We could survive because they are sparse. So basically, we do not have ambiguities, but we have side lobes. And so for this reason, with a parametric inversion, we could form an interferogram. But if you try to do the usual way, then it's not going to work.
Yeah, but you were mentioning that for safety reasons, there is like 20 meters or something?
A long track, yeah.
A long track. For which across-track separation it would correspond, like the minimum one? For across-track interferometry?
The across-track baselines?
Yeah.
I don't remember. Well, let's say that I don't remember the exact figures. Let's say that the effect is that if you want to do tomography from simultaneous interferogram, then you need the parametric model. Wait a sec. Oh, it takes forever with this thing. Okay, so more or less, this is the across-track separation. So for L-band, just imagine that the red plane is to the other side. So what is that? Some 30 meters, more or less.
Okay, yeah, but that means that for C-band you would have a lot of ambiguities if you use...
No. C-band was reflown.
Okay.
So at C-band, we even have a 0 baseline.
Okay. And then another question, if you compare, could compare coherences extracted from bistatic and monostatic, let's say use the same baseline for P-bands, the same separation and compare the coherences from monostatic and bistatic?
We did not investigate coherence. We went for tomography straight ahead. My take is that the biggest difference is that the gram scattering is weaker in bistatic data. So probably this is something that you see.
Okay, thank you.
Thanks, Stefano. Very nice presentation. You had one slide for the zero baseline temporal decorrelation at C-band.
Yes.
And then I saw on your on the horizontal it says delay, and I was just you going really fast through it, so I didn't know exactly what the delay was.
The delay? So let's say we had the maximum along track separation of 100 meters.
Exactly. Okay. That's what I thought.
So this would be a few hundredths of a millisecond, more or less. Okay. Let's say that the temporal delay was, maybe I wrote it somewhere.
Yeah, it's one of your last slides.
On the let's say in between 500 milliseconds and 800 milliseconds, more or less.
Okay, thanks.
Yeah, thanks, Stefano. Could you comment about the effect of topography when, especially when slopes are, let's say, challenging the slant run geometry, and especially the difference between the monostatic and bistatic case, where sometimes yes, it was very useful to have a ground contribution when when slopes are really opposite to the radar.
Right, indeed. This is a hilly topography, so the terrain slope matters. Let's say that we didn't investigate the variation of the bistatic response as a function of topography. This would be a very nice analysis. So you are welcome to download this data set. We didn't have much of a problem for forest height, so we could get forest height more or less independently on the topographic slope, and the reason is that we have a lot of baselines, so more or less we always have the optimal configuration for any slope. There was an impact on biomass retrieval, of course, and this was discussed yesterday, and the Chalmers people recognized that if we limit the topographic slope, then biomass retrieval improves.
Thanks for your nice overview. So in one of your last slides, you showed these relationships between coherence and biomass. Was it for P-band, L-band, and what was the spatial scale of these analysis?
Between coherence and, okay, so you had to be here yesterday, since we had a talk about it. If I remember, the biomass retrieval exercise was done by selecting plots at the scale of half an hectare. Okay. So all our results concerning biomass were done this way. The results were good, but I have to point out that the biomass range is not huge here. We have quite a large biomass, but not so much lower biomass.
And the coherence analysis, was it for L-band, P-band, or?
We didn't do any coherence analysis, actually. We just went for tomography.
But you showed one graphic, so it's the second last slide or something like this?
Where was that? Not this one.
No, not this one. Later, it's later again.
Maybe, no.
It's at the end.
No, I
of
don't
the
remember any coherence here.
No, please go later again.
Later, okay. Sorry, no, okay. There was an analysis at the C-band.
At the C-band,
that was
okay.
Temporal decorrelation versus forest biomass. Not to imply that I want to estimate forest biomass based on temporal decorrelation, but...
This was the graphic.
Yeah, no, I got it. But it's nice to see that, so the interpretation is the taller the tree, the more it sways, and so we have more coherence loss. But of course, this is just a phenomenological analysis. I don't want to say it is any retrieval technique.
So, thank you, Stefano.
Thank you.
And we move to the next. So, next presentation, we stay on the same campaign. So, and the title is The Potential of SAR Tomography and Phase Histograms Techniques for Estimating Forest Structure, an assessment based on TomoSense data, and the presenter is Changyun Wu.
Thanks for your introduction. Good morning, everyone. My name is Wu Changjun, PhD student from Politecnico Milano and Wuhan University. My work is supported by the Stefano Tappini and Mauro Marino di Alastra, who come from Politecnico Milano, also collaborated with Yang Hai and Li Yang, who come from the National Space Science Center, and Zhang Lu and Liao Mingsheng, who come from Wuhan University. My presentation is a comparison between SAR tomography and the phase histogram techniques for remote sensing of forest areas at air bounds. So firstly, firstly, let's see the models we compared in the experiment. One of the model is SAR tomography, namely TOMSAR. As we all know, with the aid of multi-baselines and two assumptions, TOMSAR can form a new aperture along cross-range direction after some focusing processes, and by setting the reference position, we can explain the SLC data expanded as a first-order expression as shown in the first equation. The solving problem of the complex reflectivity becomes a Fourier transform pair. So inspired by the DOI estimation, many super resolution algorithms have been proposed in recent years. In our experiment, we take Capon beformer and the basic equation of the Capon as shown in the last algorithm. So another algorithm we compared in our experiment, we can call it phase histogram technique for short, PH technique. And it's a new technique, and more details can be found in the reference. We conclude the phase histogram technique in our experiment into 3 steps. Step 1, compute the interferogram pixel by single look process. Step 2, select a special window, count how many pixels fall in the specific head beam we set, and place the sum of these pixels magnitude into the specific head beam. So the window size is about 50 meters times 50 meters, corresponding to 5 pixels in the range direction and 31 pixels in the azimuth direction. The window size is the same with estimation of the coherence matrix in the Capon algorithm. So the PH technique provides a new perspective that we can use the sum of the neighbor pixels with a special window to approximate the first structure. Next, the real data experiment uses airborne data from TomoSense. TomoSense experiment was organized by the ESA to support the scientific research in the field of the remote sensing of forest areas, with the emphasis on the innovative application of TOMSAR. All activities was successfully closed 2021, and finally, in total of 1,800 passes of fully polarized SAR data in PL and C band were obtained, including 2 offset flight heading, northwest and southeast. And the test site is located in the current area at the Eifel National Park in Germany, as shown in the upper left picture. More detailed information can be found in the reference. So in our experiment, monostatic airborne data were used to make the compensations and verifications. Okay, next we see the result. The left picture is LiDAR-derived first height of the northwest flight heading in SAR coordinate. The black solid line represents the selected azimuth slice for testing the performances of both two techniques. Please keep in mind that all the data sets were well calibrated and ground steered, so that the ground reference phase of any interferogram is automatically set to 0 meters. So we also make the normalization of all backscatter profiles ranging from 0 to 1. Move on the result, as shown in the right panel, we can see that the single interferogram result is not good, even complete failure, because the case of the single baseline is drastically changeable due to the unstable orbit and changeable trajectory. So there are some problems in the single interferogram pH. With single observation, a drastically changeable trajectory and unexpected vertical wave number KZ, the single interferogram pH can't work well. So thanks to the multiple available baselines of Thomsons, we can, according to the INSAR theory, we can select random one as the reference image and compile all the secondary images to perform the SAR interferometry. Finally, in total of 435 pair of interferograms can be formed with the help of the 30 passes. So it is a very huge, rich data set and provides a lot of observations. We call too many interferograms first super interferogram. So after aborting the super interferogram, it is possible to select a proper one that can fit the pre-selected head of ambiguity, for example, 60 meters, to perform the pH pixel by pixel. So the super interferogram result, as shown in the right panel, there is an exciting point that the selected KZ corresponding to the selected azimuth slice approximate constant value. This is the case that fits the space mission with the stable orbit and approximately the same slight range distance. So compared with the single interferogram result, our strategy work better. So next we compare the results between the super interferogram pH and the Thomson. We choose 3 pre-selected head of ambiguity, and the results are shown in the right pictures. All the choices of the head of ambiguity can get the like tomography profiles. We think that when we fix the head of ambiguity is close to 6 meters, more or less is about 2 times than the tallest tree in our test site. The result is best. Please see the head of ambiguity is about 45 meters. We can see that the profile will end up at the head level about 25 meters. So if we want to make the pH technique can work effectively everywhere, the choice of the head ambiguity is the key point. Obviously, all the backscatter profile of the different head ambiguity looks noisier and cluttered than the tomogram. So we can get the preliminary conclusion that the pH technique can only loosely approximate the vertical structure produced by the Thomson, and the pre-selected head ambiguity must fit the proper range. For example, it is roughly twice the first head. And another factor we consider in our experiment is the influence of the multi-look factors of the INSAR phase. We set the 3 different multi-look factors. One is 1 look in range direction and 10 looks in azimuth direction. Another 2 cases is about 1 look and 5 looks in range direction and both 20 looks in azimuth direction. We can see that increasing the multi-look factor leads to a more concentrated energy distribution in the backscatter profile. It reveals that the average process in interferogram will cancel out some scatterers contribution within a resolution cell. And next, we want to say with the degraded resolution SLC, what are the performance of both two techniques? We use defocusing and refocusing techniques to get the degraded resolution SLC data, and all the data set refocused on the same spatial grid. And we can see with the fine resolution SLC that both TOMSA and the pH technique can get the good performance. For example, the resolution is 3 meters in range and 0.5 meters in azimuth direction. We can the first column of the image. We can see the both of two techniques can get the correct first structure. However, when we use the coarse resolution, for example, 12 meters in range and azimuth is 8 meters, the TOMSA can still get the correct first structure, even though the angular spread of the profile become wider and the background of the profile become cluttered. But the pH result is random and incorrect. So this is not surprising since the TOMSA use large data volume than the pH technique. Moreover, the physical model connecting to the face and head is structurally only valid for the isolated target with a resolution cell. So we can use the simple physical model to explain our result. That we, as the pictures show, that we can express the SLC that in two cases. One case consists of one dominant scatter, and another includes two dominant scatters. We simulated a vector including 100 elements, and two cases interferogram. We draw the interferograms into the same polar coordinate. We can see as case one with dominant scatters, the pH technique can get the right position of the scatters because the interface is equal to interferometric wave number kz times the scatter's height, as shown in the bottom of the equation here. And with two dominant scatters, we can see that the interface is random. So yes, and next. Next, finally, we estimate the first height use the both two techniques, and from the scatter plot and the RMS distribution, we can see TOMSA can provide stable first height maps, and the pH technique can also provide a fair good estimate of first height. Compared with the later data, the average RMSE is about 2.6 meters in TOMSA and 4.7 meters in pH technique, respectively. And we can get the same conclusion as for another flat heading data. So my conclusion is we make the experimental comparison between the TOMSA and the pH technique based on the Thomson's error bound data. And the TOMSA can get the more stable and more better first height than the pH technique. And the degraded performance of the pH technique indicated that the pH technique is best fit the scenarios, whereas each subpixel is characterized by the presence of dominant scatters. So as a general conclusion, the result with this paper it overstates the pH is a valuable option in the context of the high resolution mutation, such as tandem X mutations. That's all. Thank you for your attention.
Thank you. Questions, comments, feedbacks? So there is one here.
Thank you for a nice presentation. I was wondering if you also tried to optimize the polarization which you use when you apply the phase histogram approach.
The polarimetric information?
Sorry, can you say it again?
So
slowly
first of all, which polarization? Maybe I missed a bit, but which polarization did you investigate?
Yes, I use the HV polarization because the HV is sensitive to the volume scattering. So I use the air-bound, monostatic air-bound HV polarization dataset.
HV?
Yes,
okay.
HV.
And if you will investigate the performance dependency on the polarization, or if you would plan to optimize the polarization so that it corresponds only to the volume reflection. So you know that I guess that when you apply phase histogram, your phase center is affected both by ground and volume reflection. And have you thought of the way to cancel the ground so that your phase for a particular polarization would correspond only to the volume?
Thank you for translation.
That's a complex problem for me. So
maybe Stefano can.
Maybe in the future I will consider these factors.
I can make a comment. No, we didn't try it. Maybe we should do it. So it's a nice suggestion.
Okay, I understand. Okay, no problem. Thank you.
Okay, Kostas.
So I didn't understand exactly because at L-band you penetrate in the forest. L-band you penetrate significant in the forest. So your phase center is somewhere between the top and the bottom so of the vegetation. But your validation result, you saw that you overestimate. So I would expect that if you, with this technique, you will underestimate forest height. But if you see the comparison with the tomographic height, you overestimate. How do you interpret the overestimation?
I'm sorry, I'm not hear clearly of your questions, and yeah, maybe step. Okay.
Okay, so what you say is true, but as long as you average a little bit, so you get the phase center that is in between the top and the bottom, as long as you average spatially a little bit. In this case, Chunjun tried with different multi-looking factors. Of course, if we average a lot, then we default to the phase center, and it is exactly as you say. But we wanted to stay at the final resolution just to see if we had the instantaneous variations. But the problem is that for L-band, at this resolution in this forest, the dominant scatter model is not exactly true. So we always have interference between different elements, and this makes the phase a bit random. And it also goes up.
Okay, Marco, you have?
Yeah, I was going to add basically what he said. So this is a single scatter approximation. So, and depends on the clutter to noise, or sorry, the signal to clutter ratio between the strength of the single scatter and the rest of the scattering within the resolution cell. And so I think the results maybe can improve by multi-looking also along the vertical directions. There's several, did you do that or no? And also looking at the results between tomosar and phase histograms, did you use the exact multi-looking factor? It seems like it was smoother, the tomosar results. And how did you multi-look? Did you multi-look the data? How did you multi-look the phase histograms?
I use 5 pixels along the azimuth and height direction. 5 cycle disc filters.
So that the multi-looking factor when you compare tomosar and phase histograms, in the case of phase histogram, was basically the box within which you calculated the histogram, or did you do an averaging?
When we form the phase histogram, we can select the special window.
Right. Okay.
It's about 5 pixels in range and 31 pixels in azimuth. When we get the profiles, and after we get that, we also use the 5 pixels disc filters to filter the backscatter profile.
Okay.
So that's 2 things.
Okay. All right. Thank you. And of course, the bandwidth and the radiometric resolution are also important.
Okay.
Yeah, radiometric resolution. Yeah.
Okay. Thank you, Johanju. Okay. Thank you.
So.
I don't know the name. So the next speaker, we invite you to. John Hai, he will talking about tomographic calibration and processing for repeat pass biostatic airborne SAR. So case study on the tomosynth L-band data. So go ahead.
Hello, good morning, everyone. I'm Yang Han. This presentation is about to calibrate and start tomography on new ESA tomosynth L-band data. This work was done when I was pursuing my PhD in Wuhan University and Polytechnic di Milano, supervised by Minshen Liao and Stefano Tappedini. And I would also acknowledgement the substantial helps and contributions from Mauro Merotti di Alessandro and the support from Yang Lei and Lu Zhang from Chinese Academy of Science and Wuhan University. Okay, this is the outline of my presentation. Okay, a brief introduction to this tomosynth campaign. Stefano has speak a lot for it. So this presentation is focused on the L-band monostatic and biostatic SAR data. And for more details, you can go to the reference below. Okay, the acquisition geometry, the tomographic imaging is enabled by the repeat pass configuration. We refer to the platform which transmitting and receiving signals simultaneous on one platform as the primary platform, and then especially for the L-band data, so for each pass we have 2 platforms to form the one monostatic and one biostatic data. We refer to the platform only receiving the radar signals as the secondary platform. So there a certain spatial separation between is employed so as to ensure the interferometric performance and the safety of pilots. And as in all tomographic acquisitions, without any composition, a direct SAR tomography on the pre-precise data would return a bad, not optimal performance. So let's give a basic background of the challenges. So before proceeding, so we have the SLCs pre-processed by metasensing. So these SLC are generated by projecting onto a reference topography using 2D time domain back projection. And then it means that all the SLC are focused and correlated from a purely geometric perspective. Unfortunately, no dedicated communication link was deployed between the primary and the secondary the platform. So unwanted phase disturbances and the geometric artifacts are mainly attributed to the uncertainties in provided navigational data and the potential presence of the cloak drift arrow. I would also like to point out even inaccurate topography information might play a role in a really high resolution application, but it's not a major problem here because we use LiDAR DTM. Okay, let's go deeper, further in detail about the challenges. So the residue position arrows from dual platforms introduce a lot of unwanted artifacts. So for example, the varying position arrows along the flight direction would cause some locally spacing varying imaging shifts and give rise to the fast varying phase disturbances. And furthermore, the kind of the position arrow in this kind of along baseline direction would give the rise to some tomographic issues. And also we might consider the potential presence of the cloak drift arrow. Given the performance of the current oscillator, we can maybe safely assume the cloak drift arrow manifests as a very function of the flying time. So it would cause the phase modulation along flight direction and some azimuth image shifts in SLCs. So we would say that given the performance of the navigational system and oscillators, so only sub-pixel image shifts and the phase residues arise. So I would say it could be safe, the proper 2D focusing could be achieved just using the raw data as far as the amplitude information is concerned. But the interferometric and the tomographic performance are not guaranteed. So we think the INSAR is relevant to SAMS and invert these arrows because it is sensitive to correlation arrows and demanding accurate phase information. So following content is going to show some examples to infer the presence of these arrows and INSAR-based calibration. Okay, so we have 2 flights of data. So for each flight, we can form the interferogram. So as Stefano said, because we have to safeguard the safety of the payload, so the baseline between the single primary and the secondary platform is a bit large, so some decorrelation is expected. But we can see some partially coherence. But for another flight, we saw totally decorrelation, so something happened. And we checked the repeat path, which means the INSAR from 2 different flights for the monostatic image. It looks good. It is highly coherent despite some local coherence flexion, but I would say it's minor due to some residue time varying baseline errors. So we can assume that the flight condition at that time is more or less not bad. And when we go to the biostatic repeat path INSAR for biostatic data, we saw a totally decorrelation and faster phase modulation along flight direction. So we said, besides the confirmed presence of the baseline arrows, maybe the cloak drift arrow is suspected to be involved. And this slide is going to show that the biostatic data compared with the monostatic data is subject to the coupled trajectory errors from two platforms. Okay, so we develop a cascaded calibration approach to addressing above the challenges. So first, we use the single-pass multi-screened INSAR for each monostatic and biostatic INSAR pair. The objective is to capture the potential clock drift-like turn in each biostatic image. But I would say that maybe the long-tracked baseline error is involved, but it performs more or less like the potential clock drift. So maybe we can just calibrate it together. And then we inverse the time varying baseline error, especially for the cross-tracked errors using different signal models. And then we defocus and refocus each biostatic images with clock drift-like phase composition terms and update the trajectories for each biostatic image. And then because INSAR always has to assume a reference trajectory, so for each trajectory, there are also some errors involved. So we develop multi-baseline and multi-screened INSAR for all the monostatic and the biostatic data set. So the algorithm is to inverse the n-1 passes of time varying trajectory errors for both platforms out of all the coherent INSAR pairs. The objective is to achieve better co-registration of whole tomographic data set in presence of the larger spatial and the temporal separations for INSAR pairs. And then we defocus and refocus all the mono and biostatic images using corrected trajectories. And the final one, the biostatic version of the phase center double localization. The objective is to determine the position errors along the baseline using all the coherent INSAR pairs. And we also want to guarantee the consistent phase centers for both monostatic and biostatic image modes. Finally, we just using the 3D time domain back projection by defocusing and the initially process the mono and biostatic ALCLC and directly project to 2D, 3D space with the correction terms. Okay, let's see some improvement we achieved during the calibration. As said before, so the original repeat pass for one pair is totally lost, but after first one calibration, we can see a significant improvement, but with some residual motion errors remain. And after two steps calibration, so we get a nice interferogram. And then we do some statistics about how coherence improvement we achieved. So before the calibration, so most points are lowly decorrelated below 0.25, and after calibration, mostly above the 0.78. And we go further to check the tomographic performance during calibration. It is so before calibration we cannot see useful information, I would say, but after two calibration it is surprised to see that the tomogram shows some significant improvement because the first two calibration steps are not intended for the tomographic calibrations, so the performance is not guaranteed. So after three calibration we can see very nice tomograms and with certain consistent. And further, we comparing our tomography section along several azimuth direction respect to the LiDAR measurement. So we mainly focus on the biostatic data. The LiDAR DSM is plotted in white lines and the LiDAR DTM is plotted in black lines. So they show very good agreement. And finally, we also want to make use of synergy of the monostatic and biostatic image. So we showed the three kinds of mode of the this kind of image, and finally we enable a joint image mode with higher vertical resolution, which in turn validates our calibration approach. Finally, conclusion. TomoSense campaign provides a nice and rich remote sensing data to feature in a temperate forest site. Particularly, the LBM biostatic data could motivate a serious advanced technology and scientific application. But in any case, I would say a fundamental requirement is the accurate measurement of the sensor to target distance within the synthetic aperture along flight and or baseline direction. So we developed the cascade calibration with following 3 steps to correct different kind of resources independently. So we achieve a nice tomogram with high quality, I would say, and our calibration enable a joint image mode with higher vertical resolution. And thank you for attention. I would express my special thanks to ISA for organizing this campaign and the meta sensing for acquiring this data. Thank you.
Thank you a lot for being time allocated. Thank you a lot. So, questions? Questions? No? Yeah.
Thank you for a nice presentation. I was wondering, you said that you use coherence to compensate for clock drift. Does it mean that once you use the coherence to compensate for the clock drift, you lose the information from the coherence? So, do you understand?
Yes, I would say we use the INSA phase in multi-screen, yes, to retrieve the clock drift or along track baseline errors. The performance, the accuracy of the inversion might subject to the, I would say, subject to the coherence, because you see the total coherence is lost. But I would say we can at firstly retrieve a kind of a coarse estimate or initial guess of this kind of error, and then we correct it some coherence shows, and we can then refine our estimates using the following information. That's our strategy.
But for each bistatic pass, the clock drift is the same. So once you estimated it for once, you cannot apply the correction for the next acquisition, or you have to correct it every time?
No. I would say that the clock drift, the error is also drifting with respect to flying time, because there is some random turn involved. And currently, we just leave the correction of the clock drift error in first step, but we think based on our experiments, our correction works and contribute a nice improvement. Maybe in the future we can assess the accuracy of our inversion carefully.
Thank you.
Thank you.
Thank you. So maybe I have questions.
Okay.
Can you explain me about the difference between the monostatic and bistatic with respect to the phase calibration requirement? I mean, in the method you say you improve from the monostatic to bistatic. Is there any improvement exactly for the phase center double localization difference?
Yeah. Yes, the big difference between these two image modes, that the monostatic image is only affected by the how to say, the trajectory error of the primary platform, but the biostatic image is subjected to the trajectory or errors of two platforms. So right now, because of the cross coherence between the monostatic and biostatic image in different passes are very bad, so we drop it. So at first, we fix the trajectory errors of the monostatic images, just like the primary platform, and then we use this information to help us to fix the trajectory or errors of another platforms. That's our strategy.
Okay, thank you.
Thank you.
So, last presentation of the session and of the morning, Ludovic Villard, 5th anniversary of the TROPISCAT-2 experiment, Insight for the Biomass Mission and Beyond.
Yes, thank you, Matteo. So yes, I'm very pleased to present this work about 5 years of TROPISCAT data, especially at P-band, which is hopefully the amount of data we'll have after regarding biomass mission time life. So I would like also to thank all my co-authors, so mainly at CSBio, but also at AMAP, ONERA, and EMS in Bordeaux, and also especially Benoît Burban in French Guiana at the EcoFog lab, which helps us a lot regarding the local and technical activities. Sorry. Okay, so briefly the outline. So I will first present give an overview of the experiment, especially regarding the key events during these 5 years of acquisition. Then I will present the key result at P-band, especially regarding all the impacts for biomass. Then I will talk about the synergies, especially between P, L, and C bands, and also with passive measurement at L-band, plus in the infrared domain. And then we'll briefly address the question of how to generalize or spatialize this data, since, of course, the main drawback of this experiment is that it's very local, as we will understand with the following slide. So first of all, so TROPISCAT-2 has been made possible thanks to the heritage of past very similar campaigns, so especially for the TROPISCAT, so a bit more than 10 years ago, which has been made possible thanks to the support of ESA and CNES, and also in collaboration with many of you, and especially at ONERA and Polimi. And then we moved to AFRISCAT for about 2 years in order to generalize the result, especially in order to address different forest structure and especially different forest topography. And then we decided to start with TROPISCAT-2, so again in French Guiana, but with the main idea was actually the objectives were twofold. First of all, to extend the previous time series, because we really figure out that even 1-2 years, it's not long enough to really have a fairly good picture of the viability in terms of environmental condition. And also to explore the synergies between, so mainly between P, L, and C band, plus more recently with passive measurement at L band and in the thermal infrared domain. So for those who don't know, the concept in very short, so it's a small radar. So actually, it's a vector network analyzer connected to several antennas, which are observing about 1 hectare of the forest land just below the forest tower. And here we have a picture of all the antenna network at P and L band. It's the same antenna. and then the smaller antenna at C-band, which are on antenna. And then here is the radiometer developed by the TeraTech company in Zurich. And here is the thermal infrared camera, which has been also installed there. Okay, and the purpose, of course, was also to consolidate the link between what we observe, especially thanks to tomography, with in situ measurement, and especially what is still a very big challenge in the characterization of vegetation water content within the vegetation scatterers. Okay, so briefly, some characteristic of the GUIA-FLU test sites. So basically, it consists of this flux tower, so surrounded by very intact tropical forest. So with here the main characteristic, and especially we can see as the typical annual rainfall a bit more than 3,000 millimeters. And then also we have all the meteo measurement regarding atmospheric condition plus in situ measurement, especially in terms of soil moisture, plus of course the fluxes, which are really the key asset and really the added value of this flux tower, because often we are thinking about the only way to really have the true measurement of biomass consists in destructive method, but another way is also to capture directly the carbon fluxes, which give you, without any conversion, the direct measurement. Okay, so here is the representation of the forest stand seen by the radar, so according to the antenna pattern. So yes, also one drawback of this system is that we do not have any resolution in the azimuth direction, so this is a top view. But of course, we have the vertical resolution thanks to the tomographic array. And here is the representation also of forest size. So for the ground topography, so we can see that also one of specificity of this set size is the slopes about 10% opposite to the line of sight of the radar. And here is the canopy height model. So in red, actually, is the one really seen by the radar due to the antenna pattern. And in green, it's just to have a dialer. It's a shorter, about plus or minus 10 meter average. And so I don't know if you can see it, but the two curves they actually are very interesting. It's the difference between so ALS. So airborne LiDAR scanning data from 2016 and 2019. So we can see that the difference is about 30 centimeters. So which is quite small, but which is still significant. And we had also some TLS measurement, so in order to get, of course, better estimates of biomass, or at least of volume. And plus, the main objective also was to use these forest mockups to generate 3D model and then parameterize electromagnetic models. Okay, so here is this synaptic. So show you let's say the main events regarding the past 5 years. So we started in March 2018 for the P and L band. Then in July we started the C-band acquisition. So so it's not yet the 5th anniversary for the C-band data. Then in 2020, we could start the thermal imaging mode. And also, interestingly, in July 2021, so we could reconfigure the C-band array with tomographic capabilities. Plus, we could add, thanks to ESA support, an L-band radiometer in order to get brightness, temperature, and to mimic smooth data. And yes, And so we can say that since November 2022, so we have all this measurement, so from the passive one to the PLC active, and with tomographic capabilities working together. Because of course, one challenge is to make all this measurement working simultaneously. And unfortunately, so it was also due to the COVID lockdown, so we couldn't go earlier on this website. So we have mainly this failure, so in the first half or in the first part of the 2021 year, due to switch issues. Okay, so now some of the main results. So first of all, we could, with this very large time series, we could compute some what we call the long-term coherence or long-term assessment of the temporal decorrelation. So basically, we only pick two times. So T1 would be the reference, and T2 will determine what we call the temporal baseline, and then study how, for a given baseline, gather all the possible data which correspond to this baseline, and then compute the coherence. So in this formula, it's simply the way we are multi-looking. So of course, we could use the spatial footprint plus the polarimetric channel plus various multi-temporal sequences. And then what is yes, very, very interesting is that we can see that, yes, of course, for this long-term trends, if we, let's say, we approach for instance, one global cycle for the biomass mission. So basically, so now it's something like about 8 months. We still have some quite significant values, so it's not completely noise. Sorry. So we could imagine also once biomass will be launched to exploit this zero baseline temporal coherences between global cycle with the biomass data, especially forest change. Something also interesting based on this long time series, and especially in terms of statistical analysis. So we could compute, so as for Tropiscat or even Afriscat, on, let's say, only 18 days coherences, which is the lag between the first and the final tomographic acquisition plan for biomass. But this time with much larger statistics, and we could, so almost for these 5 years of acquisition, have really a fairly good picture of the variability. So we can see that, yes, the variability is quite significant. So to have an idea, for instance, after 18 days, a coherence of 0.6 means that almost half of the 7 acquisition will be below the threshold of 0.8, which is often used as the critical value beyond which the temporal decorrelation has a significant effect of the tomographic reconstruction. So yes, so something to have in mind. So apart the analysis of the temporal coherency, so of course we could analyze the backstructuring intercities a long time. So basically, once we process the tomograms, we could extract, so in this case, 2 layers. So basically the top layer and then the ground layer, as let's say it will be possible with the biomass mission. So yes, so here is some of the average profile in the dry and in the rainy season. So still we can see that, yes, the differences are not that pronounced between polarization. This also confirms that, yes, in our case, the ground contribution is quite weak. So again, it's due to this 10% slope opposite to the radar. And in this example, so what is yes, interesting is to see for the ground contribution. So and especially it was really marked, really pronounced for this period, the decreasing trend of the backscatter of the ground contribution as a function of soil moisture. But of course, since the ground contribution does not impact much the total contribution, the total signal is quite stable. So we'll see later how we could spatialize or generalize this configuration to let's say, flat forest or even with opposite slopes. So now, yes, I need to speed up about the synergies. So one thing we could do, maybe the most immediate result between what we collect at P and L band, was to relate the coherence, the temporal coherence, because we could see from this curve that the shift is almost constant. So what is interesting is that, of course, the patterns are completely different between dry or rainy season. You see, in a rainy season, we have this abrupt drop, but then you reach a kind of plateau. And what is really funny or surprising is that at the end, even after about 1 month, the coherence in the rainy season are higher than in the dry season. And since we have more or less the same patterns for P and L band, we could directly compute one versus the other. So in this graph, I put in this x-axis the L band decorrelation and the coherence on the y-axis. So that's why the curve is not along the one line. But we can see that yes, the dispersion is quite small. So in other words, we could imagine to use, for instance, the PolInSAR observation to estimate with a zero baseline configuration the L band decorrelation, and then estimate the P-band coherence with not, of course, with simultaneous data, but with let's say a short time lag if we expect an ISAR every 12 days. Okay, so this is maybe a bit more prospective in terms of feasibility in a space-borne scenario. But still, if we look at what I call the high revisit coherences, it means that temporal coherences computed every 15 minutes. So for the 4 frequencies, we can see that, and yes, maybe the most astonishing thing is that the coherence at C-band are not only driven by wind, and especially during the morning when the evapotranspiration starts, because we have the minimum for the wind speed. But then here you have this drop in the C-band coherence, showing that this drop is really due to evapotranspiration and not wind at all, so which is quite interesting, especially if we imagine what we could do perhaps with the geostationary emission like Hydroterra, for instance. And in this case, if of course we generalize this at the scale of 1 day with several reference, we could compute so what I call here a similarity index. So basically, it's representing all the data with the same level of temporal decoration. We could reconstruct the curve or this similarity index, which would explain or reproduce this variation, which could be a good proxy of the hydric status. I mean, as long as the vegetation, the water vegetation content change impact temporal coherences. Okay, so now in terms of synergy, so since we could install the P-band, the L-band radiometer, we could, of course, do more or less the same temporal analysis. And what is really interesting also is we have very specific patterns for both dry and rainy season. So here you have the dry season with almost 10 degrees of difference of amplitude between the max and the minimum. And whereas during the rainy season, so here, for instance, in December, it is much reduced. And yes, so here you have the full picture of the year. So, and here is a soil moisture, which do not at all impact the absolute value of temperature, which is, of course, not that surprising regarding the ground to volume contribution at L-band. And what is interesting, shortly, is the fact that these diurnal patterns were also more or less the same with the thermal infrared, with, of course, very significant difference between dry season with almost 10-degree amplitude, or in the rainy season with something like 4 degree. Okay, and in short, so now of course the key thing with the data is how to spatialize and generalize this result to more, let's say, diverse configuration. So this, of course, is a very simple model which would work, of course, for the same range of biomass, but maybe which works quite well to predict what would be these estimates with different volume or ground to volume ratio, mainly due to the topography. So we could, thanks to the tomographic decomposition, use in this example, so temporal decoration for the volume and for the ground, and mix it with this kind of mixing law to find the total contribution. And shortly, to relate this to meteo conditions, this graph just give you an idea of what we could lose with space-borne estimate or with satellite estimates of meteo data on a local test site. But still, the results, especially here for the wind or for precipitation, are quite comparable. So, to conclude, we were very satisfied with this 5 years of data, which are not only at P-band, but also at L and C-band. And what is very important is that they are quasi-simultaneously acquired. And then, in addition to vertical structure analysis, we could also use tomography capabilities to spatialize the result, as I said, with various ground-to-volume ratio. And then, beyond all the results related to biomass, we could also explore what we could have, for instance, with a geostationary satellite and high revisit, meaning subdaily coherences to characterize not only structure but also vegetation water content, which is very important to estimate the dry biomass. And I say to open the debate, we cannot bypass fresh matter to do that. So with this, I conclude my talk, and sorry for the putting a cake here without the moon time. Thanks.
Thank you a lot, Ludovic. Are there any questions? I know it's a little bit late, but maybe I have just. So basically, that's what we have a job is scattered through 5 years ago, so now it's his birthday. So can we go back a little bit in history? In 2011, we have a job is scatter 1. And we see the phenomena due to we have the video which see the center of mass as a function of over 24 hours. So it's go up and down because we see that because there is a water inside the trunks, they change it as a function of time. So now you have some derive some index something like high risk status, and we see something like similar. So is there any perspective to make our work in the past, maybe such work?
Yes, of course, a good point. So it's true that I didn't present anything regarding the estimate of vegetation water content and dielectric permittivity, thanks different sensors. So we try with a soil moisture dedicated sensor to put directly into trees, or to radar measurement with a very small radar with antennas attached to the trunk. But yes, all this processing are I would say ongoing, and we have some result, and especially at the scale of diurnal variation. And what we could really better understand in comparison to TROPISCAT is really the impact of and the variability of these cycles according to dry or rainy season. So which is really something, which is the easiest way to capture this variation.
Yep, maybe because you are the keen after electromagnetism modeling. So is there any linking that phenomena over 24 hours in your model?
Yes. It's really the objective to better parameterize this vertical gradient in terms of dielectric permittivity, and especially, what is really useful is to have the free frequencies, because then you can really, if your model is able to reproduce the data in free frequencies, meaning with a different vision of the vertical structure, since of course at C-band you are mainly sensitive to the foliage. This is some very powerful tool to validate the model. Yeah. But maybe it will be the topic of another presentation.
Yeah, thank you a lot. So I think it's time to close the session. So we thank a lot for all the speakers to give a very interesting talk. So gratitude for the end now. Maybe thank you a lot for your joining. So have a good lunch. Thank you.
Non c'è.
Ok.
Quindi c'è ground più forest.
Sì, no, esatto.
Yummy, 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 yummy. Yummy.
Hello, hello. It works. Just a quick announcement. There's not too many people here. Huh? They're all for. Before we go into the session, so we have two sessions now, one on cryosphere, one on ocean applications. At the ocean application sessions, there's a parallel session on setting up a global network for forest validation. In the program, it says it's a closed session, but if you're interested, you're very welcome to join us and contribute to the session. That was the only announcement I want to make. Thank you.
Okay, now it works. Okay. Yeah, so unfortunately we have to start because otherwise everything gets delayed. And I welcome you to just come into the room, settle down. You can still have your sandwich if you need, but just to be here. Okay, so I'm very glad that we have also a cryosphere session at PolInSAR. I think that's also very traditional, actually. Over the years, we had always the forest part, which was extensive, but also the cryosphere is very extensive. We have a lot of very good works ongoing there. We know that Polarimetry and PolInSAR, but also TomoSAR, really works well also over snow and ice area. It's not probably progressing so fast and so far as for forest, but it's very, let me say, dynamic region of interest in terms of science and also science development. Yeah, my name is Arina Heinzig. Probably everybody knows already from the previous presentation, and I'm very happy to chair together with Thjörben Ertoft here together this session. And we are very happy also to have very nice speakers of this session. They are more in the relation to the topics of snow water equivalent. We have several of them and some other volume snow related topics. And with this, I would like to ask the first speaker to come to the speech or to the stage, which is Stefano Tebaldini. And he's presenting a paper that is called An Investigation of Snow Water Equivalent Retrieval by Cross-Track SAR Formations.
Okay, so thank you very much, Irina. Welcome again. And so it's my day today, yeah? Okay, so this work is an investigation of getting snow parameter with an across-track formation. Here is some motivation why we want to do that. Basically, the seasonal snow cover is a very important parameter. It's important for the climate, it's important for freshwater availability, and it affects the life of billions of people. But I think it's fair to say that an accurate assessment of snow depth and SWE is still challenging, especially if we go in mountain regions. This is a very short and incomplete review of the current techniques. There are high-resolution stereo imagery from Pleiad. They can tell snow depth by diamond differences. The reported accuracies can range from 50 to 60 centimeters at the scale of a few meters. Measurement of snow depth from altimeters are quite limited. When it comes to LiDAR, they only provide profile and a coarse resolution across track for the radars. SWE retrieval based on SAR radiometry and polarimetry, let's say that there are papers where it is reported that it goes very well. There are also papers where it doesn't go so well. And my take is that the polarimetry and radiometry are inherently based on physical models, and sometimes the physics is different. Then we have retrieval based on differential interferometry. This works especially well under the fundamental assumption of a transparent snowpack. There are, again, papers where it can provide an accuracy of a few centimeters, but it is critically dependent on local coherence and on how well you can compensate topography and the tropospheric propagation. So, for this reason, we would like to tell SWE and snow depth based on SAR tomography. And we have a background for this. We did explore this idea 10 years ago actually, with Laurent. And we had this experiment with ESA where we installed the ground-based radar section, tomographic radars. And this is basically what we saw. This is a tomogram of the snow, and we can count here a few layers. This was corrected for refraction, and it turned out that all the layers were correlated with some changes in the physical property of the snow. So now, just to tell you a little bit about this experiment, it took place in Austria at the site of Rothmos and Leutasch. The experiment was done with a VNA equipped with a few antennas. The VNA could be moved along a rail, and so we had a synthetic aperture radar. It was an ultra-wideband experiment that we had 4 gigahertz of bandwidth at X band and 4 giga in KU band. And this is young me, and this is young Laurent. And so basically we use this experiment to first to produce SAR images and then to produce a tomographic cube based on which we extracted the vertical profile of the snow. This is the first thing that we saw. Here we have the normalized intensity at X band and at KU band. It's nice to see, this is normalized. It is not an absolute radiometry. It is just to highlight the contrast. The true snowpack thickness here is 140 centimeters. We are on a flat terrain. We can appreciate that we have a very clear imaging. We can detect 5 scattering horizons, so 1, 2, 3, 4, 5. And of course, you are noticing that they are tilted towards the radar. And how so? The answer is pretty simple, because of refraction. Of course, the snow is a refractive medium. And so we have that if we focus without accounting for the change of wave propagation velocity, then we, let's say, a point that is physically here will appear at this other position. And this is a function of the contrast of velocity, but also of the local incidence angle. And so, for ALPSAR, we developed, or rather a brilliant student of Laurent back then, developed this method to estimate refraction based on the simple assumption that we knew that the terrain was flat. So based on this, we knew that the snow layers had to be flat. So basically, we corrected for refraction of the different layers until they would appear flat. And this was done in an iterative way. So we start from the upper layer, then we correct for it, then we go to the second layer, and so on. And this was the final result, as we were, as I was describing before. We could detect those 5 horizons. In this case, we were lucky enough that we had the snow pit prepared right after our experiment. So, and we had snow expert that could measure by hand the composition of the snow. And so we could carry out a fair comparison between what the radar was seeing and what the snow was like. And basically, the good news is that for every interface detected by the radar, we had a change of the structural properties of the snow. I have to say that we are not the ones who are looking into extract interferometry or extract tomography to look into the snow. So here, just an incomplete list of other people that were as crazy as we are. There is the ESA Snow Lab campaign by our friend Otmar Frey, using this SNOWSCAT experiment, and they provided multitemporal tomography to investigate the response to varying conditions. A paper by Tu et al. to investigate the snow stratigraphy by thermosar in changing condition at the Fraser. Chiao again provided an experiment with UAV-SAR tomography. This is very recent, and it is interesting because they reported an accuracy of just a few centimeters about the snow depth. We had the work by Yang Lei to get the dry snow parameters based on PolInSAR, basically. And then work by Patil and Ali, again using X-band PolInSAR data that was based on an empirical relationships. Now, the concept that we have in mind is basically to leverage the idea of minimum wavelength, minimum redundancy, wave number illumination that was presented this morning to come up with a very high resolution space-bound tomographic system to illuminate the snow and get the stratigraphy of the snow. This is how the concept would be like. We are considering X-band radar payloads. This because at X-band we have a lot of bandwidth, so the ITU allows for a lot of bandwidth, and in our experience, based on experimental data, X-band is a good compromise between penetration and sensitivity to snow layers. We are assuming a system with full multiple input, multiple output capabilities. We will go with FDM, so the access is done with frequency division multiplexing. We call this a rainbow system. Basically, I think it is the most simple way to build a MIMO-SAR. And there is an optimal formation deployment according to the principle that was discussed this morning. Matter of fact, we calculated that with 4 satellites, we can have a height of ambiguity of some 8 meters and a Fourier vertical resolution in free space. So without considering refraction of half a meter, this is the equivalent of an experiment with 16 monostatic passes. Or with 5 satellites, then we can have a height of ambiguity of 10.5 meters and a resolution of 0.4 meters in free space, which is the equivalent of 25 monostatic passes. So let's say that we aim at doing something similar to an airborne or a ground-based campaign. And this is just an example. This is the simple simulated snowpack. There is no snowpack physics in there. It's just a collection of layers, so we can mimic the spatial decorrelation, though. And this is how it would look like with 4 satellites and with 5 satellites. So let's say that geometrically, we think that we can detect there's no stratigraphy with a space-bound system. For the retrieval algorithm, so let's say that we are considering the 2 cases. The first one is what we call a layered snowpack, meaning that we assume that we can detect different scattering horizon, like the first one corresponds to the snow-air interface, then intermediate layers, and then the bottom. In this case, the retrieval algorithm is based on the apparent depth that you can measure with tomography. Let's say the difference between the any 2 nearby scattering horizon. This apparent depth is linked to the true depth by this parameter, which is a function of the velocity contrast and the incidence angle. So how can we invert? Well, this is a problem because it is true that the local incidence angle is known, but snow density is not known, as snow density is what gives you the velocity contrast. So this is just one equation in two unknowns, and so it seems like a no-go unless we use some prior about the snow density. But it is also true that if we add another measurement at a different angle, for example, let's say one measurement at 25 degrees, the other measurement at 40 degrees, then we can solve this system. So we can simultaneously solve for snow depth and density, which means for the ZWI, and this could be done for every layer. In the case of a transparent snowpack, so we assume that the snow can be very dry, so dry that even at X-band we just see the bottom layer. In this case, apparently we are in trouble. We cannot estimate the depth because we just see a single layer, but we can estimate its apparent height, and this is given by the height of the air-to-snow interface minus, again, the same factor that multiplies the snow depth. Again, in this case, no direct measurement is possible, but, but if we add another measurement at another angle, then we have that if we take the difference between the apparent height, then we can relate this difference to snow depth in this way, and it turns out that this relation is pretty much linear. And this is something that we can calculate, and so we can say that the difference of the apparent height is proportional to snow depth. This is more or less the same concept as of differential interferometry. It is just recast for across-track interferometry. This is an example of a sensitivity analysis. So what accuracy do we get if we go 1 centimeter wrong about the estimation of the apparent depth? And it works pretty well, especially for high values of XV. So when the density is high, and especially when the snow depth is important. This is the same for the case of the transparent snowpack. In this case, we also account for a model error due to the fact that the connection between the height difference and the SV is not perfectly linear, but okay, it's sort of work. And then, more seriously, we also run a performance analysis, this time as a function of the signal-to-noise ratio for a given configuration. And so this is with 5 satellites with 2 incidence angles with 100 lux. This is the snowpack that we are simulating. So in this case, there is no internal layering, just the bottom interface and the upper interface. And here is the accuracy that we are predicting concerning the depth and the total SV, which is, I would say that as the signal-to-noise ratio is better than some 5 dB, becomes interesting. And this is the same thing, but for a layered snowpack. So in this case, we are considering 1 internal layer, and we are trying to do something more difficult. So we want to estimate the depth and the SV of both layers. And again, it seems to work. So before I conclude, let's say that with this work, we investigated the potential of a tomographic formation to get snow depth and SV. It's a new concept, employing small satellites too, no? Oh. Okay. Okay. And the nice thing, the thrilling thing to us is that it is capable of a sub-meter vertical resolution from space. The concept is complementary to radar altimeters like crystal. Of course, crystal has another looking geometry. Tomographic system has a different geometry. You have advantages because you can conjugate the vertical resolution with having a large swath. And concerning the roadmap, let's say that the SV retrieval performance in this case is ruled by the accuracy to within which the apparent height can be retrieved. We can guarantee a fine vertical resolution by our formation deployment and by FDM MIMO tomography. Getting a good signal-to-noise ratio is more critical, of course, because we are talking of a small satellite. We also getting 2 independent view is a bit critical. We are considering different approaches. Soft, we just exploit topographic variations. Brute force approach, we just get 2 different incidence angle in 2 different geometries. Or practical, we can exploit synergy with radar altimeters. And I'm done. Thank you very much.
Yeah, do we have any questions?
Thank you for your presentation. I just have like one query. How does like the temperature of the snow affect your results?
The temperature?
Yeah, temperature, surrounding temperature.
Well, based on experience with experiment, let's say that if the snow is melting, then we only see the top layer, in which case we cannot tell the snow depth, of course. We will detect melting snow, but in this case, this is it.
Okay, I mean in dry condition also, if the temperature is like varying, I mean, does it affect the how much the signal will penetrate in the snow?
So let's say that based on the experiments we saw until now, we think that X-band is the best compromise. So it is the frequency that, so if we, unless we go for a multi-frequency mission, we assume that at X-band we will see the bottom and the top and some internal layers in most cases. But of course, it will depend on local snow conditions. Okay. So there will be conditions where it fails. Okay. But this goes for any other system.
Okay, thank you very much.
More questions?
Yeah, thanks, Stefano, for this very nice concept. I mean, you actually answered already the first questions I had. Maybe one comment. We spoke about already, sure. Exploiting the topographic variations in mountain regions for this sounds like a very appealing idea because it's an incidence angle of opportunity, so to speak, but it's very questionable if you have the same.
It's a speculation until now, yes.
On both sides of the mountain. But I really liked your summary also of the state of the art in the beginning and this question of what part of the snow do we see with X-band. I mean, you clearly show with the ground-based tomography experiment that you see all these layers and all these horizons. Yeah. But then looking back at all these studies around core H2O, for instance, people were showing that they have no signal in X-band from the snow. So I find it quite interesting that we get such different results, maybe just depending on the snowpack conditions, as you just said. But what was puzzling me in your ground-based result is that we don't see the ground at all. You showed this 5 horizons, but from the description it sounded like the last horizon was not the ground.
The bottom one was the ground.
But in the description, it looked like it's the last snow horizon, but not the actual ground. And that would have been strange if the ground doesn't appear in X-band.
I'm not sure I follow you.
Yes.
Here, our interpretation is that this was the ground.
Yeah, but the
it is slightly below.
This is the seasonal, you know, the spring snow which is captured within the snowpack. There is, especially in our alpine region, there's always a layer which is quite wet at the bottom. Okay. It is very, very often the case. In all our experiments, we've been many times in the French Alps, this was in Austria, you always have and this can be acts as a ground because it is made of very coarse grains. Sometimes it contains liquid water, and you keep it for the whole season, you know, until the melt.
All right, but so I can still sleep well by knowing the largest part of the signal will come from the ground anyway, even though we see horizons above.
This is, in fact, it will come. You see, this is the strongest contribution which comes from this, because it's remelted snow grains. Concerning your comment about the scattering by snow, yes, here what we see is not directly the scattering by snow, but it's the discontinuities inside the snowpack. You change from one layer to the other, there can be a crust, there can be something, and this is what you see.
Right,
yeah. I think we have to go on. So thank you very much for the discussion and the nice presentation. So the next presentation is by Yang Lei. Retrieval of snow water equivalent during snow accumulation using ALOS-2 and Sentinel-1 SAR interferometry.
Okay, thanks to Stefano, so I don't have to redo the literature review. And good afternoon, everyone. My name is Yang Lei from National Space Science Center in NSSC of CAS. Today, I would like to introduce some of my recent work on spaceborne L-band demonstration of the repeat pass INSAR approach for 3 retrieval over sparse vegetation covered regions. First of all, I would like to introduce and acknowledge my co-authors, including Jian Cheng or JC Shi and Jing Zhang from NSSC, and Professor Kunren Liang from Peking University, and Charles Werner from the Gamma Remote Sensing Company. Here's some background. So snow water equivalent, or SWE, is an important hydrological parameter. And most of the existing spaceborne demonstration of the repeat pass INSAR approach for SWE retrieval use C-band SAR signals with short temporal baselines, such as ERS with 3 days. However, given the large volume of spaceborne repeat pass L-band INSAR data archive from the existing and future planned missions, such as JAXA's ALOS, ALOS-2, China's constellation of twin L-band SAR, which were launched last year and just finished the in-orbit calibration, and NASA's NISAR, JAXA's ALOS-4, ESA's ROSEL, and also because L-band SAR signals decorrelate much more slowly than the C-band ones, especially over vegetation-covered regions. So it would be very interesting to show a spaceborne L-band demonstration of this approach. Although all of these missions strive to reduce the repeat cycle allowed to a few days, in reality, due to the actual data availability, we usually end up with a temporal baseline on the order of months, so which can be characterized by very low coherence. So it will be also interesting to investigate how long the temporal baseline could be in order to still guarantee a good SWE inversion performance. For example, if it works for less than a month, how about 5 to 6 months that capture the entire snow season? And how to deal with this low coherence problem for such large temporal baselines. Besides the low coherence problem, there's another problem due to the fact that most of the snow accumulation occurs over high altitude mountainous regions with not only high relief topography, but also covered by sparse and short vegetation. So what is the vegetation effect then? These are sort of the motivation of this work. Here's the refined INSAR processing workflow in order to deal with the first problem, the low coherence problem. So we have 4 components. The first one is the 2-step phase unwrapping procedure. You can see the coherence is very low. Let's see the laser pointer is working or not. Seems to be not working well. Can you see that? This one. Oh, sorry. Yeah, so the coherence is pretty low, so we cannot unwrap that high-resolution interferogram very easily. And so we choose to use a larger number of looks with a lower resolution, and then that can be easily unwrapped, and then will be upsampled to the high-resolution grid and serves as a reference to further unwrap the high-resolution interferogram. And after unwrapping, we go through this noise reduction step with some filtering and masking using the coherence as an indicator, and then some interpolation. And then we'll go through the troposphere phase delay correction step using reanalysis of weather data. And then the last step is the phase 2 SWE conversion using the DEM derived local incidence angle. Then we have this relative SWE product. And since INSAR can only measure relative changes, we need at least one single in situ data set to bring this to the absolute value. So that's this procedure. And then for the other problem, what's the vegetation effect? So we need some INSAR schedule modeling analysis. First of all, when there's no vegetation, the extreme case is we only have snow-covered ground, and there's tons of derivation in the previous works. So there's a linear relationship, a simple linear relationship here relating the INSAR phase to SWE change. And to the other extreme, when there's no snow, only forest over ground, and our group already derived a physical repeat pass INSAR schedule model by accounting for both dielectric fluctuation and random motion of the canopy for especially large temporal baselines on the order of months. So here we have beside the random motion profile, just as the RMOG model developed by Marco Laval, and we have also incorporated a dielectric fluctuation profile that's related to the dielectric fluctuation variance along the vertical dimension. So only in its simplified form, it appears as a modified version of the RVOG model, but it doesn't have to be that. And in this simplified form, you can see there are two terms related to the dielectric fluctuation of the volume and the ground, and there's a motion profile as in the RVOG model. Then we use this model and modify it to characterize the snow-covered forest and snow-covered ground. For the snow-covered ground, we need another phase term to be multiplied to the ground-to-volume ratio. So this term is exactly the same thing as shown on the top. And for the snow-covered forest, so we make assumption that the effective dielectric constant of the snow-covered forest slightly increases as a function of sweep. So that's the assumption. And then using this assumption, this derivation, we don't elaborate here, but it's essentially very similar to the snow-covered ground case. And then using this model, for the simulation parameters, we choose vegetation height around 15 meters and extinction coefficient around 0.1 dB per meter for sparse vegetation. Ground to volume ratio of -5 dB for HHO, that's what we use here. And the dielectric fluctuation and random motion terms are chosen as such to mimic the real ALOS INSAR data in our previous studies. And then we use ALOS tools viewing geometry. The last part, which is the most important part, we assume the effective dielectric constant of the snow-covered forest slightly increases as a function of sweep. So here's this one is the inversion. This one is the inversion result, the simulation results. You can see the inverted sweep almost goes linearly following the one-to-one line with respect to the actual sweep. However, when there's no vegetation. However, when there's a vegetation around with height of 15 meters, you can see there's a reduced dynamic range. Okay, so in order to validate this, we choose the US state of Colorado, where we have lots of in situ measurements. For example, the yellow dots show the snowtail weather stations, which record snow measurements, sweep, depth, density daily since 1980s. So there's a rich wealth of data. Then we have red dots here, the SnowX campaign in 2017. We have lots of snow peak measurements, but only during the February month. So for the radar data, we have the green box here, the ALOS 2 FBD stream map mode 3-sim mosaic with a temporal baseline of 4 months. So we make a note here, that's the only pair we can have in this ALOS 2 data archive during this time of year over this region. So we don't have any other option to use. And we also show some Sentinel-1 results from C-band as a comparison. So the red box shows the ascending and orange descending. Both are from TOPS mode, and they are available each month during this snow season. But because C-band cell signals decorrelate much faster than the L-band, so most of the pairs are not usable. And luckily, we only have one ascending pair, one descending pair with usable coherence, so which will be shown later. And the diameter tree height goes from 10 to 20 meters around this region, with an average of around 15 meters for the sparse vegetation. Then this is the processing line. We use ICE software, JPL's ICE software, to process up to the co-register SLCs. And then we go through the 4 steps, as I mentioned earlier. These are the technical details. Rather than going into the detail of the equations, what it essentially does is we generate a lower resolution interferogram, and then that can be easily unwrapped and then upsent to the finer grade, and then to further unwrap the higher resolution interferogram. And then it goes through a medium filter and use the coherence to only extract the high coherence points, and then assume adjacent pixels have similar sweep values. Then we can do the interpolation to get a wall-to-wall mapping. And then for the troposphere phase delay correction, we use the ERA5 weather data. And we also want to note that here the troposphere phase delay is pretty tiny compared to the L-band phase delay caused by snow, by SWE. And also, ionosphere correction is also considered in our processing. We use the split spectrum, but then the coherence is very low, so it's forbid the use of this split spectrum method. And then we also noticed ALOS 2 was acquired around midnight, so the ionosphere effect can be considered minimal here. Then the last step, we use the DEM-derived local incidence angle to calculate the conversion factor there, and then do the inversion. So here's the final product. Okay, so you can see the dots are 30 SNOWTEL stations, weather stations, and the star here is the one single SNOW-X calibration site that brings the relative SWE to absolute values. And then we show a visual comparison against the optical image. And you can see the Landsat observation was acquired 1 day after the second acquisition of the INSAR pair. So basically, our product is a pretty good visual mapping of the snow distribution. Then we want to do some quantitative comparison with the SNOWTEL in situ measurements. So this is the result. You can see, remember we used 4-month INSAR pair, and there are only 30 points available. So the R value is 0.5 with a low p-value lower than 0.05. So that's statistically significant correlation. And then the uncertainty seems to be large because we're using 4-month temporal baseline. So it can be reduced a lot if we use shorter months. Then the last part is the INSAR retrieved SWE variation goes like, has a dynamic range about 80 millimeter. But it's much shorter compared to the actual SWE variation, about 400 to 500 millimeter. So that's a little bit consistent with our model analysis. And we also want to show some C-band results as a comparison. So as I mentioned earlier, we only have one ascending pair, one descending pair with usable coherence. And for the ascending pair, we have a 6-day temporal baseline, and there are only 9 points with usable coherence, 9 points from SNOWTEL. So R value is 0.6, not bad. And then for the descending pair, we have a 12-day temporal baseline and 13 points from SNOW-X. And the R value is also similar. So what we can draw as conclusions from this C-band results is there are also statistically significant correlation. And the uncertainty is smaller than L-band because we're using 6 to 12-day temporal baseline. However, it's not recommended to use C-band because most of the pairs will be totally decorrelated due to vegetation decorrelation, temporal decorrelation. So we can only have one pair you can see from many, several months, a lot of pairs. So it's not recommended. And then the dynamic range of the inverted SWE is also shorter, even shorter than L-band case. We think this can be explained as more severe volume scattering occurs at C-band compared to L-band, but it needs to be verified later. So these are the take-home messages from this talk. You can see L-band INSAR has promising performance with usable coherence, even using a 4-month temporal baseline. Like after 4 months, it's still kind of correlated. And the uncertainty is not good because we're using 4-month temporal baseline and can be reduced a lot if you use shorter ones, such as INSAR will give us a rich data availability around 12 days or at least, less than a month, 24 days temporal baseline. And China has LSAR, the claimed 4 to 8 day temporal repeat cycle. We're trying to push that for our future work over some nice validation site. And C-band INSAR has poor coherence with the temporal baseline around 6 to 12 days, and it's not recommended to use because the vegetation temporal decorrelation is so strong. And L-band, both L-band and C-band have shorter dynamic range of the inverted SWE, and where C-band is more severely affected. So future work is definitely a lot of is yet to be done, like for example, the rigorous model analysis, and also more experimental validation using shorter temporal baseline. A little bit shorter is good, so such as 1 month or less than a month. L-band for different for forest conditions. That's it. Yeah, thank you for your attention.
Yeah, thanks a lot for this presentation. Very interesting combination between, to have forest and impact also calculated. I think that's very great. Are there some questions or comments, feedbacks to him?
Just a curiosity, you mentioned that in the presence of snow, the dielectric properties of the canopy or constant of canopy increase, but how do you know there is still snow in the canopy when you make the, because it can be on the ground?
You mean, how do you know where there's snow over forest?
I don't know if I know well this environment, but normally snow stays inside the canopy only for a while after it's blown down.
Right. So we actually, that needs more validation, but I searched on the website, I searched a lot of the pictures that people took during the snow season. They went to the snow mountain, the Rocky Mountain is in Colorado. They like to hike there and take a lot of photos. So I saw the snow on the spruce, the tree species, mostly spruce over these areas. And it's very short trees, but then a lot of snow accumulate on the trees, yeah.
Thank you.
Thank you.
There's another question.
Hi. Yeah, I have two questions. In the processing chain, you showed this step where you mask out the low coherence values and then you interpolate across that. And I was a bit wondering because in areas where you have a larger sweep change, that might be the reason for the low coherence. So by doing that, you might mask out larger sweep changes. So I don't know, I mean, maybe it's a necessary step, of course, but maybe that could also explain the lower dynamic range that you actually have in the result because you're masking out large sweep changes. And then I would, a second question was, because in that validation plot you showed significant correlation, but the color coding looked like it was the coherence level, and there you had coherences below 0.1 in the plot, or did I misunderstand this?
Let me go back to the validation. This one?
Yes, so if I understand the color table, you're using coherences of 0.05, which is interesting.
Yeah, so you mean the lower end truncated at the 0.05, right? Is it the question?
Yes, I mean, the color bar, the bluish values look like...
Actually, I truncated everything below 0.1. The coherence lower than 0.1 was truncated because that was totally, nonsense. And for the first question, exactly, that's exactly true. I mean, for the masking, it's not recommended to use for a little bit shorter temporal baseline. For this large temporal baseline, it's a trade-off. We lose information, right? It's kind of masking and then do the interpolation is not a robust way. I mean, for this, we don't have any other choice. That's the only 4-month pair we have from ALOS2. But in the future, if we have shorter ones, I don't recommend it to do that. Yeah, thanks for the suggestion. Yeah.
Do you have a question? Yeah, okay.
Yeah, so do I understand it correctly that you are trying to estimate the accumulation only? So you're not measuring the total snow depth or?
It's actually measuring, because the INSAR pair has just spans the entire snow season. Like the first acquisition was September 2016, and the next one is January 2017. So it captures the snow accumulation, and we have some ground truth. So it's the snowfall, mostly the snow accumulation occurs during this period, like 4 months.
How sensitive would it be to layering in the snow?
You mean
your accuracy in
You mean for layers, snow,
yeah.
or I mean using shorter temporal?
If you have several layers of snow.
Oh, that part. I think for L band is kind of mirroring the effective
SWE. I mean, assuming it's a uniform layer,
Okay.
so it's transparent, but it doesn't. We can do more rigorous modeling with a layer effect. Then I think it's worthwhile in the future work.
Okay.
Yeah. Thank you.
Okay, yeah, thank you. Thank you a lot also for answering all the questions. Okay, then we go further on with the next presentation from Christina Belinska from the German Aerospace Center, and she will talk also about SWE using interferometric and polarimetric SAR data.
Okay, thank you for the introduction and welcome to my presentation towards the retrieval of snow water equivalent using interferometric and polarimetric SAR data. So just as a recap, the snow water equivalent describes the amount of liquid water contained within a snowpack. So it would be the depth of water if the whole snowpack melts instantaneously, and it can be approximated by the product of the snow depth and density set in relation to the density of water. SWE is an important parameter for hydrological models to make runoff prediction and also for climate models because this seasonal snowpack is affecting our climate. SWE is also needed for water resource planning and management because many people rely on the seasonal snowpack for the water supply, and especially in the melting seasons, it's needed to make flood predictions. And we all know that SAR measurements are sensitive to snow properties because SAR is able to penetrate into the snowpack, and therefore we want to use SAR data to retrieve the SWE. The SAR data which we are using comes from the Tandem X satellite, which operates in X-band, and we always use dual polarized radar waves in HH and VV polarization. And the shortest possible baseline was 11 days. And the test site is located in the western part of Svalbard. And in the plot below, you can see an image of the coherence amplitude for an interferometric pair in February 2021 for the VV channel. And the really dark areas are corresponding to water. And the pink dot marks the test site. Because there's an in situ test site from the Alfred Wegener Institute, where they measure the SWE since 2019 with a passive gamma ray sensor. And they're able to obtain SWE estimates with a temporal resolution of 6 hours. And now we try to use our SAR data to retrieve the SWE there. There are different methods which can be used here. And for repeat path SAR interferometry, a 3-material model can be used, which relies on the fact that the radar waves are refracted in the snowpack. So here you can an example from a radar wave traveling to the ground. And when there's snow, due to the different dielectric properties, the radar wave is reflected in the snowpack. And this results in a different optical path length for snow compared to no snow condition. And this comparison not only works for snow compared to no snow, but also if there's already an existing snow cover and the SWE is increasing or decreasing. And it has to be taken into account that this only works for dry snow because the radar wave has to be able to penetrate into the snowpack. So this path delay can be translated into an interferometric phase difference. And by taking account of the geometry, the formula below is obtained, where K is the wave number, Z is the snow depth change, theta is the incidence angle, and epsilon is the dielectric constant. And one assuming a snow density and an empirical relationship between the dielectric constant and the density, following plot can be obtained. Here you can see the SWE change independence of the interferometric phase for X, C, and L band. And you can see that there's a linear relationship and also that higher values are obtained for L band compared to X band. However, this model has some limitation because we're looking at repeat path measurements, we have temporal correlation, and also phase calibration is needed. And as will be seen later, the phase delay depends on the polarization, which needs to be taken into account. Furthermore, the interferometric phase lies in an interval between -pi and pi, so therefore only a limited range of SWE values can be retrieved unambiguously, and outside this interval, phase swapping errors are obtained. So here you can see an image of the SWE change independence of the interferometric phase again, and when the phase gets larger than pi, it jumps against to -pi, seen with the dashed line here. And therefore, the values will be underestimated, and this can be corrected by adding a phase cycle. So for our case, this range was between -8 and +8 millimeters. So here you can see results for the SWE change for different interferometric pairs. So the days are always 11 days. So with red, you can see the ground SWE changes, and in blue, you can see the INSAR SWE estimates. So the points where there's no INSAR SWE estimates were from phases where the coherence was below 0.3. And yeah, so you can see that the values are unestimated. So now we take in situ measurements to check whether the actual speed change was above this threshold, and if yes, the phase cycle is added. So you can see that here. So you can see the values are now more closer to the ground measurements. Like we know that here for X-band, this phase rep correction has a big influence on the results. But even though it shows that it's important to take this into account when retrieving the SWI using the interface, so the phase rep due to large SWI changes. And the idea is to include polarimetric measurements to correct the phase reps without the need of additional ground measurements. And because additional information on the snow accumulation is contained in the copolar phase difference between the VV and HH channel. And due to the anisotropic structure of the snow, the signal delay and therefore the propagation depends on the polarization of the wave. So new snow forms a beginning more horizontally polarized wave, which leads to slower propagation speed of the HH polarization and therefore to increasing CPD values. Then over time, the CPD is decreasing due to recrystallization over temperature gradients. And therefore, the CPD can help to detect snowfall events and with the help of that, to correct the phase reps. So a snow model has been established, which models the SWI and which models the snow as ice inclusions in air. And then when assuming a snow anisotropy and the density of the snowpack, the refractive indices for the HH and VV polarization can be calculated. Here you just can briefly see the formula. It depends on the snow depth, and the part in the brackets depends on the incidence angle and also on the assumption which were made for the snow density and anisotropy. So we're now using the CPD changes for the Svalbard measurements, and to correct the phase reps according to that, following results are obtained. So this is only now a short time series and only for one location, but you can see that it's still better than with no correction. Here, the advantage was that it's less sensitive to phase rep and also no absolute phase calibration is necessary. However, there are limitations both for INSAR and PolInSAR. So you can have different SWI changes between two measurements. The SWI can increase or decrease, or the snow microstructure can change, changing the anisotropy. And depending on the temporal baseline, both effects can happen. So seeing that, the phase change is obtained for a SWI change and for an anisotropy change. And therefore, the question is whether PolInSAR can help to separate these effects. So to investigate this, we look at the temporal coherence region. So we always take two parametric SAR acquisitions from two different times and then form the coherency matrices for both images in the Pauli basis, and also the temporal PolInSAR matrix between them. Then we are looking at the temporal coherence region, shown here. And here, omega are the unitary vectors of the different polarization states. And we always take omega 1 equals omega 2. So now when applying this to the data, following results is obtained. So here you can see the tandem X data for one interferometric pair. And we've chosen one where the snow depth change was rather high and also the SWI increase was high. So here you can see a polar plot of the coherence region shown for 500 random polarization states. And the color is marking the alpha angle ranging from 0 to 90. And here from the first view, you can see that smaller alpha angles are more located at higher coherences, while higher alpha values close to 90 are more corresponding to low coherences. And the question now is which snow changes are influencing the coherence region, so the amplitude of the coherence, but also the extent of the coherence region. And to test that, we make a scattering matrix, SP, which should model a surface covered with snow. And for simplicity, we are taking the scattering matrix of a corner reflector, as seen here. And in order to model the influence of the snow, which is a refraction of the radar wave, changing the propagation, we include also a propagation matrix. Here, which can be seen with P2, and here K are the different wave numbers for the different polarizations for H and V. And in the formula, you can see the formula which is used for the wave number, which takes into account the geometry. And we use for the epsilon to distinguish between H and V the electric constant from the anisotropy model. And now the aim is to vary the snow depth and the anisotropy and to see what its influence is on the coherence region. So firstly, the snow depth is increased. So the anisotropy and the density are fixed to 0.2. And the snow depth at the first acquisition is set to 1 centimeter. And then the snow depth at the second acquisition is increasing the delta R, so the difference between them. And here in the polar plots, you can see again the coherences for 500 random polarization states. And what can be noted here that the coherence amplitude is always 1 because we haven't included the correlation effects yet. So in the first plot, you can see that there's no phase and no phase extent because no change was implemented. And you can see that with larger changes, the phase is increasing and also the extent of the coherence region. And here you can also see that smaller alpha angles are more located in the middle. So particularly interesting is the difference between the delta R 4 centimeters in the upper right and the delta R 5 centimeters in the lower left, because there the phase gets larger than 180 degrees and just correspond to a phase rip. This can be seen more detailed when looking at the interface. So here you can see the phase independence of the snow depth at the second acquisition, and you can see it in blue for the VV channel and in orange for the HH channel. And you can see that the coherence is increasing with increasing snow depth values at the second acquisition, and you can also observe the phase rip clearly. Another thing which can be observed is that the difference between the VV and HH channels are increasing, which can be also seen with the polarimetry. So here you can see the polarimetric phase change. So in blue you can see the CPD for the first acquisition, which stays constant because nothing changes there. And in orange you can see the CPD for the second image where the snow depth is increasing. You can see that the CPD is increasing there too. And therefore the CPD change shown here in green is also rising. We also calculated the phase extent of this coherence region, and you can see that it yields higher values than the CPD change. So the same can be done for an anisotropy change. So the snow depth and density is fixed, and the anisotropy at the first image is set to 0.1. And then the anisotropy at the second image is increasing. So you can see in the first plot again that there's no change, so nothing happens. And then the anisotropy is increasing the phase extent of the coherence region. This can be seen here. You can see that the interface. You can see that again that the interface is increasing with increasing anisotropy, and you can see it for VV and HH. And you can also see again that the difference between them is increasing, even though here the phase values are lower. So we're now looking again at the parametric phases. You can see that again the CPD of the first image stays constant, and the CPD of the second image is increasing, and therefore also the change. But here you can see again that this phase extent has higher values than the CPD change. However, it has to be said that here similar behavior is observed between an anisotropy change and a snow depth change. So to compare it to the real data, here's again the coherence region for the tandem X data for a snow depth change and the speed change. And now we projected it to the unit circle to have a better comparison with the model data. So we're now taking the snow depth change and calculating the density and assuming an anisotropy of 0.1, following can be obtained. So this should not be in comparison in terms of phase or extent, but rather that the model is able to reproduce some structures, which you can also see in the real data, and therefore there might be potential to investigate this further. So just to sum it up, it was possible to model coherence regions for snow depth changes and also for anisotropy changes, and the behavior was similar compared to the one with the real data. And it could be shown that the phase extent of the coherence region had a higher sensitivity than the CPD. So therefore, maybe it's useful to use that in order to correct the phase reps using polarimetry. However, the disadvantage was that it was not yet possible to separate anisotropy and snow depth changes. Therefore, further investigations are needed to influence the effects of snow changes on different polarization states, and also to include more parameters like decorrelation. So in the lower plot, you can see the coherence including SNR decorrelation, and by then adding more parameters like the decorrelation with phase or with alpha angles, so to have more observables to establish a retrieval based on the coherence region parameters in order to be able to separate the snow depth and anisotropy changes. So thank you for your attention.
Thank you very much. Are there any questions?
Thank you. Very interesting things. It's nice to see this coherency loci, work related to coherency loci. I see you don't simulate the correlation because you think there is no scattering in the layer. But we have seen from the first presentation that there could be scattering from interfaces. Is there any idea to introduce interfaces and that will explain the correlation or not?
Yeah, we haven't thought so far of yet because like we were assuming that snow is transparent and we just see reflection, but yeah, maybe it's possible to include that if.
Also, another thing, do you have any quad-pol data where you could check for these coherence losses?
Yeah, if there like would be quad-pol data available, it would probably help to model the coherence, like to model the full coherence region.
Because if you look at the coherence losses there, it will be a good indication if there are multiple layers. Because you will have multiple phase centers, you will start seeing triangles, these kind of things. So it could be a nice idea to have a look at that if you can.
Okay, thanks.
Thank you.
Hello.
There is a question behind there. Go ahead.
Okay. So thank you very much for your presentation. I was just wondering, like, when you were computing the alpha angle inside the coherence region, then is it something that you are always getting the alpha range from 0 to 90 degrees for every case, or you are also getting, let's say, maybe 0 to 10 degrees variance or something? I mean, if you go back to your slides in the coherence region, you are plotting the alpha angles. So in that case, I was just sort of observing that the alpha angle is always varying from, let's say, 0 to 90 degrees. So is there some meaning over there, or is it some random thing?
And also, like this alpha angle, like we modeled like 500 different polarization states. And alpha like is the Arcus cosinus of the first element, which describes theoretically the scattering process, with alpha 0 corresponding to surface-like scattering and alpha 90 to dihedral scattering.
So I think just what he meant is if you have also another range of alpha. So if you always have the full range like here, or if it's also less, right? This is what I understood.
Okay, so then we took always the full range.
Yeah, we had some other questions.
Maybe one. So you showed that you do, as time goes, just after snowfall, you have a change of propagation velocity for one channel and not for the other. And in this case, can you certify that the data remains correlated, that this strong change in scattering in propagation condition does not affect the correlation of your signal? Or did you check this on
We just checked the polarimetric coherence between the VV and HH channel, and it was like high.
I mean, the temporal correlation, does it stay at 1 during the whole process, even when you see these changes? I would expect that in the channel over which this change occurs, there can be some change, the correlation could decrease. Did you see this?
No, we haven't seen it, but theoretically, yes, when you have like a change which is affecting more the HH polarization, there the coherence should decrease faster. But,
thank you.
Yeah.
Okay, do we have any more questions? Could I ask a question? You mentioned this anisotropic behavior of snow. Is this always the case, or is there special situations where you have this?
And I think it was seen in different regions, like over Finland and over the Alps, and also tested in labs, but like the speed of the anisotropy change depends on the temperature. Like, so it's faster if you have higher temperature gradients.
Okay, thanks. Okay, then let's move to the next. To the next presentation. It's called Monostatic and Bistatic Polarimetric Observations of Snow Cover on Top of the Great Aletsch, is that correct? A glacier at KU Bend.
So thank you very much. My name is Marcel Stefko, and I'm for the Chair of Earth Observation and Remote Sensing at the ETH Zurich. And I'm here to present data from our ground-based observation campaign carried out in Switzerland at the Great Aletsch Glacier, where we have used full polarimetric, monostatic, and bistatic ground-based radar to observe the snow cover during different seasons. At KU Bend, so I think this is the highest frequency data so far presented. And for many of the people who focus on vegetation, KU Bend can be considered like too short penetration, and you don't really see anything. But when it comes to snow, even at Ku band, at quite short wavelengths, you do get quite some penetration, so it is of quite some interest for many applications, such as the aforementioned SWI retrieval. And so this motivates us to kind of perform these ground-based campaigns, because I don't have to really talk too much about the fact that spaceborne radar observation missions are extremely powerful at global monitoring of natural environments, but they do require extensive validation and exploration of the mission concepts before they can be developed and accepted. And ground-based systems can be a very cost-efficient way to explore these so far unexplored parts of the parameter space, whether it comes to using more exotic configurations, such as the bistatic configuration, whether small angle or large bistatic angle, or using full polarimetric radar in less popular frequency bands, such as Ku band. And so this is where our system Capri, which is based on the Gamma GPRI instrument and is a Ku band full polarimetric radar system, which is capable of both monostatic and bistatic acquisitions, coming into play, because it allows us to really explore this parameter space quite efficiently and at comparatively lower costs as opposed to other ways. And the bistatic operation mode, which we have deployed, is based on the idea of two Capri devices working in tandem. So you have the primary transmitter receiver, which is carrying out a monostatic acquisition, and then you have a secondary receiver, which also acquires a bistatic data set at the same time. I think the laser pointer has just stopped working, but, oh no, it's this one, okay. So, we are acquiring a monostatic data set, and at the same time, we are acquiring a bistatic data set from this overlapping region, while also employing a direct synchronization link in order to take care of the phase and oscillator offsets that, as we have seen today, can cause quite some trouble. And coming to the observation campaign, we have carried it out at the high altitude research station Jungfraujoch in Switzerland, which overlooks the Great Aletsch Glacier. And we have performed it in 2 seasons, so because we wanted to recapture the diversity of the snow cover properties in this region, so we had a campaign in late summer, in August, where the snow cover was experiencing daily melt freeze cycles, and the snow was getting quite wet, and then also late winter conditions when we had a large accumulation of the snowpack, of the fresh snow, and no snow melt present due to the very low temperatures. And we employed all the imaging modalities of Capri that I have mentioned, so we had the primary instrument observing the area from one terrace, and then the secondary instrument acquiring bistatic data was placed approximately 1 kilometer away, which created a quite considerable bistatic baseline. And this was also complemented with in situ measurements in order to gain insights into the actual microstructural properties of snow. To give you an idea of how this bistatic acquisition works, here is a top-down view of the beams of the corresponding primary and secondary device. And so when I play the animation, you can see that the primary beam rotates. It's a real aperture radar, so no synthetic aperture is used, but instead the beam is performing the focusing in azimuth, and as it rotates, the secondary device also acquires the backscatter data from the overlapping region and thus forms a bistatic data set under a variety of bistatic angles as the range distance increases. And to give first some kind of qualitative insights into the data sets, I am showing here the Pauli RGB basis from the monostatic polarimetric observations from both seasons. So for all the forthcoming slides, on the left it is always shown a data set from summer, when there were melt freeze crust present, and then corresponding conditions in winter when there was a fresh snowpack layer. So in the summer data set, we can see from the overall color of the scene that we are seeing quite a lot of surface type scattering indicated by the blue color, while in winter the scattering mixture is more diverse, and we see a correspondingly more diverse color mixture. And these are the monostatic observations, and we can also immediately compare them with the bistatic observations acquired at the same time. We can see that the bistatic data set, due to the configuration, has a lower signal-to-noise ratio and lower coverage, but nevertheless we can still observe the same qualitative interpretation of the scattering processes with surface scattering in summer and more diverse scattering mixture due to the presence of the snow volume in winter. And now we can move from a qualitative interpretation to more quantitative data. And so I will be presenting data from these radar observables. So because Capri is quite a multimodal instrument, so we have quite a lot of data to explore. At first, I will be showing temporal coherence at KU band, which can be of relevance for repeat pass methods. Because we are a ground-based system, we can acquire extremely rapidly with temporal baselines of 3 minutes. So we can really observe this coherence decay. Then I'll be showing the entropy and alpha angle for kind of a characterization of the scattering processes. And then I will devote some time for the polarization phase differences. So the CPD has also been mentioned in previous talks and is a quite well understood parameter which can be used as an indicator of anisotropy of snow structure or any kind of difference, and it has received quite some attention in literature. But then there is also the cross-polar phase difference, which is the phase difference between the HV and VH channels, and this one is not really receiving that much attention, and that is because in the monostatic case, due to the reciprocity principle, this parameter is always 0. But when you come to the bistatic case, this no longer has to be the case, and actually this parameter can have a different value, and so we wanted to investigate how does this parameter behave when you have a large angle bistatic acquisition. And again, to reiterate, we are at KU band, so 17.2 gigahertz, and that means that the short wavelength, even small microstructural changes or small shifts can cause very large variations in phase, which is both somehow a blessing, but also a curse at KU band, that you are very sensitive, but you very quickly accumulate phase reps. Now, about the temporal coherence, we have defined several regions of interest in the observed area. So we had an exposed rocky face of the mountain, and then a couple of regions of interest in the snow-covered area. And with the exception of the rocky face, which remains stable, we have observed quite a rapid decay of coherence caused by temporal decorrelation. So it is on the time scale of 6 to 10 hours, regardless whether we are in summer or in winter. That we lose the coherence in snow-covered regions. And so this is quite a short value when you consider implications for satellite missions, which often have revisit times on the order of days. And so this information can be useful for somehow guiding the design parameters of either airborne campaigns or spaceborne campaigns that would want to apply repeat pass methods in using KU band in snow-covered environments. But of course, so we have to keep in mind that this might not completely generalize to any kind of snow-covered environment, because the Alaj Glacier is quite specific and has quite some extreme conditions, such as overall very high wind speeds and similar. And coming to the polarimetric parameters, we can start with the scattering entropy. And here we can see a comparison of a morning and evening acquisition of each corresponding season. And comparing between the two seasons, we can see that the entropy is quite lower in summer as opposed to winter, again in alignment with the fact that there are melt-freeze crust presents, which cause lower diversity of scattering processes. And we can see also in the summer data set, comparing the top and the bottom, that over the course of the day, as the sun shines on the snow cover and causes further snow melt, the diversity of the processes further goes down towards just a single scattering process almost. And when it comes to what type this scattering process is, we can look at the mean alpha angle, and that can tell us that it is very likely a surface type scattering process, since the alpha angle observed is quite low, as opposed to winter, when the mean alpha angle has this kind of average value and is not so informative due to the high diversity of scattering processes. However, we can still also observe that the exposed areas where we can see the rock on the faces of the mountains, the alpha angle also remains low in alignment with surface scattering. And now we can take a very short break and go towards the polarization phase differences. I will be showing 4 slides, which will consecutively show the monostatic copolarized phase difference, then bistatic equivalent, and then the same for cross-polarized phase difference, so that we can really kind of visually and also quantitatively compare the differences. But already on this first slide, comparing summer and winter, we can see a complete diametral difference in the spatial behavior of this parameter. So the copolar phase difference has a relatively smooth behavior, and we can see that this should be quite feasible to invert, because there doesn't seem to be any kind of phase wrapping or discontinuity occurring. It just has a certain range or incidence angle dependence, but otherwise has a relatively smooth profile. But as opposed to that, in winter, we can see an extremely rapid spatial variation and a lot of phase wrapping occurring. So this almost even looks like it's noise, but this is not noise. This is the actual observed value of the CPD that just varies extremely rapidly from one range cell to another. And so this is caused by those small microstructural changes that very quickly can accumulate over a boundary of 180 degrees and cause another phase wrap. So when we perform repeated acquisitions, we get the same image. So these observation stays relatively stable on scales of minutes to hours, and then it shifts again as redistribution or any other changes occur. And again, the exception is, of course, the exposed rocky areas, but otherwise, this indicates that inversion of this CPD would not really be possible using just simple lookup tables. But if you wanted to use this information for some kind of parameter extraction, you would have to use more convoluted methods that would be more possibly statistical in nature. Now comparing this with the bistatic CPD that was acquired at the same time, we can observe almost like a remarkable alignment and really similar behavior in the bistatic CPD. So even though the bistatic angle is quite large, especially in the near range, we can see that it doesn't cause that much difference in the observed value of the CPD, especially in summer. And in winter, the values are of course not exactly the same, but they are still exhibiting the same kind of spatial trends. And now we can move from the copolar phase difference to the cross-polar phase difference. So again, reiterating, that's the difference between HV and VH, because sometimes different definitions are used. And when we look at the monostatic one, this one is not of great interest, maybe only to the person performing polarimetric calibration who wants to verify that indeed the calibration works and the phase difference is 0. But when it comes to the bistatic cross-polarized phase difference, we see a quite large non-zero value. So the spatial trends can be compared to the CPD, even though the values are quite different. So for the CPD, this region in summer had quite a negative value, but here it seems to have a positive value. Although this could be caused actually that the value has also been turning towards negative and then has simply gone over the phase wrapping boundary. Or it also, of course, depends on the definition, whether it's HVVH or VHHV. And in winter, again, the same story as for the copolar phase difference of very rapid spatial variation. And so what can we learn from these acquisitions? Well, we see that the polarimetric properties can vary very dramatically between summer and winter in such an environment when you're observing it at KU band. The phase differences at KU band are very prone to phase wrapping when a thick layer of seasonal snow is present. So if you have kind of a presence of melt-freeze crust or surface type scattering, you can observe a smooth trend of CPD, but if you add a layer of seasonal snow on top, it creates a very difficult situation for parameter inversion at KU band. Also, in terms of exploring the bistatic parameter space, we have confirmed that the reciprocity principle cannot be assumed when you are using bistatic data, because we observed a non-zero value of the cross-polar phase difference. And also when it comes to design requirements of KU band repeat pass interferometric missions, we have observed a relatively large rate of temporal decorrelation, which can then cause corresponding requirements for the revisit times of methods that would want to use repeat pass methods in this data. So with this, we have gained quite some insights into the scattering behavior of snow at KU band, both in the monostatic and bistatic modes. And we hope that this can also help provide better prior estimates for future observation missions or can help guide the design requirements of future observation campaigns. Now, we are continuing our presence at the High Altitude Research Station, so this is just to give you a very small sneak peek into what we are planning to do next. So we are currently also undergoing a more deeper analysis of the interferometric data. You can see also a poster by Esther that is shown in the back of the hall. And so we also, for example, want to assess the reconstruction of these three-dimensional displacements fields similar to what Harmony is doing. We are also looking into further analysis of the polarimetric data, and we are also performing new measurements leveraging the flexibility of the ground-based system to now explore the small bistatic angle space in order to investigate one effect called coherent backscatter opposition effect. I do not really have time in this presentation to talk about it, but you can also come ask me later if you're interested. So I'd like to thank you very much for your attention, and I'll leave the conclusions up, and thank you very much.
Yeah, thanks a lot, Marcel. It was a very great overview of the activities with a, let me say, stable radar system observing snow and snow properties. Are there some questions, comments, or feedbacks? Yes.
Thanks for your excellent presentation. Have you noticed any effect of imaging condition from near range to crescents on those polarimetric parameters?
Sorry, can you repeat? So,
have you noticed any effect of the imaging configuration or geometry of the ground-based radar from near range to crescents on your polarimetric parameters?
Yes, so I mean, even coming to the CPD, we can there see kind of a trend that the problem with our imaging geometry when you have a ground-based radar system is, of course, that many of these parameters are tightly correlated. So we have quite a shallow incidence angle in the whole scene, but as you go further downrange, it becomes even shallower, and so you have this coupling of incidence angle and range distance. And but here, for example, for the CPD, you can see that at near ranges, it seems to diverge further away from the zero value into the negative. So indeed, there does seem to be an incidence angle dependence.
So it's also good to look into satellite-based parameters and compare how you can kind of cross-validate these parameters. But not similar wavelengths doesn't exist, but like close one.
Yes, I mean, we cannot, there is of course tandem, which is at X-band, yeah, even though does seem to cause quite a bit of difference, but it's certainly something of interest for us. And also there is several actually Ku-band missions that are currently proposed. I think there is the SCLP mission, which should be using Ku-band, so we hope that it will get some data, even though I'm not sure if it's full pol. I think it's not.
Thank you.
Thank you.
Some other questions, comments? Yeah.
Thanks for the presentation. Really nice to see results with Capri. I used it many years ago, and I hope you are having the same fun that I had using it now, because it's really a cool system. The question was regarding these phases that you are showing there. I think you modulate them with the amplitude of the coherence, right? Because one
yes.
is very dark, the other is bright.
Yes, indeed, yes.
So it's nice, it's interesting to see that when you do the coherence HVVH for the bistatic, this seems to be very low, like in summer, for instance.
You mean this one? Or?
Yeah. Do you have any interpretation why there is such a big loss of coherence between the two cross going bistatic, but not too large bistatic?
Yes. I think this might also be an SNR issue, because here we have kind of several factors going against us. It's bistatic, which causes a reduction in gain. Then it's HVVH, which usually have a lower value of backscatter than copolarized channels. So I think especially here, and also in the far range, kind of due to the spreading of the beam, the resolution is not so bad. So I think maybe some different areas are also interfering with each other. This is something that we want to try to enhance in the future, because we have a lot of acquisitions, but they are temporarily spaced, and so we have to be very careful when we are putting them together. But we do want to try and see if we can kind of get some more data even from the regions that now have low coherence.
Thank you. That's Teresi.
Okay, yeah, so thank you. I think we're already late. We just continue now. Thanks a lot, Marcel. Okay, and then we proceed with the last talk of this session, which is from Georg Fischer, also from the German Aerospace Center. And he will talk about PolINSAR Fern density retrieval.
Yeah, hi. Thank you for the introduction. I'm Georg Fischer from DLR. And with this talk, I want to show you some ideas we have of how to look below the surface of an ice sheet and learn something about its subsurface structure. And one example of it being Fern density retrieval. So why do we want to do that? If you look here at our sketch of our little ice sheet, we have snow accumulating on the top every year. And the snow from the previous years then becomes firn, which becomes compacter and denser with depth until it eventually becomes ice. Now this situation undergoes changes over time. So the snow is accumulating, part of it might melt again, and that meltwater might then refreeze again in the subsurface. So it becomes clear that the volume change that we measure, for instance, with altimetry or soil interferometry, is not necessarily directly the mass change of a glacier or an ice sheet. And indeed, that's mentioned as one of the key uncertainties in these mass balance estimations and climate change studies, that density and density changes are critical to really know this volume to mass conversion for the mass balance. Related to that, also the refreezing of meltwater or the meltwater retention in firn is a key uncertainty, because in that case, the meltwater is actually not a mass loss, but it reduces the elevation at the surface. And of course, these parameters are difficult to measure, so it would be great if there's more information about their spatial patterns. So the idea is now what we can do from a PolINSAR perspective, right? Let's first look at polarimetry. You know, of course, all the advantage of polarimetry, of learning something about scattering mechanisms. But a key observable, which was already mentioned in the previous talks, is the copolar phase difference between HH and VV, because it gives us a sensitivity to the anisotropic wave propagation in firn. A more obvious way of looking into subsurface structure is, of course, SAR tomography, because we can basically do a 3D imaging of the subsurface. If we don't have the baselines for tomography, we can invert PolINSAR structure models, as you all know. And the fourth aspect I want to address in this talk is the multi-frequency information content. So I will now try to give you an overview of what you can do in all these four aspects and how we can maybe combine them. Let's start with polarimetry. So the key process behind this is the temperature gradient metamorphism of firn. That is due to the difference in temperature between the air and the temperature inside the firn, and that causes the firn grains to grow in a vertical direction. So we have a slight vertical elongation of those firn grains, leading to a dielectric anisotropy, which causes then this HHVV phase difference, this copolar phase difference. To give you an example, we look at an airborne data set from Greenland, where we have a 200-kilometer long polarimetric data take, and it starts at the very western edge of the ice sheet, very down low, where we have only glacier ice and no firn. And then we go to the right, higher up into the ice sheet, where we then have tens or like several meters or tens of meters of firn. And that data looks like this. So you see here the L-band HHVV phase difference. In the left part, we are in this ablation zone without any firn, and we get mostly values around 0. But then to the right, you see this very strong and reddish positive copolar phase difference appearing due to this firn anisotropy. This was modeled by our former colleague Giuseppe Parella, and he's actually watching the online live stream right now, so hi Giuseppe. And the way he modeled this was by considering 3 model parameters: the vertical scattering structure, the density, because this gives us the direct relation to permittivity, and then of course the anisotropy. So in the model, the anisotropy drives the shape of these vertically elongated firn grains. Then the density, of course, gives us the density of those firn grains in an air background. So we get as a model output the permittivity for the horizontal polarization and for the vertical polarization. If we then integrate their difference over the vertical scattering structure, we can model our copolar phase difference. So in the past, this was, for instance, used by making assumptions of all these model parameters to invert firn thickness. And now you see in the left part where we know from glaciology that there's no firn, we get some artifacts due to crevasses and extreme surface roughness. But towards the right, we can estimate firn thicknesses up to 10 meters. Now, what I really like about this model is that it gives us a direct physical link to density, with the potential to at least retrieve bulk values of subsurface density from copolar phase difference measurements. Now, to do this only with polarimetry, we need to make assumptions about all the other model parameters, which is, of course, not so nice. And we have to maybe keep in mind that the model is maybe a clever but also a strong simplification of the real firn properties. So this was polarimetry. Let's go to tomography. And for this, we will look at test sites which are higher up in the Greenland ice sheet, where we have tomographic data. And this is now a P-band tomogram where we see a quite uniform scattering distribution with depth, which slowly decreases with depth. And this is exactly what we also expect from our in situ reference data. So this is here a ground-penetrating radar profile. And the situation here is that there's relatively a lot of melting going on each summer. That meltwater refreezes again in the subsurface, forming ice features, ice inclusions, ice layers. And this causes this strong volume but uniformly distributed volume scattering structure. And that's also why our Pauli image here is so green. If you go a bit higher up in the ice sheet, we start to see very distinct layers in our tomogram. It's now, for instance, here at 5 and 10 meters. And this is due to the fact that we have here a limited amount of melting happening each summer, and that meltwater refreezes in the form of those distinctly frozen melt layers that we can also see in our in situ ground-penetrating radar. Now, I mean, tomography over ice is just beautiful. Not just these results, we've also seen other examples from other people here in the room on alpine glaciers and so on. So we really get these beautiful tomograms over ice. But of course, if we want to go towards geophysical information, we need to make the connection with modeling. And also, of course, we have only a few cases of dedicated airborne data sets where we have suitable baselines for tomography over ice. Now, let's try this. Let's make the connection between the polarimetric firn anisotropy model, but now we take the vertical structure from tomography as an input into the model. That leaves us only with the anisotropy and the density as unknown parameters. And similar as in the first talk today, we use multiple incidence angles to solve then for a bulk density estimate. So to jump to the results, what you see now in this plot here on the left in red is the copolar phase difference as directly measured from our polarimetric data. And the black line is the model result of our best fit. And that best fit we got for a density of 0.62. And if you compare this to a firn core from that location, we at least match quite well on average the density of the first 20 meters. Now, if you do the same model inversion at the higher test site, we get our best model fit for a lower density, and that's good because we expect also a lower firn density there. And also here, if you compare it to a firn core measurement at the test site, we of course cannot resolve all these fine details, but on average, those first results are quite nice. Now, this was really just the first shot of such a firn density retrieval. It's promising, but we have to keep in mind that here we used all the baselines we had, and we were throwing here inside a lot of samples with a lot of incidence angles to retrieve one measurement. So what is clearly missing here and what I would like to do as one of the next steps is sensitivity analysis in terms of incidence angles and baseline to arrive at a more practical implementation. We might not always have these baselines. So with limited baselines, we can then go towards PolInSAR models and their inversion to learn something about the subsurface structure. And a structure model for an ice sheet consists of well-known components. So these refrozen melt layers we can model as Dirac deltas. We've seen now this one test site where there are 2 prominent Dirac deltas, but potentially there could be even more. Each of that Dirac delta has a layer to volume ratio, and it can be located at an arbitrary depth. For the volume, we use a uniform volume model with this well-known exponential shape, but we allow for a vertical shift of the upper limit because we've seen in the tomography that sometimes the first few meters are quite transparent. Now, if we invert such a model, in this case, it's an inversion of a uniform volume with only 1 layer based on a triple baseline setup. I show you here the same tomogram as you've seen before, but now just with bluish colors as a reference for comparison. And the PolInSAR model inversion are in red, the upper limit parameter of the volume component, which quite nicely captures sort of this upper boundary of the main scattering. And in green, that's the inverted position of the Dirac delta, which quite nicely follows the location of the most dominant layer in the tomogram. So that's quite nice to know that we also can use limited baseline and PolInSAR structure models to invert at least the main scattering structure in the subsurface of an ice sheet. But of course, we always have to play this game between model complexity and observation space. And I guess, or I have the feeling that for ice sheets, it's also a bit of a question how appropriate certain model setups are across the different areas and locations. Now, to play this game even a bit crazier, we add the multi-frequency perspective to PolInSAR. And the motivation for this came actually when we looked at the tomograms. So down here at the bottom, you see the first 2 tomograms are P and L band, and they both show us these refrozen melt layers at 5 and 10 meters as we have seen them before. But then if we look at C and X band, another layer above at 2 meters starts to appear. So now our idea was, can we use a limited set of baselines by considering basically only the Dirac deltas in our structure to invert a more complete picture of those refrozen melt layers. And if you want to find Dirac deltas, there's an established algorithm for that, the music estimator, and that's exactly what we did here. So with a triple baseline setup and the music algorithm, we find quite nicely in each of the frequencies those refrozen melt layers. But of course, this depends a lot on the appropriate baselines. And for instance, at X and C band, you start to see some ambiguities appearing. But if we now combine this to a multi-frequency result, you see here in blue and orange the X and C band layer detections, which are very consistent for the 2 and 5 meter layer. And in red and green, the L and P band results, which are very consistent at 5 and 10 meters. So comparing to the significant refrozen melt layers, which we know from our in situ data, this multi-frequency result gives a more complete picture of the subsurface structure. Now, this was a multi-frequency idea of exploiting the different information content across frequencies. But we also see that across frequencies, sometimes these layers are common or at the same location. So for this, we had a different way of thinking about a multi-frequency combination, and with the idea of using the layer positions at one frequency to invert a more complex model at the second frequency. So imagine you have maybe tomography at P band, for instance, you get those layer positions, and then you can invert a more complex model at another, for instance, L band frequency. That's what we did here. It's again a triple baseline PolInSAR inversion, now with the layer positions as an input from P band, and then we invert the volume and layer to model parameters, the volume parameters and the layer to volume ratios from the model as shown before. And I thought I don't speak so much about the inverted parameters, but show you this in the sense of a simulated tomogram. So this is now not a real tomogram, it's a simulated tomogram based on the PolInSAR model inversion results shown in the upper plot. Now we see here that there's a lot of noise. We don't always get a nice result. Sometimes we lose the second layer. But if you compare it to the full baseline L-band tomogram, we at least get sort of the rough main scattering structure right. So these two multi-frequency ideas that I just shown are very preliminary ideas that we just wanted to try. But I think what became clear is that the additional information content by combining multiple frequencies is very obvious, both in terms of complementary information, but also we find common structures. But of course, having multi-frequency data at the same time, at the same place is always difficult. And I think there are for sure better ways of maybe exploiting multi-frequency data in the future. With this I came already to my summary. So I've shown you kind of a fast sweep through all the methods which have their different advantages and certain limitations. But I hope what became clear is that maybe the exciting way forward towards a subsurface structure information or maybe such a film density retrieval is by combining those methods and observation spaces. Thank you.
Thank you very much for this very nice presentation. We are a couple of minutes into the coffee break, but we will allow a couple of questions. Anyone who wants to ask?
Thank you for this very nice talk. I would like to ask you if you can summarize which data you need to get density, and then if you can comment on the applicability of the method in generalized snow conditions. So like you're talking about fern, but let's say that we consider dry snow, wet snow, different condition and even different depth.
So the way we combined here now the anisotropy model with vertical structure information, in this case from tomography. So for that we need at least copole polarimetry to have the phase difference. And I mean, in theory also just structure inversion based on a single baseline PolInSAR could be already a way forward. What is really required in terms of sensitivities and also incidence angles, that's something I still have to investigate. There I cannot give you an exact answer. But potentially it would be single baseline PolInSAR data, but then it's a question of accuracy. And of course we need, probably as you've shown it as well, quite a large incidence angle diversity to exploit that. Now this temperature gradient metamorphism in Fern, I think it's quite a, how to say, I think from the glaciological side a well understood process and happens, as far as I understood, everywhere where there's Fern. So I think that should be maybe good news in terms of applicability. Now, also for snow we have seen that we can exploit anisotropic wave propagation effects. But then probably we need quite, again, then different frequencies and to have the sensitivity. And maybe the structure information from your X-band constellation in space. Yeah? So I think there is potential, but the question about applicability and sensitivity and which kind of observation space we really need is still something that's to be answered.
Okay, thank you. So keep us posted, since we are discussing whether it is better to have a dual pole mission or a full pole mission. So in case. We're very interested in this topic. Thank you.
That sounds
One
good.
more?
Thank you very much for your presentation. When you say that the multi-frequency way of combining all these bands gives us the best results or added value information, have you compared your result of density of Fern using ground penetrating radar, or how did you validate and say that this is the best we can get? That's the first question. And among those wavelengths, which one individually gave the best density estimation, you think?
So which wavelength
yes, which
can
wavelength?
us give the best density estimation? Wow. So I think in quantitative terms, I cannot answer this right now, but I think it's also not sure if you can really compare frequencies, because for each frequency or wavelength, you get a different penetration. So you're actually measuring the density of a different depth, right? So it depends. If you want to access maybe just the density of the first few meters, you need X band. If you want to access the density of the first 20 meters, you need L band or P band. So I think maybe the question is rather what you want to measure, and then the question of
okay, at least if you compare with the ground penetrating radar baselines or layers, which one was closer in terms of these three layers?
I mean, that ground penetrating penetrating
GPR,
radar was a 500
layers.
megahertz frequency, which is rather close to
no,
P-band, right? So the most dominant layers in the GPR are those that we've also seen at L and P-band. So our X and C-band data have seen sort of finer layers, shallower layers that were only very weak in our ground penetrating radar data. So it's also then again a question which frequency or wavelength is the GPR. But I think that the power of multi-frequency is, in this case, also in the different penetration depth, right? So you can sort of sense different depth. Yeah.
Thank you.
Okay, thank you very much. Thanks to all the speakers and the nice presentations in this session. There is now a coffee break, and we should reconvene at 16:20.
Announcements. First announcement, because I was asked by a couple of people, the Geotrees meeting is an open meeting, not a closed meeting as was announced in the program, so you're very welcome to join us in the meeting room on the end of the room. Second, tonight is the night. I'm pretty sure you enjoyed the Fête de la Musique yesterday, but the real thing is tonight. Please join us at the PolInSAR party in the Delirium Café, which is only 500 meters down the road here at 9 o'clock. I also have to warn you, this is a self-served party, so ESA does not take any responsibility. Huh? But I hope I see you all there. Huh?
just to see.
So you know, so this is the
This
remote
is not
control.
the
It
one.
doesn't matter which one, both.
Okay.
But that's the laser pointer.
Thank you.
So hello. Maybe a little hello to everyone in the coffee break. We want to start the ocean and sea ice session and welcome you to take a seat. Okay, great to see that there are more and more people coming from the coffee break to the session. Nice. We still feel a bit alone here.
Hello, I want to welcome you to the last session of today about ocean and sea ice application, and we will hear 2 talks on sea ice application, one about sea detection, and 1 talk on PolInSAR methods using calibrations.
So the first talk will be actually slightly different than in the program. We had last-minute rearrangement, so we start with Yayasri Poludasu, who is responsible at ISRO for SAR calibration and validation, and unfortunately couldn't make it for the SAR mission and calibration session on Monday, but now it's great that we have her talk now, and she will speak about hybrid polarimetric SAR calibration and validation.
Yeah, good evening to all, and thank you so much for giving me this opportunity at this point of time. And I would like to present my paper titled Calibration and Validation of EOS4 Hybrid Polarimetric SAR Data. And I am along with my co-authors Samram Sahu, Niharika, Ramu, Usha Sundari, and Sita Kumari. And we all work in Indian Space Research Organization, ISRO, Department of Space, India. Yeah, as we all know that synthetic aperture radar with polarimetry has many applications related to right from the biomass and then agriculture, forestry, strategic applications, oceanography and disaster monitoring. Taking all these things into consideration, ISRO has come up with a satellite which we call it as RISAT-1, which is a C-band SAR, which was launched in 2012. So it is having the major modes like strip map, ScanSAR, and sliding spotlight mode with different polarizations of single, dual, compact, as well as full pole. And moreover, the swath coverage is from 10 kilometers to 23 kilometers, and with spatial resolution varying from 1 meter to 50 meter. And interferometric mode is also there, but presently it is in the experimental mode. And if consider the state-of-the-art technology, RISAT-1 is a C-band SAR. In 2012 it was launched, and it is first of its kind in the Earth observation to have the hybrid polarimetry apart from the mini SAR of Chandrayaan-1. And later, with that experience, ISRO has gone forward with ScanSAR mode of acquisitions, which is having the larger swath and offering both the hybrid as well as full polarimetry. So as we all know, hybrid polarimetry is transmitting a right circular polarization and receiving linearly both H and V polarization. So with that combination, EOS4 has been launched, and the motivation is to provide calibrated and validated data products to support the user community with the continuity to exploit the hybrid polarimetric data to have the long-term stability and data integrity. And the objective of the present session is performing SAR calibration and validation for EOS4 strip map as well as ScanSAR hybrid polarimetric data, and to implement different polarimetric decomposition techniques by deriving the Stokes parameters and performing the sensitivity analysis on standard radar targets. So in view of this, I just want to brief up about the Indian space program. So right from the conceptualization of the satellite in terms of studying the satellite configuration and the payload acquisition and the feedback from all the user community, the design, implementation, and the reviews, testing, approvals, everything will be finalized, and it is next followed by launch at Sriharikota in India spaceport, and later with the in-orbital phase a detailed analysis like mission performance and the data product quality evaluation will be done with calibration and validation. And after the due reviews, it will be operationalized for the stakeholders to utilize the data. And parallelly, it also supports the strategic user stations for the defense purpose. So if we see the Earth observation data processing for EOS-4, that is our radar imaging satellite 1A. So it is built up in a world-class environment, which we call it as integrated multi-mission ground segment for Earth observation satellites, and which is having a 3-tier storage area network with enhanced user services with online ordering and dissemination, data availability with minimum latency for processing, and efficient file transfer for a secure and scalable network, and automated workflows, algorithm development, and analysis. So the entire ground segment has been well established at Hyderabad at National Remote Sensing Center, and we have station at Antarctica also, so that we can have more number of downlinks and to support the data to the stakeholders with less turnaround time. And the data workflows, if you see, right from the data ingest, we'll have the pre-processing of the data and the data product generation, quality analysis, and after due product archival, it will be disseminated to the users via Bhunidhi portal. So coming in specific to the EOS-4, which I was mentioning, it is a C-band SAR, which was launched on 14th February 2022, having the 3 type of imaging modes called strip map mode, as you can see it here, and ScanSAR mode of acquisition, where the multiple beams will be switched on automatically one after the other with some overlap to have a larger swath coverage, and the spotlight mode of operation to have high resolution imaging. So with these different kinds of imaging techniques, so presently we are interested in the medium resolution ScanSAR mode having 8 beams and coarse resolution having 12 beam configuration, and which is having the swath coverage of 163 kilometers and 223 respectively, and covering the spatial resolution from 8 meters to 50 meters. So if you see the specifications of EOS-4, it is operating in the C-band of 5.4 gigahertz and supporting all the frequency bands, all the polarizations, and incidence angle from 12 to 55 degrees. So here are the spatial resolutions of all the different modes of strip map, ScanSAR modes, with worst case sigma naught of less than 18 dB is available. And these are the standard data products that are being available for EOS-4, where level 1 SLC ground and level 2 enhanced terrain corrected georeferenced products are available. Apart from that, because of its capability of hybrid polarimetry, we are having the value added products like with the projection UTM and WGS84. If you see the data product specifications, the geolocation accuracy is less than 50 meter, and with radiometric accuracy of 3.1 dB and absolute radiometric accuracy of plus or minus 1 dB is being specified. So these are the sample products that are available for a strip map. If you can see the Kuwait and Odisha and Australia. And these two are the ScanSAR mode of operation with medium resolution of 33 meter. So these are being used for the disaster support management also. And the data that is present to the user community via a web portal called Bhunidhi. So where you can get the data products with this link bhunidhi.nrsc.gov.in, where the users can put their request and then they can acquire the data and download the data. So apart from that, we are having all India coverage with 17-day repeativity. Every 17 days, the whole India will be covered to have the theme-specific time series analysis for the stakeholders. Coming in specific to the SAR CalVal activities at ISRO, we are having a pan-India CR network in which the objective is to have perform the radiometric, geometric, and polarimetric calibration of spaceborne and airborne SAR sensors, which can operate in multi-frequency and multipolarization. As well as another main objective is to derive the SAR image quality metrics for data product validation. And for that, we have permanent sites where the corner reflectors are deployed, and some campaign mode sites are also available where on campaign mode, we will be deploying the corner reflectors. So this is EOS4 fine resolution strip map data. So in which you can see the corner reflectors that are deployed, and this is the impulse response function. Apart from that, ISRO has come up with indigenously developed wideband active radar calibrator. So this transponder works in from L band to C band. So presently it is in the testing mode, and like in Rosamond we have the corner reflector array. So here also in southwest India we are having CalVal site which can be used for in the campaign mode. So these are the corner reflectors deployed at NRSC, Hyderabad, and we also had an experiment at Antarctica, and these are the reflectors in the Pan-India network. So to qualify the data, we need to do the geometric and point target analysis, and this has been done on the ScanSAR mode of data of medium resolution SAR. And the geometric accuracy was less than 50 meter as specified, and the impulse response function peak side lobe ratio, so they are within the limits. So presently our focus is on the polarimetric calibration. So EOS4, as it is having the hybrid polarimetric data, single look complex data has been considered for both strip map and ScanSAR imaging modes to perform the validation of the polarimetric parameters. So for that we have used the point target and distributed targets. And presently, as ScanSAR data is a burst mode of imaging, all the data sets are present as a different beams. So to have that beam-wise, burst-wise data, so all this burst has to be mosaicked so that we can use it as a mosaicked complete scene for the complete analysis. So for that one, first this Stokes parameters are generated, and then Stokes child parameters like degree of polarization, relative phase between RH and RV phase has been calculated, degree of circularity and scattering mechanism. So with those child parameters, decomposition techniques like M delta, M chi and M alpha are applied on the images to understand about the surface double as well as the volumetric scattering of different targets. So first we have done the analysis on the strip map mode of data, so where there is no burst or beam kind of acquisition. So here you can see the corner reflectors that was deployed in IMG, our NRSC CalVal site, in which the blue color represents the square trihedral and which has a surface scattering, whereas the dihedral has a double bounce effect, corner reflector effect, leading to the red color. So it implies it's a double bounce kind of scattering, and this is a scatter plot, and the degree of polarization and the relative phase. So different parameters like degree of polarization, relative phase, circular polarization ratio, ellipticity, degree of circular polarization and linear polarization, all these parameters are calculated over the deployed corner reflectors, including the transponder. So we can see the values are almost consistent for surface scattering, whereas for dihedral, which is having the double bounce effect, has a different variation. So this itself will say that the calibration of the system has been done. So this is what I was saying, mentioning about the ScanSAR point target data. So here, mosaicing of the burst is not a simple task. It has many intercrossings which has to be handled at the time of mosaicing the data, because there will be many number of bursts, and we have to find out the first valid line and number of valid samples in that line, and the minimum range of burst buffer that should be considered, start and end of the beams, considering all these parameters which comes in a sequential form. So everything has to be captured and made it as a single beam. So here you can see the beams, all the 8 beams of medium resolution ScanSAR data, on which individually the beam-wise hybrid polarimetric parameters are performed, and we have mosaiced all these beams into a single product. So here you can see the trihedral corner reflector, which has been deployed in our IMGO's CalVal site. And if you see the observations, the relative phase component for the burst mode data, because when we have the 2 bursts, there can be some overlap region. So when we mosaic it, there can be chances that the relative phase can change. So we have taken an area of common interest having the homogeneous region, and we calculated the relative phase, and it is measured to be around 3 degrees, so which is acceptable, and it is within the limits of the relative phase. And we have considered both the calibrated and uncalibrated data, so it is with the variation from uncal to cal data is plus or minus 4 degrees variation in relative phase and 2 to 3 degrees in ellipticity. Moreover, Stokes parameters are derived whatever has been derived are well within the limits, and has been verified with the corner reflectors, because they aid in the characterization of target properties based on the dominant scattering properties. And any data should be radiometrically stable. So especially for the ScanSAR data, where all the 8 beams are operated one after the other across the swath and in the along track direction, so the elevation antenna pattern, the variation plays a major role. So for that one, we had around more than 75 acquisitions over Amazon rainforest, and here you can see the gamma naught pattern of MRS systematic coverage, where the reference gamma naught is around minus 6.5 dB. So the variation is within that limit, and this is the mean gamma naught for both the polarizations RH as well as for RV pole. So you can see the consistency with respect to the reference gamma naught red line. So both the variations are within the 1 dB, plus or minus 1 dB as per the specs. So we have considered more than 75 data sets, and the absolute radiometric accuracy is within the limits. So finally, I would like to conclude that, so we had a brief description about the ISRO's ground segment activities, especially and moreover the payload capabilities of EOS-4, which is unique with its unique hybrid polarimetric feature. In ScanSAR mode. So till now we had strip map mode only, but this is a ScanSAR mode of operation, and ISRO's CalVal activities and its facility, and geometric, radiometric and polarimetric calibration and validation, which has been performed using the point and distributed targets, and its image quality metrics are discussed, and they are as per the specifications, and absolute radiometric accuracy is within plus or minus 1 dB, and this analysis of hybrid polarimetric data has been done for different standard targets like corner reflectors using the Stokes parameter based decomposition techniques, and the significant improvement is observed between the uncalibrated and the calibrated data, and now the readings are within the specifications. And EOS-4, which is ISRO's follow-on C-band SAR mission of RSAT-1. So it is also been operational with hybrid polarimetric level 3A products. So which are M delta and M chi decomposer products are also available. So which can be used for the land and ocean applications. And this calibration and validation of ScanSAR mode hybrid polarimetric data will definitely upscale the polarimetric-based applications which need a larger swath coverages. So for that type of applications, whether it can be ocean or ice, or it can be biomass, or it can be an ecosystem, agriculture, so the large swath with these capabilities of SAR polarimetry will definitely aid in the more upscaling of the polarimetric-based applications. And I thank others are grateful to ISRO for providing this opportunity to present at PolInSAR workshop. And we are also thankful to ISRO CalVal data processing and data planning and programming teams for their support and in carrying out EOS-4 data calibration and validation exercises. And to have a quick recap, so this is the complete full India mosaic that has been acquired with 17 days repeativity, having 18-meter pixels and line spacing. So it is being covered every 17 days, and one descent mode is dedicated to have this continuous coverage. So that it will aid in the theme-specific time series analysis. Thank you so much.
Thank you very much. A very interesting mission. Are there any questions from the audience?
Thank you, Yasri, for this nice presentation. I have a question regarding the transmit polarization, because you mentioned you have both linear, dual, and hybrid pole. My assumption is that your transmit polarization is always circular. Is that correct?
Which one, sir?
The transmit polarization is always circular, or you're also able to transmit linear.
This hybrid pole you're asking?
No, in general, because you mentioned as well you have a single pole, a dual pole.
Yes.
And the question is whether the single pole or dual pole, whether they can also be VVHH or VVDH.
Yes. VV, HH, dual pole means HH plus HV, VV plus VH.
Okay, and as well then circular, sending circular and receiving both linear polarizations for the hybrid pole.
Yeah.
Okay, thank you. Okay, excellent.
Yeah, I'd like to ask about the data policy. Perhaps I missed it, but what's the data access for non-Indian users?
Okay, so EOS-4 has the capability to acquire in other regions also. So apart from India, so you can you can ask for the ordering of the data from one website. It is an ISRO's web portal which has been dedicated for the users to order the data and to download the data. So with that portal you can register and then you can order for the products. So even the data product description document is also available in the same link, so that even the sample products for level 2 enhanced georeference products are also available, so that people can work on that.
Okay, thank you.
Thank you.
Thanks. Thank you very much for this presentation, and congratulations also for this calibration results, which are really perfect. Looks very great.
Thank you.
Thanks for these. Yeah, I had a little bit a similar question, not the distribution of the data, but more if you have a mission concept, right? If you have some concept, or are you just acquiring the whole time? Because I imagine you have a kind of duty cycle where you just get over certain areas some data and not the whole time. So the question is, do you have a mission concept somehow?
Yeah, so the imaging duration in a given orbit is 10 minutes. Okay, so in that, one of the orbit is dedicated for this systematic coverage, and other orbits can be given to have acquisitions on some other part of the Earth. So in that way, we are having not less than 1, sometimes 2, based on the orbit and the location. So sometimes we get 2 orbits per day also.
And you're acquiring continuously then?
Yes. So
Okay.
every 17 days, the same area will be, because it is a left loop direction in the descending mode, and with a specific incidence angle, because most of the applications related to agriculture require a specific angle around 36 degrees, and with dual pole. So with that configuration, India being an agricultural country, so one of the orbits has been dedicated for that application.
Yeah, thanks a lot. I've seen some of the images there, look really fantastic. Very
Yes.
great.
Thank you, thank you.
Yeah, okay, it's also related to the previous 2 questions. And are you ever performing acquisitions also over Europe? And then in this case, could we access those?
Acquisitions over Europe?
Yes.
Yeah, for EVOS4, the acquisition can be done, sir. So this EVOS4 doesn't have any restriction. So throughout the globe, any requirement of a given area can be acquired. So this is open to the entire Earth.
So could we address the question, the request to you then directly?
Yes, yes.
Okay, thanks.
Yeah, so you can, there is Bhunidhi portal where it has given the link where you can order and where you can put the request also. So you can specify your requirements, like which polarization, what is the incidence angle, imaging mode. So accordingly, the planning will be done, and it will be informed to the user that these dates the data is available. So if it is okay, then they will proceed for the planning.
Thanks a lot.
Thank you. Achha, I mean, here, Kuwait, one sample I have put, sir. Yeah. So one on USA, one on Australia, and another one, the topmost left, is on Kuwait. So like that, we can have acquisition throughout the world.
Okay, so if there are no more questions, then thank you again.
Yeah.
And
thank you so much.
And I'm happy to introduce our next speaker. It's Lan Qing from ETH with a presentation on Antarctic sea ice elevation and roughness retrieval using Polarimetric SAR interferometry.
Good afternoon, everyone. My name is Lan Qing Huang. I'm currently a postdoc researcher at ETH Zurich. So today I will present my work about using polarimetry SAR interferometry on sea ice application in Antarctica. So first, what is sea ice? Sea ice is frozen ocean water in the polar regions, and sea ice is actually a very sensitive indicator to global change. So the topography of sea ice is determined by ice ridges, shear zones, and hummocks. In addition, the snow on top of the sea ice can also affect the surface topography. Therefore, in order to characterize the sea ice topography, we need not only to consider the sea ice itself, but also the snow cover on top of it. Now let's move on to the data side. The data I used is a coordinated campaign between TenderMax from DLR and the Airborne Operational Ice Bridge optical data from NASA. The campaign was conducted on 2017 in October. As you can see from this map here, the location is in the western part of the Weddell Sea near to the Antarctic Peninsula. The yellow rectangulars here, they shows the footprint of TenderMax imageries, and the white line, they are the flight track of the airplane. So now let's zoom into the 4 scenarios which I used in my study. The backscatter intensity values of the 4 scenarios are shown on the right hand. Where you could see the higher backscatter intensity, which means the brighter value can be interpreted as rougher and thicker sea ice, whereas the darker colors corresponds to the smooth and thinner sea ice. In addition to the TenderMax data, we also have data from digital mapping system. The DMS is equipped on the operational S-bridge aircraft, and it can acquire optical images of the sea ice. As you can see on the images here, from this optical image, the sea ice structure is very clear. We can see the deformation of the sea ice, and also we can see whether the sea ice is covered by snow or not. By using the photogrammetric techniques, this photo can be converted to digital elevation model, DEM, and hereafter will be referred as DMS DEM. And this DMS DEM is used as the reference data in our study. So, and I also want to point out here is that in the sea ice study, co-registration is a very challenging issue because the sea ice is always moving. In this campaign, the DMS data was acquired 6 hours before the TenderMax acquisition. Therefore, I manually compensate the shift of the sea ice during these 6 hours because of the sea ice drift. Therefore, we can ensure that the TenderMax and the DMS data, they are well aligned with each other. And the objective of our study is to generate the sea ice elevation from single pass INSAR data. So here, the sea ice elevation is defined as the height from the snow-air interface relative to the sea level. So in cryosphere, we also call it snow freeboard. But if we want to measure it using TenderMax data, what we actually measured is the height of the INSAR face center relative to the sea level, because the X-band radar, it can penetrate into the snow and even upper part of the sea ice, depending on the particular type of ice. So for the older sea ice, when they are older and thicker, the desalinity process can happen. Therefore, in this case, the radar can penetrate into the upper part of the sea ice. Therefore, that's the key issue we need to cope with when we want to use INSAR to derive the elevation of older sea ice. So here I highlight the part which is a penetration bias, and it is this penetration depth that we need to use a model to correct or compensate, and therefore to get an accurate snow freeboard. As I said, this penetration bias is only considerable for older sea ice. For younger sea ice, we assume that the salinity is very high, therefore the radar cannot penetrate into the ice, therefore just the standard INSAR process can be used to derive the digital elevation model. Therefore, just a short recap is that in order to accurately retrieve the CS elevation, we need to first do the CS classification based on the penetration bias. So here I plot the proposed methods in the flowchart on the left. The input of our method is the TenderMax data, and in the first step, we classify the sea ice into younger ice and older ice. The younger ice is defined as the thinner ice where the penetration depth is below 0.3 meters, and the older ice is defined as the ice with penetration depth above 0.3 meters. And the classification method is shown in the middle flowchart here. We use the random forest as a model, and we tried out different features, including the backscattering-based features, polarimetry, and also interferometry-based features. And we ranked the features, and we selected the 5 top-ranking features as the input of our model. And we split the data into training side and the testing side. And for the testing side, we it indicates that the accuracy is 0.84. Given that we have a quite balanced data set, therefore this accuracy cannot prove the effectiveness of our method. Therefore, we apply this classification method to all 4 scenarios and then generates the classification map for all data. So now we already classified the CIs into younger eyes and older eyes. As we have talked that the younger eyes, we can just apply the standard INSAR processing because the penetration is negligible. And for the older eyes, we need to find a way to compensate this penetration bias. Therefore, here we applied a model which was proposed in our previous studies. We call it a 2-layer plus volume model. And the equations is shown here below. On the left of the equations, this is the complex INSAR coherence, which can be measured from the data. And on the right part of the equations, the INSAR coherence is decomposed into 2 parts. The first part is the topographic phase, which is exactly what we want in our study. And the second part, it corresponds to the decorrelation, where we're taking into account the surface scattering from the snow-ice interface and the ice-water interface. So from these equations, we know that this model, it has 3 parameters. The first one is the layer-to-layer ratio. And we also developed empirical functions to estimate the layer-to-layer ratio using the Polarimetric coherence. And the one which corresponds to the snow depth, it can be used, we just use some external data which measure the snow depth as the input of our model. And then this model, we only have 2 unknowns, and we can just invert these equations to solve the solution. And then we get the phi 0. By using the capacitor, we can convert this phi 0 to height, which is the topography elevations. And now we have already generated the height for the younger eyes and the older eyes. Therefore, the last step is to merge the results of a different type of eyes into an entire DM. So here I would like to show some results. So over the study area, we have 4 scenarios. Here I visualize the first scenarios, where you could see that the topographic elevation, it's ranged from 0 to about 2.5 meters. And we also have a zooming of area 1, 2, and 3. We compare the topographic phase from the SAR-derived method and also the reference data from DMS. And we see quite a good agreement between each other, which kind of virtually prove the effectiveness of our proposed method. And we also did some quantitative analysis. On the left images, the second column, it is a classification result based on our method. So in the first step, we classify the CIs into older eyes and the younger eyes. So here is the result for the 4 scenarios. And then the final SAR-derived DM is shown in the third column here. Because for each scenario, it is overlapped by a narrow strip of DMS data. Therefore, we just kind of extract the height and plot the height profile of the 2 acquisitions, which you could see on the right images. The blue lines here, they are the reference data, and the orange lines here, they are the SAR result. We could see that our derived results, it can capture the variation, the topographic variation very well. And the root mean square error between the derived data and the reference data are below 0.25 meters for all scenarios. Since now we already validate the effectiveness of our methods, we just apply this method to extended area in the Weddell Sea and the Ross Sea in Antarctica. And we download 162 TenderMax images in total and derived the digital elevation model in Weddell Sea, which is shown in the middle image here, and in Ross Sea on the right hand here. And what we found interesting is that the sea ice elevation near to the Antarctic Peninsula in the very northwest part of the Weddell Sea, it shows quite significant deformation. The average elevation is above 1.2 meters. And then if we go outwards the coastline, more towards the ocean, we found that the sea ice elevation becomes lower. And then if we go much more to the southeast directions, near to the continent, we found that the elevation started to grow again. And in the Ross Sea, we found that the sea ice tends to be thicker with a higher elevation nearby the Terra Nova Bay, and then go to the northeastern direction, southeastern directions. The sea ice becomes shorter or becomes thinner. And statistically, for this regional variation of sea ice topography, we calculate the average elevation and roughness for each segment. The name of the segment, you can find it on the geolocation map. And what we found is that for the segments I highlight in the red rectangulars here, they all shows higher, they all shows average elevations above 0.5 meters, which gives us a conclusion that the sea ice in the northwestern part of the Weddell Sea exhibits higher elevations than other regions. And we try to interpret this result. So here we also plot the ice chart data, which gives us the different type of sea ice in the Weddell Sea. And what we found is that for all the segments which in the northwestern Weddell Sea, they are covered by sea ice, by multi-year sea ice more than 57%. So which means if we assume that the multi-year ice usually are thicker and therefore have higher elevations, so this can explain what we observed here. And so here comes to my conclusion. So first, we have talked about that we proposed a method to retrieve the sea ice elevation from dual polarization interferometric soil images, taking into account the different penetration bias in different type of ice. And then we apply this method to extended area in the Weddell Sea and Ross Sea. And we found that the sea ice undergoes significant deformation nearby the Antarctic Peninsula. And we also noticed that the sea ice in the northwestern part of the Weddell Sea are higher than the other regions. Finally, we want to highlight that sea ice topography can provide add-on informations to the sea ice classification mapping. So maybe in the future, we can provide a kind of operational topographic map in addition to the currently operational sea ice classification map. So that's it. I thank you for your attention, and I will go back to the conclusion slide here.
Thanks for the presentation. Are there questions?
Hello, thank you for your nice presentation. I just want a simple definition. I mean, I have known poly basis, but what is this poly ratio? I mean, can you define it?
Sorry, what issue?
Poly ratio. You have used a feature called poly ratio. What is its definition?
As a poly ratio, it is the poly first, which is the VV plus HH, and the poly second, which is the VV minus HH. And then we just calculate the difference between the poly 1 and the poly 2. So in dB scale, it is subtraction, and in linear scale, it is the ratio. So that's why we call it poly ratio.
Okay, and did you also try like copol ratio?
Yes, we tried it, but as I said, we only selected the 5 top ranking features. So obviously the copol ratio we tried, but unfortunately it is not in the top 5 features. So we just excluded it.
Okay, thank you very much.
Thank you.
Thanks for your presentation. In your two-layer model, so you have two heights. So one is HDMS and another one is HNSAR. For HDMS, you measure the height of the top snow layer, and but for the other one, it starts from the face center of the ice. So there is a difference between these two heights. Yes. Maybe you mentioned, but I didn't catch it in your validation. Did you account for this difference between HDMS and HNSAR?
Our objective is to calculate the height from the very top surface, so which is HDMS, and that's why we use it as a reference data. And we use that two-layer plus volume model to correct the in-surface center into to the top surface. Therefore, we use the DMS DM as the reference data. So I'm not sure if I...
No, I mean, yeah. The difference between these two heights, how did you corrected your HNSAR? Or in the end, your HNSAR is corrected or calibrated or some way? Or because there is difference between these two heights? If you show your two-layer model...
Yeah.
Yeah, here, just next slide. So the HDMS starts from the top of the snow.
Yes.
But so how did you, when you show your experimental results, so did you correct or calibrate one of these heights some way, or so there is some bias in between these two? Okay.
Yes.
Thank you.
Thanks.
Are there more questions? Or? Then thank you.
Thank you.
Our next speaker is Torbjørn Eltoft from the Arctic University of Norway, speaking about polarimetric analysis over sea ice. And I also have heard he has a little interesting polarimetric puzzle for you.
Good afternoon, everybody. Yeah, I'm going to talk about the polarimetric features of sea ice and the data were collected during a cruise we had to the Western Fram Strait in April-May in 2022. My co-authors are Debanshu Ratha and Laurent Ferromil. What is this? This is the wrong. Okay, so this, I have a feeling this is the wrong presentation, but let's see what comes. Yeah, so this shows the track of the cruise, and these red dots indicate locations where we did some sea ice measurements. And we will actually be heading to, let me see if I can, to this area here, where we have fast ice. And the reason for this is that since the ice is not moving, we are able to study also temporal variations in the features. And this image shows the fast ice area to the left and the drift ice area to the right. And our station is just at the border, so we will also have some drift ice in the area. And you can see here, this is an ALOS-2 image from May 3rd and 4th, and you can see how the drift ice has changed, whereas the fast ice is still the same. Just to give an impression about how SAR see ice, I put up an optical and a SAR image showing the same patch of sea ice. And you know that if there is snow on the ice, the optical image will not be able to see the ice, whereas the SAR penetrates through the ice, and you can see details in the sea ice that can help us understand the characteristics. And we also know that sea ice is subject to a lot of forces from wind, waves, and currents. So you will have a lot of different structures on the surface which will give rise to various types of scattering, like surface scattering, which probably is the most dominant. But you will also have occasions of volume scattering and double bound scattering. And as you know, polarimetry can, in some sense, help us to decompose this. So this shows at the upper row the three polarimetric channels where we have HH, HV, and VV. And you see that the HH and the HV and the VV are more or less giving the same kind of information. Their intensities are more or less the same, whereas the HV is much lower. And if you look at the lower row, we have the diagonal elements of the T matrix. And as you can see, the component that is supposed to represent the surface scattering is much brighter than the double bonds and the volume scattering components. Yeah, so this is the area which we will concentrate on. And since we went into this area, we know exactly what's around it. And as you can see, we have this flow here, this flow here, which we identify as a first-year ice flow. We have a refrozen lead here. We have some area of thin ice where you can see a lot of shadings. And you have different types of deformed ice here. And here you can actually see the ship. And in this white dots here, they are icebergs. And to the right now, we have shown a polarimetric decomposition of this polarimetric image. And it kind of shows that in the deformed ice, you, of course, get very strong signals, whereas in this flow here, we have very, very low signal backscattered. And in the thin ice area, we have a quite nice palette of colors representing the various ice structure that you can actually see in this thin thin ice. Yeah, so this is giving an impression of how the area looks like. This deformed ice here is right behind the ship. You see the ship here, and this flow here is this flat ice that we have here. And this shows a mosaic made from drones that were flying over the area, so we kind of have a good understanding of how the situation is here. So we would like to do the segmentation of this image, and we will use this matrix here, which you all are familiar with, to get the Jones vector of the scattered signal. And from the scattered vector, we create this C matrix, and from this C matrix, we are able to extract several polarimetric features that we used for classification. So we use this relative kurtosis, which is a measure of kind of the texture of the image. We use the geometric brightness, which is the determinant of the matrix, which is kind of similar to the span. It gives a kind of the total measure of the total power. We use the Cooper ratio, we use the cross-pole ratio, we use the real and imaginary part of the coherence between HH and VV. And we put this into a mixture of Gaussian scattering model, classification model, where we to segment the image. And this is an example of how the image looks. And you can see that this flow here is basically divided into two different classes. We have this refrozen lead, which is very dark in the polarimetric images. But you can see that there actually is two classes there. And it turned out that this has a very thin ice on top of it, and this blue segment, I think, is more or less open water or very thin ice. We also see that the deformed ice come very clearly out, and we see that in this young ice, where you have all these colors, you get a lot of clusters. And I don't know if in this presentation I have it, but I tried to put in an image just to illustrate how this looks like. So we can also do this kind of analysis to look at the different features, which segments they pick out, and we can of course identify which features are important for classifying or separating out the different segments. And this is showing the geometric brightness. We have the Cooper ratio, which I will come back to. And what is interesting with this Cooper ratio is that over this flow here, we actually have a situation where we have a larger HH than VV. And when we know from our previous information that this flow, there is very little depolarization, very little HV, there is almost no, we cannot measure any double bonds. So this is a kind of an interesting observation that we do. And I will come a bit back to this, maybe it's the next slide. Now, this is showing the cross-pole ratio. And the cross-pole ratio, as you can see, is very good at picking out this very thin ice. And this is also true for the Cooper ratio, so which is a familiar feature for analyzing or detecting thin sea ice if you have that available. So, yeah. Okay, so this is showing a time series of the same area. And if you go through this, it starts on the 11th of April. And we have the 28th of April where we were there. Then we have till the 18th of June. And you can see the flow here in all these images. You see that the drift ice is changing, so it's moving away and it's opening up. And we have kind of a strange effect here, where you see that in this image there is a very large green component. And it might be that we are in a situation where we have kind of a dual variation, where because the temperature is rising exactly on that day. And we can see that, when we look at temperature from the ship and from stations nearby, there is a rise in the temperature exactly in that period. And from the 29th of May until the end, we are up in the melting season, and you can see that there is a dramatic change in the polarimetric features. So I wanted to know how much information can I get from dual pole from this data. And I used a similar approach. I simply used the dual pole version of the covariant matrix, and I generated these same features in addition to the kurtosis and geometric brightness. We used the copolarization intensity and cross-polarization intensity, and we used this cross-polarization ratio, and I put in this linear polarization, degree of linear polarization, which is generated from the Stokes parameters in the same way as we saw yesterday. And this is showing to the right the classification using only the dual pole data. And we see that we can pick out the flow quite similarly. Well, it's not that same division between the two groups, but I think this is quite a nice segmentation. The only problem, I think, is in the thin ice area, where we see that there is more randomness in the segments. And okay, so this is just to illustrate that also for the dual pole you can get a good detector for the thin ice using this degree of linear polarization, and also this degree of polarization. This is the one that you can generate from dual pole, and this is what you get from a single pole, from dual pole. This is from quad pole, and these are from dual pole. Yeah, actually this I wanted to put in just to illustrate that if your signal penetrates into the ice, there is a different structure in the first year and the multi-year ice, which polarimetry could help you to separate between these two because of the, let's say, internal structure. Okay, let's move on. Yeah, if you go back now to the, you see this is the confusion that I saw when I started. Let's go back to this problem that we saw with the H being larger than the VV, and of course, if you have a multi-layer model, you will have all this, and you have penetration down to the sea ice. You will have multiple scattering event. But when we did the analysis of the snow profile, we saw that there was a saline layer at the bottom of the snow, and this was very, very rough. And our suspicion is that this somehow generates some double bounce effects that causes this HH being larger than the VV. And this shows the temperature. Yeah, this is an image of the profile. And yeah, I don't know what comes next. Yeah, this one. Yeah, this is showing the intensities of the C and the T components. And I will concentrate on the C. You see that over the layer, when we get into here, we have H being larger than the VV. But when you go into the melting season, this disappears. And this is, yeah, we can come back to why. Whereas when we look at the rough ice, we have a drop in the HV, but we have an increase in the HV over the thin layer. So, and I think this is an effect of the snow that's getting wet, and you get more or less the surface, and you have some volume scattering that increases in the snow. And here, this is in the multi-year. So the snow is basically filtering out the signal that goes into the ice. Yeah, I think I'll stop there. These are some images from the groundwork.
Thank you. Interesting how sea ice looks like. Are there any questions? I think in the back was maybe the first one.
Thank you very much for your interesting presentation. So I was just wondering, like, when you are going for the segmentation, how to determine that how many segments I am going to get from the features?
Yeah, this is this you can do it in two ways. You can either decide, you can put a maximum and let a sensitivity parameter determine how many clusters you get. So there is, basically it determines, the algorithm itself determines how many clusters you end up with by setting a sampling rate and a sensitivity parameter.
Okay, thank you.
Question here from.
Oh, actually, I have the same question just as the previous one about the number of the clusters. But I'm wondering, maybe can you comment a little bit how we can validate the number of the clusters it is when it's generated from the algorithm? Because in classification, usually maybe we could be over-classify a little bit or sometimes under-classify a little bit because the CIC is quite complicated. So, yeah.
I think, I mean, the number of classes that we had there is too much to be useful. I mean, it depends on what you want to do with this. When you look at an ice map from an ice service, they have 5-6 classes, and the number of classes that you see is the number of classes that the data gives you, but they are not necessarily important for, let's say, an ice information service.
Thanks.
And another question here in front.
Oh, yeah.
Oh, sorry.
You said number 9?
No. Yes, this one. Can you say why it is dark, why it is bright? If a thin ice is why dark? What is the thin ice means? What is the depth of thin ice? Why it is dark?
Well, it's not necessarily the thin ice that is dark. It's the smooth ice that is dark. So if the thin ice is rough, like you have some rough ice here, which is this area, you have very thin ice. But this is a refrozen lead, so the ice is very smooth. It's almost maybe a few centimeters. Whereas here you have also thin ice, but the surface is rougher. And you see that it has quite a much brighter signal.
Do you have photographs? This?
Excuse me?
Photographs, field photographs. That.
What is it? Oh yeah, we didn't do any coring here. We did coring here, and here it's 1 meter.
All right, then there are no more questions. Thank you very much again.
I want to introduce the last speaker of today. It's Peter Lanz, and with a talk on automatic refugee inflatable vessel detection with Polarimetric SAR.
Yes. Hello, everybody. Thank you for the introduction. We've been working on a very specific application. We were working on the automatic detection of refugee rubber inflatable boats. And the motivation of our project is the ongoing humanitarian crisis in the Mediterranean Sea or at the southern European maritime border regions. We can see here on the map that most of the incidents are concentrated on a very small area, or quite small area, between Libya or Tunisia and Italy. And yeah, this region where most of the incidences happened is about 450 by 350 kilometers big. So this is the search and rescue area zone. And in this region, most of very often those kind of boats of rubber inflatables are used for the passage. They are 3.5 meter wide and 12 meter long, and they are full with 80 from 80 up to 170 people. So they're fully packed with people. And that's why we concentrated on exactly those vessels to detect them. And the vision which is behind our project is to have like a infrastructure that continuously has satellite SAR imagery that can be automatically searched for after those rubber inflatables. That's our part we're working on, to increase the situational awareness for the search and rescue ships on the ground. And since we don't have access to real data, to real satellite imagery of such boats, we did a data simulation approach. So the first step, we tried to find out how to simulate people on the boat. And that's for that we used a handheld radar, and we tested different kind of materials, and we found out that clay pebbles, which are wet and put into airtight bags, they are very usable for. So they look in the X-band, in the C-band, they tend to look quite similar to human humans, to human bodies. So you see on the image we put last year, we set up a data collection campaign, and we put a rubber inflatable that looks exactly like those which are used in the central med. And we filled it up with those clay pebble bags. And we collected Teracer X data and also data from other platforms, but we mainly use dual pole Teracer X data. And this from this collection, we have different polarizations, different incidence angles, and 2 different boat orientations. And then we combined it with archive Teracer X data, dual pole Teracer X data, with different wave heights to find out what's the maximum wave height we are able to detect those rubber inflatables with which detector. And this is the outcome of the Teracer X archive research. So we found for different dual pole polarization channel combinations and for different incidence angles, a specific number of different images with different wave heights, so up to 6.5 meter, which is before 8. And we verified those wave heights with in situ buoy data and with wave models. So for each image we used, we have a double verification of the wave height. And this is now an example how we did the data simulation. So we used the pixels of the boat with that looks like in the SAR image as if it was full with 80 people. Those are the yellow pixels, and we copied those pixels into the images of the open ocean with different wave heights. Yes. Then, in the next step, we worked on detector fusion. So we tried to combine different kinds of detection algorithms, and we did this at the detection binary mask level with either an or an and logical operator. And the other thing we did is we did dual pole detector development. So we used we took the original Interferometry detector, which is a volume scattering detector, and then we inversed it to have kind of a surface scattering detector. We call it pole ratio 2 in our work. And then we took the original Interferometry and applied it to copolarized dual pole data. And this is like a double bounced dihedral scattering detector. We call this pole ratio 3. And this one also we inversed, and this we call a Bragg scattering detector, something like that. And we call it pole ratio 4. And we also added a T22, it's the element of the T matrix, the T22 element. It's a double bounce detection, and it's like, it makes sense because the vessel in the ocean, the theory is that it produces some kind of double bounce scattering. Yes, and in the next step, then we did we tested a number of well-known detectors, what you see here in the table. Those are, the numbers are area under curve values from rock curves. And those results, so this table is our basis to identify which detector works best at which polarization combination and at which incidence angle. So we found out that the PMF and the PWF work very well. The CRC4 works good. The polarimetric symmetry detector works well. And interestingly, the polarimetric entropy detector is the best one for low incidence angles. And what was also very interesting, the entropy detector, according to our test data set, works better with increasing wave height. So all the other detectors, the detection quality goes down when you increase the wave height. But for the entropy detector, you see here that detection quality goes up at least until 3.5 meters here. Yeah, and then we use those detectors which worked best at the detection testing. We use them to find out which detectors we can, how we can improve the detection quality by combining some of them. So we tried to combine 2, 3, or 4 detectors, like of the best ones for dual cross-pole and for dual copole data. And what came out was that in the dual cross-pole case, the PWF works best. Like the PMF, the polarimetric match filter, they have similar performance. And the second best was the polarimetric symmetry detector, and the third was the combination with an OR of the pole ratio 1, which is the ID-pole rad, and the pole ratio 2, which is the inverse ID-pole rad. And for the dual copole case, it turned out that the polarimetry entropy detector combined with the T22 double bounce detector combined with a logical AND works best, and the second is the polarimetric whitening filter. And here we see more of the results for the cross-pole detector. So as I said, the PWF works best. And we see that for higher spans, which means higher span means higher, it can be interpreted as if there were higher wave heights. So for the different cases of higher wave heights, you see that the PWF works best. So there's the biggest difference between those three. And our pole ratio OR detector came in third place. And for the dual copole detectors, we see that our combination of the T22 double bounce and the entropy detector outperforms the PWF with our data set. And we also see that at high spans, it's where it works best. And this we give this credit to the entropy detector, which works better when you have higher waves. Yes, and another kind of result when we say we want to have 80%, we want to have more than 80% of probability of detection, and we don't want to have more than 1% of probability of false alarm. Then we see that at the copole, with the copole data, with the HT22 end detector, you can go up to 1.5 and 1.3 meters. And in the cross-pole case, with the PBF detector, we can go up to 2.4 or 1.6 meter wave height. And in the VHVV case, we can just go up to 0.5 meter. So the VHVV channel polarization is not very favorable compared to the other two. And our recommendations we find is that medium or high incidence angle are better than low incidence angle. That's kind of well known. The vessel orientation relative to the line of sight had no significant impact on the results. And here's another kind of how to present the results. At the probability of detection of 90%, you see that in the VHVV case, the probability of false alarm goes over 1%, and in the other two polarization combinations, it's better. And for the future work, we are thinking of improving detection results, like decreasing probability of false alarms by doing blob analysis and size filtering. Like if you have a big wave, then you can say, okay, it's too big than being the boat, so you can like sort out some false alarms. We were also thinking of implementation of a priori wind field estimation to to know what's going on, how high are the waves in my image, so to be able to better interpret the detection result. And what would be the best thing is if we had like real data, like collect real sea truth data of a fully occupied refugee vessels. All right, thanks for listening.
Thank you. Are there questions?
Thank you for the very interesting talk. I'm curious, so you said that kind of you had the ground truth generated on a lake, basically, and then you pasted those pixels into kind of the sea background, right? But how do you think the effect of the interaction between the sea and the boat itself might bias this kind of approach?
Yes, that's thanks for the question. That's what we're missing in this case. We miss the interactions between the sea, like the waves and the boat. Around the boat, we also have on the lee side of the boat, you have like lower waves because of the wind not going there and producing waves. So this is also a thing we don't have in this case. But the boat, the boat has a flat underground area. So this thing we take with us. So it flattens out the surface of the ocean, like it flattens out the surface of the lake. And that's also the reason why we combined the IDPO rad, like the double bounce detector, with the inverse IDPO rad, with the surface detector, to see either the double bounce coming from the people in the lake or on the water surface, and also to see this flattened area, like next to the people or beyond the people. If you have side-looking radar, it's possible to see it. And and what you also don't have is that bigger waves would rotate the boat in different directions. This is also what we miss. On the lake, it's like stable.
Yes, thanks you. Also from my side, I think that's very interesting and it's very important, right? That's a very important application, but also very complex thing, right? As you just explained, not so easy. So, and the other point that I also see is the spatial resolution, right? Because these boats are very, very small. In addition, not so big. TerraSAR-X is probably a solution, but I'm not sure if this is enough, really. Because you need to do some averaging also when you use polarimetry, so that's also a little bit a problem. There's a lot of difficulties. So my question would be probably more going into the direction, why only rubber boats? Nowadays we know there are also other boats, right, which are in danger and would be important also to map or to track. Is this a solution to go to bigger ships? Or to not rubber, right, but real ships? I don't know.
Thanks for the question. We decided to concentrate on those because those are the most vulnerable. When they start, they're basically in distress, so they're not seaworthy at all. You can't even go on a lake with people on it. So that is the one reason, and we thought the bigger boats, migrants sometimes use also like old fishing boats or bigger boats, but for that I think that the normal vessel detection systems already in place to find them, because they're like higher up. They're made of metal, or they have metal parts sometimes. So we try to concentrate on the really very difficult, the most difficult object. And being able to find that, we can also apply our result maybe to a little bit bigger objects with metal parts. That was so, yeah.
So then it would be only a question if you can finance, for example, a real example, right? This somehow not to put people on boat, but at least to have the boat somewhere in the Mediterranean Sea or so, and then to have an imaging there.
Yes, that's part of the vision, that there's some supranational or national body that provides the funding for continuous data, yes. Thanks.
Someone else? Okay, then thank you.
Thanks.
Well, I mean, this was the last talk of today. We don't have a fifth presentation. In theory, we still have time, so if someone wants to discuss anything or raise a certain point regarding sea ice and ocean applications or mission calibration, now is the time to speak up. Otherwise, I also remind you of this online discussion platform, Padlet, where you can contribute with research ideas, gaps, recommendations to the community. And then maybe also we have to say more tomorrow in a summary session. But otherwise, thanks for listening and see you tonight in the party.